function of the conference start at 9 o'clock up to 9:30. Thereafter, Professor Bala will talk 9:35 onwards. Thereafter, yeah. Professor, hi, Professor. Good morning.
Good morning, everybody. Good evening, everybody. People all around the world.
Good morning, sir. Good morning.
Good morning.
Yeah, good morning. Yeah. Okay, now it is time. Let us start the program. I think others will join in the first. Okay, Dr. Papa, please.
Okay. Hello, everyone. Namaskar. Welcome to the 8th International Conference in Statistics for 21st Century, jointly organized by the International Statistical Fraternity, the Department of Statistics, School of Physical and Mathematical Sciences, University of Kerala. We have got a galaxy of eminent stars in statistics with us today, and I welcome you all once again with utmost happiness to 4 days of intellectual indulgence. Let us start the inaugural session of the conference with a moment of silent prayer and gratitude to the Almighty. Please. Thank you. I would now like to welcome Dr. Satish Kumar, Director, School of Physical and Mathematical Sciences, and the convener of the conference, to say a few words of welcome to the gathering. Satish, sir, please.
Warm welcome, very warm good morning to all. In fact, we are here in the inaugural function of the 8th International Conference on Statistics for 21st Century. We call it as Icstc 2022. I find this day very auspicious as several stalwarts in the area of statistics from all over the world joined together in this gathering, and also in coming 4 days to deliver talks and interact with us in this virtual platform. Eminent statisticians like Professor Hira Kaul, Professor Balakrishnan of McMaster University, Professor Barry C. Arnold, Professor Ashish Sengupta, Professor Bimal Sinha, Professor Arivarignan, Professor Somesh Kumar, Professor Lachmander from Sweden, and several others. Lot of Professor David Banks, yeah, and Professor Kusubavisky, Professor Malay Ghosh, Professor Thomas Matthew, Professor Jaya Sargokovin, Professor Kundu, and Professor Kibria, Professor Gauri S. Datta, and several others are there. Professor others are there in this gathering. Sorry for naming all of them. Professor Indranil Ghosh, several others are there. I think you can see their names there. Around 100 or more than 100 speakers are there in the invited group, and more than that, more than 150, 160 are there in the contributory presentations. Among them, around say 84 compete for a particular best research paper award from the young group of below 40 years. And several honoring sessions were also arranged as a part of this conference to honor our former professors of this department as well as our alumni, especially Professor U.S. Nair, Professor Miss George, Miss Eliama George, Professor Krishna Pillai, Professor M. Mathai, Professor K.S. Pillai, etc., etc. And several other, in fact, Professor T.S.K. Mutha, the Young Statistician Award is also, competition is also here in this field. So, please. Now, my duty is to welcome great professors like especially Professor Hira Kaul has agreed to inaugurate this conference. I utilize this occasion to, first of all, welcome Professor Hira Kaul to this gathering, this inaugural function.
Namaskar, everybody.
Good. Next, the professor, our former professors, Professor Kalyanaraman sir, Professor Yagin Thomas sir, and also Professor Balakrishna also agreed to, as the present ISPS president, agreed to felicitate this conference, this inaugural function. I utilize the occasion to welcome my guru, Kalyanaraman sir, Yagin Thomas sir, and Professor Bala from Kusat, also this. I also utilize this occasion to welcome those stalwarts of the area, presently Professor Barry is here in the group. Probably Professor Bala also joined in the meantime. Other professors, I utilize this occasion to invite each of them, all these stalwarts, especially the delegates of the conference. They are in fact the success behind any such these types of events. With your blessing, and let us go. I hope we have a very good days of academic as well as research level interactions in this coming 4 days. With your once again wish you all. Let us hope for a great moments in these 4 days. Let me to remind with you.
Thank you, sir.
And once again, welcome all, please. Okay, please.
Thank you, sir. We have got Professor Hira Kaul with us today. Professor Hira Kaul actually do not need any official introduction to the statistical fraternity. He's the emeritus professor in the Department of Probability and Statistics, Michigan State University, and is a person who is internationally renowned among the statistical academia. He's a visiting professor to a number of internationally renowned universities, including the University of Sydney, the University of New South Wales, North Carolina, and as well as IIT Mumbai. And he has served us. Served us in various posts as editor, as a referee of many renowned journals as well, including the Golden Jubilee volume of the Journal of Indian Statistical Association. He was the co-editor of Statistics and Probability Letters, and also the associate editor of a number of renowned journals. His areas of expertise are reliability, survival analysis, non and semi-para, and as well as inference in stochastic process. So we are extremely happy to have you here with us, sir. And I request you to kindly inaugurate the conference for us today. Welcoming you, sir.
Thank you. Thank you very much for your kind words. And so how do I share a slide now?
Sure, sir. You can share it.
I do hit this one here.
Just there's an upward arrow, Professor.
Share, select.
The bottom, there is an upward arrow.
At the bottom of the screen, sir, there is an arrow mark, upward arrow.
Yeah, I'm at that. I'm now on the slide. It says window or screen.
Click on the enter screen.
Screen, okay.
Yeah, then
allow this.
Click in the middle of that box coming. Yeah, now it's coming.
It is coming.
Yeah.
Yeah, presentation.
Yeah.
You can go to the your presentation. Yeah, Professor.
Do you see it? Do you see my slide?
You can see, Professor. You can see. You can make it bigger size. Okay, if needed.
All right. So.
Okay, Professor. It's fine.
About 3 days ago, Professor Satish Kumar asked me to do this function, inaugurate this function. And I quickly thought of a few things to say. It's indeed my pleasure and honor to inaugurate this conference, as I've said, organized by International Statistical Fraternity of the Department of Statistics, School of Physical and Mathematical Sciences, University of Kerala. As we all know, the Department of Statistics of the University of Kerala, Trivandrum, was established in 1945. It is the second oldest in the country. It is older by 10 years than the similar well-known departments like University of California, Berkeley, and the Michigan State University. Those were established in 1955. The department has had a long history of quality research activities. I visited this department first time in December of 2010 to give a colloquium talk when I was an erudite scholar at the Cochin University of Science and Technology. Since then, I have visited the department several times. In 2018, I was an erudite scholar in this department. In the last decade, the department has organized numerous conferences and workshops. This is all due to infinite amount of energy of Professor Satish Kumar and his team. They organized conferences and workshops even during the pandemic years of 2020 and 2021. I do not recall any conference being held, virtual or otherwise, between March 20 to June 2021. This is indeed commendable. These conferences lifted the spirit of the participants during rather depressing times. These conferences bring together renowned researchers from around the world, as has been already emphasized, and create opportunities for students and faculty at the University of Kerala, Trivandrum, and in India at large to learn firsthand about the recent advances in statistics and data science, a new word here. As in the past, this conference having talks in a variety of diverse areas of statistics and data science. The list of speakers includes renowned people from around the world, including India. I look forward to listening to many of these talks and learning about some of the recent advances in statistics and data science. I would like to thank Professor Satish Kumar for having given me an opportunity to participate in several of these conferences and workshops. Now, here's a little bit suggestion. Having workshops and conferences in person, of course, is a bit more rewarding for the participants, professionally and culturally. I'm hopeful that the next TC meeting will be held in person. I personally enjoy visiting historically and culturally rich city of Trivandrum every time. I would like to end by wishing participants a successful conference, and thank you for listening.
Thank you, Professor.
Thank you, sir. Professor N. Balakrishna, Senior Professor in Statistics and Dean of Faculty of Science, CUSAT, is currently the President of ISPS, a well-wisher of our department. He is an expert in time series and has various research collaborations in and outside the country. He is with us today, and I request you, Professor Balakrishna, to say a few words in felicitation of the conference. Welcome you, sir.
Okay. Good morning, everybody. Respected dignitaries online from different parts of the world. First of all, I congratulate Professor Satish for holding this conference. Maybe this is the successfully 7th or 8th edition of this statistics for 21st century. He and his team has been doing it consistently. Of course, recently online, otherwise it was offline. As Professor Kaul wished, we hope by next conference will be physically, hopefully in Trivandrum. So I thank Professor Satish for making ISPS as one of the partners of this conference. Finally, I wish the conference a grand success. Thank you, one and all.
Thank you very much, sir. Now we have our dear Kalyana Raman sir with us today. Sir is actually a father figure to all of us and a well-wisher of the department. Actually, his blessings of great professors like him have given us the energy to pursue such endeavors. Kalyana Raman sir, I request you to say a few words of blessing on the conference, and I welcome you with humbly to say a few words. Welcome you, sir. Can I request Professor Satish Kumar sir to please stop the presentation that is going on? That might.
Professor Kida, would you please stop sharing from that? Not that, sharing.
You can stop. Yeah, thank you, sir. Thank you.
Now it is fine.
Kalyana Raman sir, please. Sir, you are on mute. Kalyana Raman sir, kindly unmute the microphone.
Yes, sorry. Thank you for the good words, Shubha, and good day to all. It's always a pleasant experience to be part of programs associated with the Department of Statistics, University of Kerala. I left the university in the year 2001 on superannuation, and now it is already past 20 and odd years. And still, I am able to associate with all the programs being conducted by the department, and I thank the power that grants me the situation, and I will continue to be doing this until I am allowed to do it. Actually, Dr. Satish and his team is to be appreciated in very big words, but which I am not going to do because you should not praise the student in his presence. So naturally, as a teacher of Dr. Satish, I should not make very big statements about him. So that's why I'm not saying anything about it. And all that I can do is, I can only wish and bless that he continues to do this for many more years to come and not stop with the 8th edition or 9th edition or 10th edition. So it should be set as a, a culture in the department or a tradition of the Department of Statistics, which has a very long history. Dr. Hira Kaul mentioned about the initial stages of the department, but it is beyond that. Actually, in 1931, His Highness Balarama Verma of Travancore assumed his office as King of Travancore State, and he took a sequence of decisions, far-reaching decisions. He decided to establish a Department of Statistics for the purpose of assessing the agricultural yield and agricultural land availability and the income and all associated parameters with the agriculture of the then Travancore state. At that time, Dr. U. Shivaraman Nair, who completed his PhD under Junior Pearson, was available for that purpose, and he asked him to take the leadership of organizing the department and also organize the data collection for the purpose of running the government, which resulted in a Central Research Institute, where Department of Statistics was one of the departments. And also, Dr. U.S. Nair took efforts to establish the collection of data for the governance of Travancore state at that time, which has resulted in the current Directorate of Economics and Statistics, which is one of the big departments of the government of Kerala. And he established this Central Research Institute in the year 1935, which you can see by the stamp in some of the books available in the department library. And later, when the University of Travancore came into being, this department was joined, went to the University of Travancore in the year 1945 or somewhere around that. And again, in the year 1952, when the University of Travancore was renamed as University of Kerala, this became a full-fledged department of the University of Kerala from then onwards. And a lot of people have served here, and they have done their work in those days as it was available for them. And the department has one of the best libraries in the world. Even materials which are not available in current departments, you can find in our department library. So big a library is, and because of his connections, Dr. U.S. Nair procured all possible journals that could be made available for academic discussions. So in that context, the current people the people who are managing the affairs of the department currently, they are doing a wonderful work by organizing this program. Now, organizing this program means not a simple work. See, a lot of people are coming, and these people are going to sit right from morning 9 o'clock to evening 9 o'clock and go on conducting the exercise one by one. And that cannot be just taken as a simple exercise. It's going to be a very big exercise. And I pray and I request all to give their cooperation for the successful completion of this program, and I wish the program a very grand success. And also I request all to participate and cooperate with the regular programs which are going to be happening over the next years. And I can assure you that this is not going to stop here. This is going to continue for many more years. And I also request that Dr. Satish Kumar should not feel otherwise and stop these things either by aging or any other conditions. And we are all there to help you to whatever extent that you want. And you should continue this for many more years to come, so that this will be called as a tradition, just like the two festivals of Padmanabha Swami temple in Trivandrum. This also should come on December. December means Icstc will be there. So that should be the situation that you should create, and that will be a big event that you create for the history of statistics. And I wish you that you do it with all perseverance. So I wish you and all the participants a very happy welcome to the conference, and I wish the conference a big success. Thank you all.
Thank you, dear sir. With your blessings, I'm sure that we'll be able to take this forward for many number of years in the future too. Thank you, sir. And we wish your presence every time with us. We have got our dear Professor Yagin Thomas sir also with us. Sir is a former HOD, former emeritus professor of our department, and actually is the source of energy and inspiration to all of us associated with the Department of Statistics. Dear Yagin sir, I request you to say a few words of blessing to the conference. Welcome you, sir.
Dear Professor Hira Kaul, distinguished statisticians all over the world are linked for delivering special talks in the conference, delegates of the conference, teachers and students of the Department of Statistics, University of Kerala, a warm welcome to all in the name of this department for your participation in this conference. I feel proud of my nomination to offer my felicitations for the successful and grand success of the 8th International Conference on Statistics for 21st century. We all know that many of the outputs generated from empirical researches, such as in agriculture, animal sciences, medical sciences, life sciences, and social sciences, remain as idols, having bones and flesh only. They remain as such worthless until a breath of life is blown on their noses so as to make them valuable and dynamic. The breath of life is nothing but an appropriate statistical methodology. We are linked through this conference from the various parts of the globe to share among ourselves new lifelike methodologies generated from our researches. Thus, the ultimate result of this international conference is that at the end of this conference, we will be empowered to give life to many more idols created by our fellow scientists of their disciplines so as to make their idols dynamic and useful. A perusal on the program of this conference gives idea of wide range of deliberations forming part of the menu of this conference. So I firmly believe that at the end of the conference, all participants will be empowered and gain the much more momentum and orientation in their research in the coming days. I wish you all to have a nice academic engagement all through the sessions of the conference. I wish you all to have a pleasant memory about this conference all through your life. On behalf of the Department of Statistics, I also wish you all to have a joyous Christmas and a blissful New Year 2023. Thank you all once again, and I remain.
Thank you, dear Professor. People like you actually provide us with the energy to go forward. Thank you, sir. Now we are coming to another part of the inaugural session where we will be declaring the various awards installed by the supporters, the well-wishers of the department. First of all, we have the Professor A. Mathai Award, Best Thesis Award, which was instilled by Dr. A. Mathai, who is the Emeritus Professor in the Department of Mathematical Sciences, McGill University, and the Director, CMS. Every year, we get a number of candidates for consideration of the award, and it is a national award which is given to the best thesis based on the theoretical contributions and the practical applications of the research that is taken up by the candidates. This year's jury chairman is Dr. Vincent Matthew, who is the Dean of the Faculty of Sciences in the Central University, Kerala. Professor Vincent is with us today, and I request him to take over the mic and declare the awards for the current year. Professor Vincent.
Very good morning to one and all. Professor Balakrishna, Professor Hira Kaur, Professor Kalyanaraman, Professor Jagin Thomas, Professor Satish Kumar, and all dignitaries present here. I am very happy to be associated with this event. Actually, I was asked to adjudicate and also to consolidate the reports given by various people on the Best Thesis Award in the name of Professor A.M. Mathai. We have finally came to a conclusion that the result is like that. The first prize will go to Dr. Harishankar. The name of Harishankar is placed first. Thank you. With this, I wish all the best.
May I request what places? Please tell the places they are, departments they are from.
Yeah. Some details maybe.
Thank you, sir. Thank you very much.
Yeah. Hello. Hello. Am I audible?
I think Harishankar can introduce himself from where he
Yeah.
is, what is his area and kind of things.
Sir, I completed my PhD under Dr. C. Satish Kumar.
Good. Yeah. Kindly tell
And
the title of this.
my area is discrete distribution.
So please on your camera,
Okay, sir.
so we'll be able to see you. Now, if there are difficulties, yes.
Sir, I completed my PhD under Dr. C. Satish Kumar, and my area is discrete distribution theory on generalized versions of Ewell distribution and its applications. And I take this opportunity to thank all the respected professors who gave this prestigious award. And thank you very much, and a very good morning to all of you.
Thank you.
Thank you.
Yeah.
Thank you, Dr. Vincent. Now it's time to declare the winner of the C.R. Rao and Parvati Rao Gold Medal, which goes to the highest scorer in MSc Statistics for the previous batch. I now request Dr. Satish Kumar sir to please announce the winner for the award this year.
Teacher, with the VS is then.
Yes, sir, I am here.
Yeah, you please, yes, please announce.
C.R. Rao and Bhargavi Rao Gold Medal. This award goes to Srimati Miss Jaisna CJ, first rank among MSc Statistics program. Is Jaisna here? Is here?
Yes, sir, I'm here. Thank you so much, sir.
Okay,
yes,
congratulations, congratulations, Jaisna.
Thank you so much. Sir.
Switch on your camera and see.
Please switch on your camera, Jaisna CJ.
Am I visible, sir?
Yes, visible. You are now visible.
Yeah. Okay, sir.
Okay, thank you, Jaisna.
Thank you, sir.
Thank you. We have got 3 more awards in the name of our dear Professor Kalyanaraman sir, which goes to the highest 3 scorers of PG. Dr. Riaz, can you please declare the names of the 3 awardees also?
Now, Professor Kalyanaraman sir, best first rank among MSc Applied Statistics and Data Analytics students. This year, the gold medal goes to Miss Anagha. Yes. Is Anagha is here?
Yes, sir. Thank you so much, sir.
Okay, please switch on your camera.
Thank you, sir.
Okay, congratulations, Sanaga. Now the silver medal goes to Navanida KJ. Professor Kalyan Raman, silver medal goes to Navanida KJ.
Sir, thank you
Yes,
so much.
Navanida, please switch on your camera.
Thank you so much, sir.
Okay. Then bronze medal. This time this goes to Ardra T. Ardra. I think she is not present in this occasion. Okay, Ardra, congratulations. Okay, thank you, sir. Thank you all.
Thank you, Riaz. And hearty congratulations to Harishankar as well as all the gold medal, silver medal, bronze medal awardees. We are extremely proud of you and we wish you all the best in your future endeavors. We are coming to the end of our inaugural session, but before that, I'd like to say that we have got 6 more awards as part of the conference, the Best Paper Presentation Awards, which is given to young researchers in statistics. Nearly 80 entries are there, 83 entries to be precise are there for that award category, and they'll be presenting their papers over 6 sessions, and 12 out of these 83 will be shortlisted by the end of Sunday, and these 12 candidates will be presenting their papers once again in the final round, which is scheduled for Monday, and from there we will be selecting the final 6 awardees for the 6 Best Paper Awards. I request all your presence in these sessions so that we will be able to identify the best candidates for these awards that are part of the conference, which we give every year. We are coming to the closing session of our inaugural session, and I would like to extend my heartfelt thanks on behalf of the conference as well as the Department of Statistics for all of your presence, because your presence makes our days valuable. Your words of motivation helps us to go forward in every step. We wish your support every day, every time in future also. And I hope that all of us together can have a very intellectual 4 days ahead. I'm sorry. So on behalf of the conference and the department and International Statistical Fraternity, I extend my sincere thanks to all of you for being with us. Thank you once again. We'll be going directly into the technical sessions. Sadish sir, shall we end the inaugural session?
Okay. Now let us move to the,
Thank you all once again. Namaste.
Move to the keynotes. Yeah. Anjana, please introduce prayer and initiate the session.
Sure, sir.
Yeah.
Warm greetings to everyone. We shall begin with the first technical session of the 8th International Conference on Statistics for 21st Century 2022, which is a special session in honor of Professor U.S. Nair, which is to be chaired by Professor G. Arivariknan. Now, Professor Arivariknan is a retired senior professor of statistics from the Madurai Kamaraj University, India, who had been in the teaching profession for about 4 decades. He was the head to the Department of Applied Mathematics and Statistics, Madurai Kamaraj University from 1992 to 2012, and the chairperson of the School of Mathematics MKU from 1991 to 2001, 2002 to 2004, and 2008 to 2010. He was granted the CSIR Emeritus Scientist 2012, which continued for 5 years, and the Emeritus Fellowship by UGC in 2017, which he chose to carry out in the Department of Statistics, Manonmaniam Sundana University, Tamil Nadu, India. Professor Arivariknan is an elected Fellow of the Academy of Sciences, Chennai, and a Fellow of the Royal Statistical Society, UK. He is also a life member of ISPS, IAPQR, International Indian Association for Statistics, Indian Patient Society, Indian Society for Medical Statistics, Kerala Statistical Association, as well as Aura Society of India. He is keenly interested in the domains of stochastic modeling of logistic systems, statistical computing, and spatial statistics, and has published about 100 research papers in various journals. And it is with great pleasure and honor that I welcome you, Professor, to chair this session. So without further ado, over to you, Professor Arivariknan.
Please mute this.
Is audible?
Welcome. Professor.
Thanks to Professor Satish Kumar and other organizers for asking me to participate in the conference and asking me to introduce the speaker. I am very delighted to do it. I am very happy to introduce Professor Balakrishnan to the audience, though Professor doesn't need any introduction. He is one of the prominent statisticians of our time. I met him personally during 2000 and 2001, once at IIT Madras conference and another at Chennai during International Indian Statistical Association conference. Since then I saw, or I should say, listened to him many conferences, mostly online. Professor Balakrishnan received his BSc and MSc from University of Madras in 1976 and 1978. His PhD from IIT Kanpur in 1981. He was an assistant professor for 3 years from 1986, associate professor for 6 years, professor for 20 years from 1985, distinguished university professor from 2015. He was a vice president of International Indian Studies Association for 2 years, July 2001 to June 2003, president of the same association for 1 year from July 2004 to 2005. He was an adjunct professor, National Central University, Taiwan, beginning 2007. He is a distinguished visiting faculty professor in China and Saudi Arabia. He is elected member of the International Statistical Institute in 1982, fellow of American Statistical Association, the IMS, and Turkish Statistical Association. Here he held visiting positions in 15 universities, studied in many countries. I don't want to list all of them, too lengthy. He has guided 51 PhD theses. He is an editor-in-chief for communication statistics in 3 series, theory of methods, and another 2. Associated for 4 journals currently, and in the past for 8 journals, and editor-in-chief for many series of journals from John Wiley and Taylor and Francis, etc. I am very happy to say these things. It's quite lengthy, and if I say all about Professor Balakrishnan, I need another 1 hour, but I know all the participants are eagerly waiting to listen to Professor Balakrishnan's speech. So I give way to him. Sir, please continue your talk.
Thank you. Thank you very much. Let me see whether I can get the screen on. Then I can speak.
Yeah.
Can you see the screen?
No, not.
Yeah, it's coming.
Yeah, it's coming.
Yeah. Okay.
It has come.
First of all, before I start, I also want to thank Satish Kumar and the local organizing committee for inviting me to give this talk. This is actually a nice break because I am marking about 250 exams. So this gives a nice break from the routine of marking. I'm going to talk today about linear prediction. You can consider this talk to be sort of old wine in a new bottle. The topic is old, but what I want to do is share with you some of the recent findings and the interesting generalizations that we can make on linear prediction. So let me first acknowledge the collaboration. The very first work of mine in this was jointly a couple of papers with C.R. Rao. Then when I visited General Electric in Najib Doganaksa, I was a senior scientist. We wrote a paper together, and then the last two are recent collaborations of mine. So this talk, I am taking bits and pieces from different papers, and I want to put a story together and explain how various things are connected. These are the papers, and if anybody is interested, they can find these online, or if you write to me, I will be able to share. So here is a roadmap. Unfortunately, I have listed here many topics. Perhaps it is too ambitious for a 40-minute talk. So I want to, first of all, tell the chair just to give me a warning 5 minutes before the end of the talk so that I can wind down wherever I am in this list. At least I want to get to chapter 7. So if I can go to topic number 7, I will be very happy to stop there. So I'm going to first give a little introduction. I want to motivate the prediction from a life testing point of view. So think of n identical. This is just a restricted scenario. Very soon I will generalize it to generalized linear models. So let us start with the motivation for the problem. Suppose there are n identical units placed on a life test, and we observe the lifetimes of the first R units to fail. Clearly R is less than n. This is a type 2 right-censored sample. So the notation I'm going to use is X for the random lifetime. The first subscript indicates the order, second subscript indicates the sample size n. Then what we are interested in is predicting the lifetime of a future failure that we have not observed. So that means we want to predict X as n for some S that's larger than R but less than or equal to n. So this prediction problem is an old problem. It comes from 1960s. It is referred to as a one-sample prediction problem. Suppose another life test of m identical units is to be conducted. You may then be interested in predicting the lifetime of any failure. Yes, at the failure from the future sample that you are going to test. Then based on what I have observed from the X sample, which is a censored sample, I want to predict what will be the failure time in a future experiment. This is what is called as a two-sample prediction problem. Actually, the two-sample prediction problem is a lot easier because you have independence between the observed data and what you want to predict. So the problem becomes more tricky in the one-sample prediction case. So the earliest noteworthy work on one-sample prediction was carried out by Goldberger in 1962. And what he derived was an optimal, best linear, unbiased predictor. And for that, he used the Gauss-Markov theory framework. So this predictor will be a linear function of the observed order statistics xin. Obviously, you want it to be unbiased for the future failure time xsn, and it should have the smallest mean square predictive error, and that is what is called as best linear unbiased predictor. Since then, significant amount of work has been carried out on both one sample and two sample prediction problems. Several different approaches have been developed: least squares based methods, likelihood based methods, approximate likelihood based methods, Bayesian methods, and so on. In fact, there are 2 or 3 books that exist on prediction problems. One of them is an old book by Icstc and Dunsmore in 1975, and in predictive inference based on Bayesian methods by Seymour Geiser in 1993. Even that is about 30 years old. So I'm going to start first into Goldberger's construction. So Goldberger's construction was utilized in 1975 by Kaminsky and Nelson in a JASA paper. They derived the best linear unbiased predictor of a future failure time, XSN, for a general location scale family of distributions. What that is denoted by xn star on the left-hand side. There is a location scale family. So mu is the location parameter, sigma is the scale parameter. So you get mu star plus sigma star, alpha Sn is the expected value of Sth standardized order statistic. This would have been a point predictor, except what we want to do is introduce a correction which actually accounts for the randomness in the quantity that we want to predict. So mu star and sigma star are the best linear unbiased estimates of mu and sigma based on the observed data. ZINs are the standardized order statistics. Alpha is the mean vector of Z. Sigma is the variance covariance matrix of Z, which is assumed to be a full rank. So I have a sigma inverse. Omega is the covariance between the order statistic that I want to predict and the order statistics that we have observed. So now what I'm going to do is, this is the work that has been exploited by many authors. They have constructed tables of best linear unbiased predictors, evaluated the predictive error, its mean square predictive error, etc. But I'm going to introduce another technique that's called a case deletion method. This is a common method in regression, and I want to connect these two. At first, it will look like they are mutually exclusive topics, but very soon you will see the connection between them. So let us take a generalized linear model of the form y equal to x beta plus epsilon, and I want the errors. Errors need not be independent, but I want them to be centered. So the expected value of epsilon, the error terms, will be a 0 vector. The variance covariance matrix of the error term will be some scalar sigma square times a positive definite matrix sigma. Y is a dependent variable n by 1 vector. X is a n by p matrix of independent variables, so you can call them as a design matrix. Beta is a p by 1 vector of regression coefficients. And what I want to do is, suppose I assume that X is of full column rank and the matrix sigma is non-singular, then for known sigma and unknown little sigma, we know the least squares estimator, what are called as weighted least squares estimator. This is the best linear unbiased estimator of beta, is the usual least squares estimator that is given here. It is a linear unbiased estimator because it's a linear function of x, not in x. X is the design matrix. So y is my random vector. And now what I'm going to do is assume I have a y0, which is an unobserved value of the dependent variable. But I have the corresponding observations of the independent variables denoted by vector x0. So then we have from the equation that I gave before, the linear model, this unobserved value y naught should be equal to the independent variable x naught vector multiplied by the regression coefficient beta plus some error variable epsilon naught. And obviously, according to the previous notation, I need the expected value of epsilon naught to be 0. Variance of epsilon naught will be sigma squared times some nu naught. We need the covariance, etc. So this simply is the quantity that I want to predict. These are the associated covariates that are given to me. Now, then for known sigma y naught and nu naught, I have the best linear unbiased predictor of y naught to be a linear function again of y. So a case deletion method was introduced by Cook in his pioneering work in 1977. The case deletion diagnostics have since been generalized to multiple linear regression, multivariate linear regression, etc. So I'm going to introduce what is a case deletion diagnostics and then try to connect it to the best linear unbiased predictor. It was extended to generalized linear model by Christensen et al. In 1992. So I want to use the formulation of Christensen et al. To motivate my work on prediction. Let us now suppose the future value, the value that I want to predict y naught, let us pretend for now it has been observed. And obviously it comes with the corresponding covariates x naught that have also been observed. Then what is the full data? The full data will be that I will have the vector y that I have already observed before. Now this future value y naught, which I have not observed, I am pretending to have been observed. So my augmented value will be y and y naught. So it will become a n+1 dimensional vector. The best linear unbiased estimator of beta, which I am going to denote by beta naught star, assuming this predictable value y naught to be available, is given by beta naught star plus beta star equal to beta star. This is the original best linear unbiased estimator of beta based on the given data. This is the updated best linear unbiased estimator of beta when a new data becomes available. According to the case deletion diagnostics, this is the updating equation. Beta naught star is beta star plus this quantity. This quantity involves the new matrix X. X is augmented with the covariate X naught. Sigma matrix will be partitioned into a original matrix sigma, the covariance matrix sigma y naught and the variance of y naught, etc. So this is one of the key steps in case deletion diagnostics in linear regression model. So if you look at the book by Cook and Weisberg, this is a fundamental result that is given there. Now, notice in this equation, beta star is completely computable. It is completely computable because it's based on the data. But beta naught star is not computable because it's based on y naught. Y naught has not been observed. So, while beta star is computable as it is based on the given data, beta naught star is not computable as it involves y naught, which is unobserved. Actually, it is what we wish to predict. So, there is no other alternative than to have beta naught star to be equal to beta star, because I have not observed a quantity. So there is no way I can come up with another estimate of beta as an update. So beta naught star should be equal to beta star. That happens when and only when y naught star, the second term, should be 0. Y naught star, the second term, is 0 exactly when the y naught star, the estimate of y naught, is equal to this quantity. But that is exactly the Goldberger's best linear unbiased predictor. So the best linear unbiased predictor that Goldberger derived is nothing but that quantity which is going to make my best linear unbiased estimator with the updated data and the old data to be equal. So this is what the result published in American Statistician by Najib Doganaksai and myself. The theorem says the blue-based estimate of beta remains unchanged if the best linear unbiased predictor-based prediction of future observation is treated as an observed value. So the updated estimate of beta and the old estimate of beta, the regression coefficient, will be the same. And that's an important observation because that connects the case deletion method to the best linear unbiased prediction. Equivalently, we can state that the best linear unbiased predictor of the future observation is precisely that value that makes the best linear unbiased estimators of beta based on the observed data and on the amalgamated data, including the future observation, to be exactly equal. And so I am going to take a simple example to motivate. Nelson and Schmee, in their paper in Technometrics in 1979, gives this example with 10 units and 5 failure times they have observed. Suppose you want to predict, they ask, how long would the experiment have continued if we had gone till the last failure, the 10th failure? Or how long do we have to wait for the next failure to occur, X610? And then they assume various distributions, log normal distribution, etc. They assume, for example, using a normal mu sigma square, they use the tables that have been produced by Joseph Schmee. It turns out that the best linear unbiased predictor of the next failure will be 148.5. Exactly, you have to wait for 10 more hours. Actually, there is in Nelson's book, there is a tables of best linear unbiased estimators for normal distribution are given in appendix. With R equal to 5, you find the best linear unbiased estimator of mu to be 143.4. Similarly, with R equal to 6, with the coefficients coming from the book, you notice the last value is not calculatable because X610 has not been observed. So I can find my best linear unbiased estimator of mu to be this. All I have to do is equate these two. It is one linear equation in one unknown. Voila, you get the best linear unbiased predictor for X6 to be 148.5, which is exactly the best linear unbiased predictor found before. So similarly, you can continue. You can use X6 as this value, use the table to find X7 star, X8 star, X9 star, X10 star. You can set up a sequential procedure to construct best linear unbiased predictors for all the remaining order statistics. And why use estimate of mu? If I use the estimate of sigma, you can prove a theorem which says that they are equivalent. If I use the coefficients of sigma star and construct the predictors, they will also be the same. So theorem 1 reveals that it is an important observation is in Nelson's book, there are about 50 pages of tables given of blues and bloops. What this theorem 1 reveals is that it is sufficient to have one of these tables. If I have the tables of blues for optimal linear prediction, then you don't need tables for best linear unbiased predictors because they can be constructed automatically from the tables of blues. So I'm going to give you an alternate derivation, which is another way of looking at the problem that will give you generalizations. So let us take X and Xs and star to be A transpose X, where A is a coefficient vector that I need to determine suitably. Now, the mean squared predictive error will be nothing but the expected value of what I wish to predict, the predictor, and what I wish to predict square. This can be minimized. Of course, we have to use the Lagrangian method. the Lagrangian method, we need constraints. If I want unbiasedness, then A transpose 1 should be 1. A transpose mean vector should be alpha Sn, so that the expected value of xSn star and the expected value of xSn merge. So this gives rise to unbiasedness conditions. Then you do simple Lagrangian minimization, you obtain the solution exactly as given before, mu star plus sigma star alpha Sn as given earlier. So this is precisely the best linear unbiased predictor given earlier by Goldberger, but you don't have to go through Gauss-Markov theory, etc. and partitioning of matrices. You can do it simply by Lagrangian method, and you introduce unbiasedness conditions and optimize by minimizing the mean squared predictive error, you get the predictor. So now this leads to an immediate generalization. So far I have talked about only predicting one quantity. What if you want to do a simultaneous prediction of two future failure times? Let us think of xSn and xTn, where S is less than T. Of course, this should be R because we have observed R order statistics. So if I take xSn double star to be A transpose X and xTn double star to be B transpose X, A and B are some coefficient vectors that need to be determined suitably, then I need a mean squared predictive error matrix, because now I have two random quantities, two linear estimators, and they are correlated. So I have a mean squared predictive error matrix, which I have denoted by sigma squared W1, W2, W3. W3 is the mean square cross product moment, and W1 and W2 are the mean square error for the two predictors. So you can immediately give what are the expressions for this W1, W2, W3. They will be as functions of the vector of covariances and the covariance matrix sigma. So, and these are immediately calculatable if I know what A and B are, but I have to optimize. Evidently, we can minimize the trace of, so I have the 2 by 2 matrix here. This is the 2 by 2 mean square predictive error. We can minimize any norm we want. For example, I could take the trace or the determinant, etc. So if I take the trace and minimize the trace of the mean square predictive error matrix, it is evidently the marginal linear, best linear unbiased predictors. That makes obvious sense. If I minimize A for minimizing the mean square predictive error, I will go back to the marginal predictor. And the joint best linear, now what happens? If I now, instead of minimizing the trace, which is a marginal criteria, what happens if I minimize the determinant? So the joint best linear unbiased predictors determined by minimizing the determinant of the mean square predictive error are of these forms, where A and B are given by these complex vectors. I have given here the vector A and B, but remember that my objective function is the determinant. So it will be W1, W2 minus W3 square, subject to the 4 unbiasedness condition that you need to minimize this objective function. And you can derive it. And where I can give what are these, V1 is just the 1 transpose sigma inverse 1, V3 is the covariance, etc. All of them are determinable purely from the quadratic forms and the linear estimators I have given. In order to prove this result, the construction of proof is a bit complex. We first require there are 4 unbiasedness conditions. A transpose 1 must be 1, A transpose alpha must be alpha Sn, so A transpose X is a predictor of xSn. B transpose 1 must be 1, B transpose alpha must be alpha Tn, so B transpose X is a predictor of xTn. So we have to use the Lagrangian method with the 4 unbiasedness conditions and the determinant we need to minimize. And so where lambda 1, lambda 2, lambda 1 star, lambda 2 star are the Lagrangian multipliers. Then we have to take this xsn double star, which I gave earlier the formula for A, substitute, and then you take A transpose X, which is your predictor. After some judicious linear algebraic derivations, what you find is that the predictor turns out to be exactly the same as the marginal predictor that we got from Goldberger's theory. So what this says is that the Goldberger's predictor that we got for 1, even if I try to predict 2 correlated future failure times, they are correlated. And if I take them as linear functions and minimize the determinant, I still get the same Goldberger's predictors as the predictor in the joint case. So the joint best linear unbiased predictors are simply the marginal best linear unbiased predictors, and they are indeed equivalent. So whether we use the trace efficiency or the determinant efficiency, the results turn out to be the same as the marginal predictor. So you can instead consider the problem of predicting a linear combination of them. If I take L and K to be some arbitrary fixed constants, I can take Y double star. This is a linear quantity. Y double star will be C transpose X, and the C transpose 1 should be L plus K, C transpose alpha to be L alpha Sn plus K alpha Tn. We can minimize the variance or the mean square predictive error subject to the unbiasedness condition. You simply get the coefficient vector C to be L times the coefficient vector A plus K times the vector B. In other words, the best linear unbiased predictor for the linear combination is exactly the linear combination of the best joint best linear unbiased predictor of the 2 quantities. So this leads to something called complete mean square predictive error matrix dominance property. There was a paper that C.R. Rao and I wrote in 2003 introducing this criteria. Whenever you are trying to estimate or predict various correlated quantities, you can introduce what is called as a CMSPE matrix dominance property in the class of all joint linear unbiased predictors. All that it means is if I take a quadratic form with the mean square predictive error matrix with L and K, this will be less than or equal to any other joint predictor that you can consider. So the same quadratic form for any other joint predictor will be at least as large as this quadratic form, in which case we call it as the complete mean square predictive error matrix dominance property. And the joint best linear unbiased predictors do share this property. So obviously, the complete mean square predictive error matrix dominance property is a very general property satisfied by the joint best linear unbiased predictors. The efficiency I gave earlier, trace efficiency, determinant efficiency, are all particular cases that we can get from this general principle. In fact, this is related to what is called as Loevner order. The complete mean square predictive error matrix dominance property can be put in the framework of Loevner order in order to derive joint linear estimators and joint linear predictors. That is an alternative way. Instead of requiring unbiasedness, start with general linear estimators, require the mean square predictive error matrix should be ordered with respect to the mean square predictive error matrix of any other estimators in the Loevner order. Then what you get is the result that I just gave. This is a result with Rahul Mukherjee established this year. So I'm going to talk about best linear simultaneous prediction if I take L future order statistics, because I only talked about 2, what happens if you take L future order statistics? Of course, I can take S1, S2, SL, they are ordered. They have to be bigger than R because I have observed R failures and the sample size is N. Then you can actually prove that the best linear unbiased simultaneous predictors are necessarily the same as the corresponding marginal predictors. And the proof is quite complex. It's a paper in Journal of Multivariate Analysis and Heavy Linear Algebra. But you can come up with this proof, thus generalizing the previous result. So I say here, the result is proved by starting with some linear combinations, L of them. Then they need to be determined suitably. Then you minimize the determinant of the mean squared predictive error matrix. Now I have a L by L matrix. I cannot write it explicitly and go through the Lagrangian multiplier. So you need a special technique. You write down the diagonal element, write down the off-diagonal element, finally apply some judicious matrix derivatives, then you will come up with a system of L linear equations and L unknowns. And that is what you need to solve. So you can establish that the solution always exists and is unique, and it satisfies the complete mean square predictive error matrix dominance property, and they are the marginal predictors. So that's a very general result. So I'm going to quickly take an example. I gave you earlier the best linear unbiased simultaneous predictors for that example. Actually, they will turn out to be a vector. The only thing is now, earlier I solved one equation with one unknown several times, 5 times. Now I have a system of 5 equations and 5 unknowns. I can simultaneously solve. The solution will turn out to be the same as the marginal best linear unbiased predictors that I gave earlier. Actually, the associated mean square predictive error matrix can be calculated. Because it's a joint prediction, I have minimized the mean square predictive error matrix. All I have to do is substitute for sigma star, and I immediately get also the mean square predictive error. So I can use multivariate delta method to come up with asymptotic confidence intervals for various predictors. That's also possible. So one of the things you can do is ask yourself, can we lose the unbiasedness? Can we derive the best linear invariant estimators without unbiasedness being present? This was first discussed in a paper by Nancy Mann in 1969. Using the results of Mann, Kaminsky et al. In JASA paper, they actually derived the best linear invariant predictor of XSN to be the best linear unbiased predictor of XSN minus a constant times sigma star. This is the biasing factor. If XSN star is unbiased, so if I take the expected value of XSN star, it will be equal to the expected value of XSN. This introduces the bias, but the bias makes the mean square predictive error to be smaller than the best linear unbiased predictor. So an alternate expression for the best linear invariant predictor can be given, and this actually is much easier to derive. You don't have to go through the best linear invariant estimation method. Actually, you can use the Lagrangian method by minimizing. You want to get the minimizing the mean square predictive error. Now you don't have an unbiasedness condition. Without unbiasedness condition, you can derive, and it gives you the same predictor. Now notice one sticky point here. The sticky point is I have the coefficient A vector gamma inverse delta S. Notice the gamma matrix is earlier I had sigma inverse. Now I have gamma inverse in which sigma is present. But there is also a quantity delta. Delta is nothing but mu by sigma. So it involves the unknown parameters mu, and sigma, but it always appears in the form of the ratio mu by sigma. If I know that the population distribution is symmetric around 0, this guy will disappear. Otherwise, you will always get a different predictor. So the quantity delta plays an important role in the relative performance of the best linear invariant predictor against the best linear unbiased predictor, because the measure is going to be based on delta. If this delta is small or delta is large, what happens to the best linear invariant predictor? That's a question. So you can define a relative efficiency measure. I put the mean square predictive error of the best linear invariant predictor divided by the same of the best linear unbiased predictor. This relative efficiency is a continuous function of delta, and we can show that it achieves a unique maximum at some delta star. Unfortunately, there is no explicit solution for the delta star, but we can determine it numerically because it's a unique maximum. It turns out that this relative efficiency is always less than 1, revealing that the best linear invariant predictor always possesses smaller mean square predictive error than the best linear unbiased predictor, no matter what delta is. But how do I use it? Because delta in practice is unknown. So one possibility might be a plug-in method. The plug-in method says that you get the estimate of delta. For example, I have the best linear unbiased estimators mu star and sigma star. I can take delta hat to be mu star by sigma star. When the value of delta hat is away from delta star, the blip will always have a better performance than the blue, meaning will have a smaller mean square predictive error. So I give you an example to motivate this. Here is a data coming from Baumick and Gibbons' paper in Technometrics. They assume logarithmic transformation of the data to be normal. In other words, they assume the log normal distribution for this data. R equal to 9, or the first R order statistics observed. Based on X, the best linear unbiased estimates of mu and sigma are given here. When I plug it in, I get delta hat to be 1.328.
Dear
The
Professor,
relative efficiency for the marginal predictors. Or
dear Professor,
I want to predict the 10th failure, 11th failure, 15th failure. When I take delta to be equal to delta hat, I have given here. These are the delta star value, and these are the predictors. These are the mean square predictive error for the best linear invariant predictor. Unbiased predictor, I have given the relative efficiency. What you observe is that when delta star is high, the relative efficiency is close to 1. So that means the unbiased predictor achieves highest precision. But when delta moves away from delta star, the unbiased predictor loses efficiency, sometimes to the tune of 25%. So unbiasedness, thus you end up paying a price for the unbiasedness. So these values reveal that the best linear invariant predictor is much better than the bloop unbiased predictor when we use delta hat in place of delta. So we can similarly derive the simultaneous predictors of two quantities. Only thing is the mathematics is going to be really messy, because I will now have two coefficient vectors. I will have a 2 by 2 mean square predictive error matrix that we need to minimize, and all of them, notice delta is always present. So this quantity delta, something like a coefficient of variation, plays a key role in the development of best linear invariant estimators and best linear invariant predictors. So,
Professor,
yes.
another 2 minutes, please.
Okay, I will conclude with this, just a numerical calculation. In this case, if I have two types of relative efficiencies, we can define, because now I am predicting simultaneously two order statistics. So I can take the ratio of the determinant of the mean square predictive error matrix or I can take the ratio of the trace. The two efficiency measures are different. Both the D efficiency and T efficiency, you can show that they possess a unique maximum, at which point the best linear unbiased predictors get close to the best linear, not unbiased, but best linear invariant predictor. So here I give you some values. So for example, I have taken different values of delta and I have given the integrated efficiency measures for D efficiency and T efficiency for various values of delta. And you can see that as this delta value becomes larger and larger, the integrated measure turns out to be significantly lower for the biased predictor instead of the unbiased predictor. So the above results show that both the D efficiency and T efficiency are less than 1. So the best linear invariant predictors have overall better joint performance than best linear unbiased predictors in a wide range of delta. If I go from delta equal to -10 to +10, -50 to +50, evaluate at various values of delta and take the integrated measures, that's what you will get. So there are some variations for these results. Unfortunately, I don't have time to go through them. I have given here just the example that I took before. If I do the joint prediction of 10th and 11th, 14th and 15th, I have given the determinant efficiency and the trace efficiency. You can see here that the determinant efficiency can be substantially higher, more than 200% higher when you compare with the unbiased predictor compared to the losing the unbiasedness gives you the benefit. So they are always better in terms of best linear invariant predictor. This result has been generalized in our Journal of Multivariate Analysis paper this year. If I predict L simultaneous order statistics, it is the same result. Whatever I have presented here for order statistics holds in general for general linear model. So there are lots of problems of further interest. We can think about optimal prediction, what kind of censoring schemes would lead to a determination of optimal scheme, and connection. If we don't have Fisher information, we have Tukey's linear sensitivity measure. This can be connected. Some work we have done in this regard that I don't have time to go over. So thank you very much. Here are some references that I have cited, and let me conclude here. Thank you very much for listening. And if you have any questions, I will be happy to answer.
No, sir. I don't think anybody will be questioning you. But however, I would like to ask the audience to come out with some remarks and the reactions and appreciation and so on. And please, at the bottom, you can see the raise hand symbol. Those who want to speak, please click the icon so that we will be knowing that who is willing to talk. Then we will call upon.
Due to the lack of time, I had to go a little faster. So I hope it was still clear. If anybody has any questions, please feel free to ask.
Sir, Kalyan Raman.
Yes, please.
How do I understand unbiased predictor different from unbiased estimator?
That is actually one way to explain. Unbiased estimator means we are estimating a parameter, and the parameter is unfortunately unknown, but it is at a fixed value. So all you have to do is you have to come up with an estimator that's unbiased. That means on an average over repeated sampling, it will be exactly at the parameter, but the amount of variability that it has will be less. But when I go to prediction, what you are estimating is also a random variable. So think of one sampling scheme. If I observe the smallest three, the fourth one that I want to predict is also changing. So that means my prediction is going to estimate that quantity, plus it has to account for the variability in that quantity. In the case of parameter, there is no variability. It's unknown but a fixed value. Here, it is unknown, but that's fluctuating. So I have to not only estimate its center, but also have to account for its variability. So the best linear unbiased predictor, therefore, will have a larger variance or mean square predictive error than an estimator, because it accounts for two variabilities.
Yes, yes, yes. Thank you.
In the absence of any other query or remark from the audience, I would like to thank the speaker for his nice presentation and for enlightening us on some important topics. Now I hand out the session to Professor Satish Kumar. Please, sir.
Thank you.
Thank you, Professor Arivagnan, sir, for chairing the session in a very nice way and a very attractive way. And also, let us give a big clap to our Professor Balakrishnan for your wonderful talk. In fact, several benefited, no doubt about that. And those who can have clarifications needed or any problem, they can contact in the meantime. And after reading those materials, that's better. Anyway, let us move to the next session. Once again, on behalf of the Department of Statistics, University of Kerala, School of Physical and Mathematical Sciences, University of Kerala, and other associates, we extend our gratitude to Professor Balakrishnan, McMaster University, Canada, for your wonderful talk, and Professor Balakrishnan, Professor Arivagnan, for chairing the session and supporting our activities. Thank you so much, Professor. Thank you so much. Now let us move to the next session. Yeah, thank you. Thank you so much. Next session, we have two other eminent speakers. Everyone are waiting for that. Not wasting time. Tajunisa, please introduce the chair and invite the, please assist the chair to do further proceedings.
Okay, sir.
Yeah.
Okay. Warm greetings to all. Now we move on to technical session 2. This session will be chaired by Emeritus Professor K. Kalyan Raman, Sir, of the Department of Statistics, University of Kerala. He has over 4 decades of professional experience in academics, consultancy, as well as research, and is a regular invitee to academic staff colleges in the area of quantitative methods, research methodology, and analytics. He is an expert in statistical computing and has a key role in introduction of statistical computer programming in southern India. He, as a teacher, has been part of our department as well as various major business schools in India. Professor Kalyan Raman, Sir, has published a number of research papers on theoretical and applied statistics in various national and international journals and has been associated with the analysis of more than 1,000 PhD theses in various disciplines. Now he is very keen on enriching himself with machine learning and artificial intelligence. In addition to this, he is also a very proficient in Carnatic music. Professor Kalyan Raman, Sir, has always been an inevitable part of all our events, a strong pillar of support for all our activities, and his blessings and guidance is simply irreplaceable. With great honor and privilege, I humbly invite Professor Kalyan Raman, Sir, to chair the session. Over to you, sir.
Thank you very much for the nice words that you made about me. And it's always a pleasure to be part of the programs in the Department of Statistics, University of Kerala. And I will be chairing a session where two stalwarts are going to present their findings in a paper. And the first one is by Debasis Kundu. And I just say a few words about his achievements. Why I say a few words about his achievement, if I start telling all his achievements, the whole time allotted for the talk will be over. Debasis Kundu, Doctor, he is Rahul Namita Gautam Chair, Professor, Department of Mathematics and Statistics, IIT, Kanpur. He had his B.Stat and M.Stat from ISI, MA Mathematics from Pittsburgh University, and he has a GPA of 3.95 out of 4. And a PhD from Pennsylvania State University. His research interests are statistical signal processing, nonlinear regression, survival analysis, generalized exponential distribution, and statistical computing. From the year 1990 until November, as he stated, he has published 348 papers in national and international journals, and he has been in the editorial board of very important journals, and a very few number of journals. I mean, the very fact that I don't have to say one by one, and few of his papers have been cited more than 100 citations, and overall citations of his publications are coming in terms of 15,791 citations. That is, he has been working with Pittsburgh and Pennsylvania universities also before he joined IIT Kanpur, and he has a number of research workers. He has completed his work, and above all, he is an FRS, Fellow of Royal Society, and I welcome Dr. Debasis Kundu to present his paper on that is let him present his paper on the title that he has chosen, and it's a very long title. And on behalf of the organizers, I welcome Dr. Kundu to present his findings, and it is for 40 minutes, and now it is exactly 10:34, so you can go up to 11:24. Sir, please, sir. I think your mic is muted. Your mic is mute.
Yeah, can you hear me?
Yes.
Okay. Yeah. Thank you for the kind introduction. And it is always difficult to speak after Bala. So I don't know why you have to keep Bala at the beginning. Bala should be kept at the end. Okay. So that should be the usual norm, because in all the places, the best person is always kept on the last one. Okay. So anyway, so we have kept it even at the beginning itself. So okay. So let me try. Okay. Let me just share the file. Okay, can you see? Can you see my file?
It is coming, Professor. It is coming.
Okay.
It is fine. Now it is, you can make it full screen.
Okay, so let me start.
Yeah, Professor.
Yeah. So let me start. Yeah. So the name of my talk is the stationary G process with an application in analyzing gold price data. Okay. So so this is more or less the outline of my talk. First, I'll give the motivations. I mean that from where the problem comes. I'll then talk about briefly about this the generalized exponential distribution, because this G process, which is nothing but the generalized exponential distribution process. Then we'll talk about the G process. What do we mean by it? Some of the basic properties, And then we'll be talking about the maximum likelihood estimation. And finally, I'll just analyze the data, the gold price data, which is the motivation behind it. Okay, can you hear me, all of you?
Yes.
Okay. Okay. Good. Okay. So now let's look at the motivation of this work. So I am interested about this gold price data. Okay. So and I was looking at it, and it is I mean all these data are available actually freely in the internet, and so it is the Indian market gold price data for 45 days starting from October 6th. So they have some actually gap because the weekend they do not publish. So those dates have been removed. So basically we are looking at up to Friday and then again Monday. Okay, so these are the gold price data of what we have for 45 days. So let's look at some of the basic nature of this data set. Just by looking at it, it looks fairly stationary. Okay, and it is observed that again, as the preliminary tests, it shows this one that if you're looking at the first order autocorrelation, which comes out to be positive, whereas the second order comes out to be negative. Okay, not only that, if we just plot the odd sequence of the data and the even sequence of the data, if I take it separately, both of them are positively skewed. I mean, if you're just looking at it separately, both the odd data and the even data, and the most important part is that there is a positive probability of ties. Okay, so which basically means there is a significant proportion of this data set which shows that xn is equal to xn plus 1. Okay, that's what we have. So some of the difficulties what we have seen that the usual AR and the MA process is not going to work. That is there. I mean, which we are trying to fit. It does not work. Of course, there are some other processes which are available in the literature, like this Pareto process, Weibull process, gamma process, logistic process, and which are there in which are available in the literature for quite some time. But two things what I have observed. First of all, we do not have any proper estimation procedure. Of course, I mean, you can go for this the usual maximum likelihood estimator. I mean, we can put the things that we can do it. I mean, without I don't think too much of a problem, but that is there. But of course, it is not being documented about at least I'm not aware of some estimation procedure, efficient estimation procedure. But another thing is that none of these process will take care about the ties. Okay, so that is also another difficulty what we have seen, that they do not take care about the ties which can happen between xn and xn plus 1. So that's the reason that we have to think about something else which will take care about the ties, and for that we are coming up to this the process what we are talking about, the G process, which is the generalized exponential process. So for that, I mean, I'm just give a brief introduction about the generalized exponential distribution, which may not be familiar with many of you, which is a fairly simple distribution in the sense that it has a very, very compact distribution function, which can be written in the form of 1 minus e to the power negative lambda t to the power alpha. It's on the positive real axis. Here alpha is the shape parameter, and lambda turns out to be the scale parameter, and the corresponding probability density function, which can be written in this form, alpha lambda e to the power negative lambda t, 1 minus this one to the power alpha minus 1. The main feature about this generalized exponential distribution is that it behaves very similarly as the Weibull and the gamma distributions. Okay, they have the shape wise. It's a very, very similar to the Weibull and the gamma distribution. Not only that, as you can see that if you put alpha is equal to 1, then it becomes an exponential distribution. So exponential distribution is a special class. So as we can see that all these distribution, like the Weibull distribution, where also the exponential distribution is a special class, gamma distribution is also where the exponential is a special class. So all these distributions are basically the generalizations of the exponential distributions, but in the different directions. Okay, but the nice part about the generalized exponential that it has explicit distribution function. Therefore, it can be used very conveniently in case of the sensor data, and it is closed under maximum. Okay, so these are the some of the things what I had mentioned it here, which I had already mentioned that for alpha is equal to 1, it is an exponential distribution. The shape of the PDF of the hazard function, PDF and the hazard function of the generalized exponential distributions are very similar to the Weibull and the gamma in the sense that it can take basically the hazard function can be increasing, decreasing, or constant, just like the Weibull and the gamma, and the shape is also either a decreasing function, particularly if the shape parameter is less than 1, and it is an unimodal if the shape is greater than 1. Okay, of course, it does not depend on the scale. Okay, the shape of the probability density function. Okay, and it is closed under maximum. And therefore, I mean, we have seen this one that for many data analysis purposes, it can be used quite effectively in place of the gamma and the Weibull distributions. Okay, this is one thing which makes it very easy to generate a generalized exponential distribution, which simply comes from the distribution function. If you just write down the inverse of the distribution function, because if you look at the distribution function, which is 1 minus e to the power lambda t to the power alpha, and if you just equate this one becomes equal to u, so that automatically you will get that x is equal to negative 1 by lambda log of 1 minus e to the power 1 by alpha. So if you generate an uniform between 0 and 1, then x becomes a generalized exponential with parameter alpha and lambda. This particular formula will be useful. We will be using this one in generating the G process, what we'll be talking about. Okay, as we said, that it is closed under maximum. That means that if you're looking at the two generalized exponential distributions which are independently distributed, and if they have the same scale parameter, that means lambda, if they have the same scale parameter, but if they can have a different shape parameter, then the maximum of the two generalized exponential distribution is also a generalized exponential distribution. And this particular property has been exploited to generate basically what we called the bivariate generalized exponential distribution. Okay, because when you go from the univariate to the bivariate, of course there are lots of ways to do it, but suppose we want the marginals also to be a generalized exponential distribution. So one of the natural or simple way what we can do, that suppose I take 3 independent generalized exponential distribution with the same scale parameter lambda, but the different shape parameters, say alpha 1, alpha 2, alpha 3, then I can define my x, which is the maximum of x1 and x3, and y, the maximum of x2 and x3. And you can see that because of the presence of x3, which is there in both, x and y become independently distributed. So x and y becomes a dependent. They're dependent. Okay, because due to the presence of x3, although x1, x2, x3 are independent. So what we did, so that's a way we can define the bivariate generalized exponential distributions, and of course that we'll be using this one. We'll be seeing this one, that how that can be used in going for the G process. Okay, but what we have seen that well, as I mentioned at the beginning itself, that when you're looking at the data, so we are looking at the odd sequences and looking at the even sequences, and we have fitted separately the generalized exponential distribution, because both of them we have seen to be skewed, and we have fitted both with the generalized exponential distribution, and what we have seen that the generalized exponential distribution fits well to both of these. Okay, so that basically gives us the motivation of the following the G process, and that's the reason that we come up to this particular G process, and that's what we have defining it. Okay, so this is the formal definition of the G process, and if you remember, we are using the generations of the generalized exponential distributions that I have explained it before. If you remember, that's the generations of the generalized exponential. That means that you take it uniform between 0 and 1, and then you make this transformation, which will give you the generalized exponential distribution. And that is precisely what has been used in this case. So what we did, we have taken a sequence of independent, identically distributed, uniform random variables, 0, 1, okay? And you take any alpha 0 and alpha 1, which is greater than 0, okay? And in this particular case, we have taken it the scale parameter to be 1, but we can easily introduce the scale parameter, the same scale parameter in both of these. So what we did, we are saying this one that, well, xn, which is the maximum of the negative log of 1 minus un to the power 1 by alpha 0 and negative log of 1 minus n minus 1 to the power 1 by alpha 1. So what we can see that the first one, which is negative log of 1 minus un to the power 1 by alpha 0, which is clearly a generalized exponential distribution with the shape parameter alpha 0 and the scale parameter 1. And of course, I can easily introduce the scale parameter as 1 by lambda at the beginning. And the same thing about the second component, which is negative log of 1 minus un minus 1 to the power 1 by alpha 1. So that is also another generalized exponential distribution with the shape parameter alpha 1 and the scale parameter lambda. As I said, we can introduce the same scale parameter in both of these. Okay. Now, this xn is called the G process. Okay, so that's the way we have defined. That's the way we have defined the G process. That is the maximum of these two generalized exponential random variables. Okay, so now let's see what are the things, what are the justification of the name. Why we are calling this one as a process, and why we are calling this one as the G process, because xn, if xn satisfies equation 1, the way we have defined my xn, then what it can be easily shown that, well, xn is a stationary Markov process. Okay, so that's not a difficult one to show. Not only that, xn follows the generalized exponential distribution for each xn, for each n, xn follows generalized exponential distribution with parameter alpha 0 and plus alpha 1. So that's the reason, that's the justification of the name of the G process, that, well, it's a process which is a Markov process, stationary Markov process, and each of them, each of the marginals following the generalized exponential distribution. This is a simple characterizations which we can obtain for the G process. What it says that, well, suppose my x1 is a generalized exponential distribution with parameter alpha 0 plus alpha 1, and ui's are IID random variable with an absolute continuous distribution function fx on 0, 1. Okay, so ui's are any arbitrary absolute continuous distribution function, absolutely continuous in 0, 1. Then the process as defined in 1, which is nothing but the maximum of the two, because remember that I have defined my x1 and I have saying this one that ui's are independent, identically distributed, which is absolutely continuous between 0 and 1, which is in this form, which has this form. Then the process is a strictly stationary Markov process if and only if ui's are IID uniform 0, 1 random variables. Okay, so this is a simple the characterizations of the generalized G process. Okay, now so let's look at some of the properties of this G process, what we have defined, and naturally the first thing which will come, which is the joint distribution function of xn and xn plus n. Okay, so the way it has been defined, if you see this one, that xn is defined as un and un minus 1. So clearly, if you go beyond 2, that means that you skip 1. So that means that if you're looking at xn and xn plus 1 for any n greater than or equal to 2, so clearly they will turn out to be independent because your ui's are independently distributed, and so definitely it's a lag one process basically. Okay, that's what we have. So the joint distribution of xn and xn plus m. So clearly, both of them are the generalized exponential distribution that independently distributed. So simply that turns out to be as the product. Okay. On the other hand, if you are looking at for m is equal to 1, so that means basically that if you're looking at xn and xn plus 1, so clearly you can easily obtain, I mean, just by the simple definition of the distribution function, that the probability xn is less than or equal to x, xn plus 1 is less than or equal to x, and that we can easily see this one. That the maximum, because that is a maximum of the two, which simply turns out to be 1 minus e to the power minus x alpha 1, 1 minus e to the power minus y alpha naught, and this function g of xy, which is simply nothing but the minimum of these two. It's a simple exercise actually. Just go to the definition of the joint distribution function of x and y. Okay, so that's the way I can get the joint distribution function. Okay, so let's look at some of the other simple properties, because those things will be useful, because that when we'll try to analyze the data, when we have the data, so that these are the properties which basically we should look for, at least we should look for, so that I can fit it if these properties match with the data analysis one. Okay, so as I mentioned, that if you're looking at the dependence property, so clearly xn and xn plus m, they're independently distributed if n is greater than 1. So that we have already seen, because that is very obvious from the definition itself. Now let's look at some of the dependence property of xn and xn plus 1, because we have already seen this one, that if xn and xn plus m for m greater than 1 it is independent. So let's look at some of the dependence property between xn and xn plus 1. And of course, we are looking at the joint distribution function, as I had mentioned. So the joint distribution function for xn and xn plus 1 for 1 minus e to the power minus x to the power alpha naught less than or equal to 1 minus e to the power negative y alpha 1 for x and y, which satisfying these things. The joint distribution of xn and xn plus 1 simply turns out to be 1 minus e to the power minus x, whatever it is written in 4. So clearly, it has two components. The joint distribution function of xn and xn plus 1 has two components, and the two regions are being divided in terms of those two equations, 1 minus e to the power minus x alpha naught less than or equal to 1 minus e to the power minus y alpha 1, and other one is a greater than that. Okay, and of course, when they are equal, then you can see that 4 and 5 they basically match. Okay, so when those two quantities are equal, then this 4 and 5 basically they become equal. So the joint distribution function, of course, it's a continuous function everywhere. Okay, so that turns out to be the joint distribution function, which has two components for those two different sets. So the natural thing is that we can look for several of those dependence properties, and one of the standard one, what we can think about, what we can look at, the positive quadrant dependent, which basically gives you the covariance between xn and xn plus 1, which is greater than 0, and it can be easily verified that xn and xn plus 1 has the total positivity of other typical property. Okay, those things can be just by looking at the distribution function, you can easily obtain this one. But this is another nice one which play an important role actually, and it has becoming a very popular nowadays. What they're talking about, the copula. Okay, so let's look at what is the copula one. I think it's a well-known thing now, but let me just briefly give the definition. We know that for any multivariate distribution where the marginals are absolutely continuous, then I should be able to write down the joint distribution function of this x and y in terms of the copula function, what we call, which is basically a distribution function defined on the closed interval 0, 1 cross 0, 1, and which is in this formula. Okay, where this fx and the fy, these are the marginal distribution functions, And the nice part about this one is that for any bivariate or the multivariate distribution, the corresponding copula is unique. Okay. So that is a very, very important part. I mean, the copula is unique. So as you can see this one, that based on this copula, we can easily generate lots of this distribution. And not only that, another important point about the copula is that the many properties of this bivariate or the multivariate distribution, they are basically only copula dependent, in the sense those properties do not depend on the marginals, and which is basically depends only on the relation, on the corresponding copula, which may not be very, very surprising, because if you're looking at that, particularly when you're looking at the relations between x and y, that may not depend too much on the marginal, but and the associations through the copula, which is more important. And the copula functions, we can easily get it back. The copula functions, which you can get it back from the joint distribution function, you can recover from the joint distribution function by based on this formula, which is fx inverse and the fy inverse. And as we can see, that's the reason that we need this the absolutely continuous, which is a unique property which gives you this one. Okay. As I mentioned already, the copula becomes extremely useful today because particularly you can decompose the multidimensional problem into the univariate problem, and then the copula functions. We can generate several distributions from a given copula. Many properties remain invariant. I mean, as I said, that we can derive many properties, and if it is true for a given copula, any other bivariate, multivariate, or the bivariate or the multivariate distributions will have the same property if they have the same copula. Okay, so that is the reason. That's what I mean, that many properties remain invariant, particularly all those dependent properties and all these things. And another one is that, which is what also very important, that estimation becomes easier. Okay, so in the sense that you will be able to estimate, the parameters in a much more easier manner compared to the maximum likelihood estimator, which might be much more difficult if your dimension is very high. Okay, so that's the reason that it is becoming extremely popular today. Just to take care about that. Now, if you're looking at this G process, we can get the copula, the joint distribution function, this xn and xn plus 1. We have this copula function. Okay, we have this copula. This is the one. The reason actually we are putting it here, because again, these copula things which can be used in deriving many of these association properties. And if you're looking at it, if you use this particular notation, that delta is equal to alpha 0 by alpha 0 plus alpha 1, so you can see that the copula can be written in this form. Okay, and therefore, if you take delta is equal to 1, which basically means that if you take a delta is equal to so this is the copula density also, which is there. Actually, if you take delta is equal to say half, okay, if you take delta is equal to half, then also you'll be getting in a nice format. One particular case actually, okay. And this is the corresponding copula, copula density, what we have actually, okay. So now, if you're looking at the Kendall's tau, again, as I said, that it is a copula property. So we can obtain the Kendall's tau for that particular copula, and which turns out to be this particular one. And therefore, we can see this one, that it has the minimum and the maximum value of the Kendall's tau correlations, which going from 0 to 1 by 3. Similarly, we can have a Spearman's rho also, which also we can get. And again, here also you can get this one, that the minimum and the maximum value is 0 to 3 by 7. Okay, so these are the things, what are the simple properties what we have. Okay, so now let's come to some of the notations, because these notations will be useful for the deriving, particularly the estimations of the unknown parameters. And so we are deriving, we are giving these notations. Basically, what we are these notations are being used to divide the space xy into three different regions. Okay, so one region is S1, where the set of xy. So you can see that it's a curve which is 1 minus e to the power minus x alpha naught equal to 1 minus e to the power minus y alpha 1. So that is a curve on this xy plane. So one region which is above the curve, another region is below the curve, and another region is on the curve, which is my C. Okay, so S1, which is xy, such that which is 1 minus e to the power minus x alpha naught is less than this quantity. My S2, which is 1 minus e to the power minus x alpha naught is greater than that quantity, and my C, which is on the curve. And not only that, this curve C, which has this the parametric representations, which I should be able to write it in the form of this T gamma T. Okay, that's a standard way of writing a curve. Okay, parametric in the parametric form, what you call, and the gamma T, which is in this particular form, which is negative log of 1 minus e to the power minus t alpha 0 by alpha 1. So you can see that I just divided this the space xy into three regions. One is this curve, which is C, which has this parametric form gamma t. I'm putting this one because this one will be using this one when you'll be going for this maximum likelihood estimators. So these things will be useful actually. Okay, so this gamma t, which is the parametric form of the curve C, and then I have S1, which is above the curve, and S2, which is below the curve, and things like that. Okay. So now we can see this one, that we can make a nice decompositions. Is a standard decompositions. What you can make it about this, the joint, the CDF of xn and xn plus 1. So the joint distribution function of xn and xn plus 1 can be written as an absolutely continuous part and a singular part. And so therefore the convex combination P times f of A, which is the absolute continuous part, and 1 minus P times f of S, which is the singular part. And now if you're looking at the singular part, which has this particular form, Fs, which is in this form, and therefore my Fa, which can be obtained by subtraction. So of course the joint distribution of this xn and xn plus 1 has this unique decompositions actually. Okay. And of course, if you are trying to look at the joint PDF, if you're looking at the joint PDF, I mean, which of course has this three different form. One is this F1 when xy belongs to S1. That's the reason that I had made this three region. My F2, which is xy belongs to S2, and on the curve F0, which is y is equal to gamma of x. And where my F1 and F2, which has this particular density function, which you can see that it is nothing but basically the product of the two generalized exponential density function. Okay, so that's the way it is. Okay, so yeah, so this is my my F naught also. So F naught also I'll be able to get it using this. You have to do this line integration actually. That's the way I got it. Okay. So now if you're looking at the special case when your alpha 0 is equal to alpha 1 is equal to alpha, when you have the special case, of course, then it turns out to be in a slightly easier form, because the whole problem comes because that your x the curve C, which need not be a straight line, but if you take your alpha 0 is equal to alpha 1 is equal to alpha, that turns out to be the straight line x is equal to y. So in that case, it turns out to be in a simplified form. So your xn plus 1 has this joint density function for x less than y, for x greater than y, and x is equal to y, where your f1x f1xy, which is in this particular form, my f2xy, which is in this particular form, and your f0x, which simply turns out to be another generalized exponential distribution. And well, in this particular case, that means that if your alpha 0 is equal to alpha 1 is equal to alpha, in this particular case, it turns out to be the bivariate generalized exponential distribution as it has been defined by Kundu and Gupta. Okay, so now if you're looking at the joint PDF of x1, x2, xn, which is simply coming out to be, if you're looking at, I mean, it's a very, very simple way. By conditioning one, you can easily obtain the product of f of xi, xi plus 1, I is equal to 1 to 10 plus 1, divided by the marginals, f of xy, f of xi, I is equal to 2 to up to n. So, okay, and of course, this particular, the joint likelihood function, will be using this one. We'll be using this one in developing the maximum likelihood estimate. Okay, so whenever you will be developing the likelihood inference, definitely this joint likelihood function will be useful. Okay, so yeah, let's look at another interesting property, what we called as the stopping time, and which I think makes sense in this particular case, because I mean it is like this, that when you be trying to sell, I mean, suppose you are a trader, when you are trying to sell or whether you are trying to buy, so these are the stopping time might be helpful in that respect. And so we define the stopping time as the minimum time so that the process exceeds a certain level L. Okay, so as you can see that, well, maybe that might be the time you want to sell. Okay, so so suppose I denotes that n is the stopping time. Say, for example, today I buy some gold and I'm planning to sell it if it exceeds certain level. Okay, so what should be my stopping time or the holding time for me? And so that is the practical implications in this case. So what we are looking at it, n is equal to k, if and only if my x1 is less than or equal to L, my x2 is less than or equal to L, and my xk is greater than L. Okay, so this is the stopping time. So that means basically in terms of this gold price, if you can think of it, is basically the holding time, how long I should hold so that I can obtain minimum L amount of money. Okay, so now in this case, we can easily obtain that if P is equal to, if I define this P is equal to 1 minus e to the power minus L, so you can actually obtain the stopping time. Okay, so I can easily obtain the stopping time, and the expected stopping time also I can easily get it, because the probability generating function I can easily obtain, and therefore I mean I can obtain the expected stopping time, all the things whatever I need, which I should be able to obtain it actually. Okay, so it is useful in the sense that, as I mentioned, that well, suppose I am a trader, I just want to buy some gold and I make some money. So I mean I buy today and then I just wait. How long I should wait? What is my expected holding time? Okay, so that's the way I can interpret the importance of the stopping time.
Sorry to interrupt. Yeah. 5 minutes more.
Okay, sure. Yeah. So yeah, I'll be coming to it. Okay. So this now let's look at this the maximum likelihood estimation, and which is basically that. Now we are introducing the scale parameters. So once you introducing the scale parameter, that the joint density function basically will look like this. And once the joint density function, so I can write down the likelihood function, log likelihood function, which is in this form. Okay, yeah. So this is now if my alpha 0 is not equal to alpha 1, so this is my f1, f2, and g0. That's what I have. So the main the crux of the problem is what we did, so that we had made any parameterizations. Okay, so that is the important part. I mean, that is the main thing actually. I mean, there is nothing, not much is there. So it's a 3-dimensional optimization problem, but we make these reparameterizations, which is gamma is equal to alpha 0 plus alpha 1. The only issue about this point is that because the range, which depends on the parameter. Okay, with the range depends on the parameter. So you can see this one that. So we go for the profiling method. That means that for a fixed gamma, I try to maximize with respect to alpha 0 and alpha 1 and lambda, and then we maximize with respect to gamma. Okay, so that's a standard procedure what we follow. I mean, so for a fixed gamma, I write down the likelihood function with respect to alpha 1 and lambda, maximize this one, and then maximize with respect to gamma. Okay, so yeah, so let's come to the data analysis one. So that's what we did for this one, and so we have this lambda hat and we have this alpha hat, which is this one, and the associated the log likelihood function, which turns out to be this one. And we have also used that when alpha 0 is not equal to alpha 1, these are the results. These are the results what we see, and therefore, if we go for a testing that my alpha 0 is equal to alpha 1 versus alpha 0 not equal to alpha 1, actually we reject the hypothesis. Actually, that's what we have. Okay. Unfortunately, we are not yet able to develop a good goodness of fit. We have done something based on the bootstrapping one. That's what we did. But it is still not. We have done something for the data analysis purposes, but still that's not. It's not. Yeah, we need to do some more work on that one actually. Okay, so that's what it is. And yeah, I think that's what it is. I just close it here. Okay, thank you very much. Thank you for your attention. Yeah.
Thank you very much, Dr. Debasis Kundu, for completing your exercise within time. And this is the time for questions. If there is any question, please ask. We will be pleased to answer them.
Hello.
Yeah.
Yes.
Sir, am I audible, sir?
Yeah.
Myself, Nandini, from Bardiyar University Department of Statistics. I have a doubt, sir.
Yes.
Sir, is there any other measures or model selection methods other than information criteria or goodness of fit test, sir?
What is that? What I was saying?
Is there any other model selection methods other than information criteria measures or goodness of fit tests, sir?
No, we have this. If we go for a Bayesian one, we have this in the Bayesian criteria also, and they call this they call this base factor. Definitely, okay, that is there. Okay, so yeah, I mean, if you can go for a Bayesian inference also, which are there. Okay, yes, and that is also becoming very popular nowadays. This base factor method. Okay.
Okay, sir. Yes, sir.
Sure.
Thank you, sir.
Any other questions?
Can I ask for a inquiry?
Yes, sir. Please.
I saw the property that if I look at data points with a departure of at least 2, then that distribution seems to be only dependent on alpha naught plus alpha 1.
Yes.
And only if we look at the consecutive pair,
yes,
it is a function of alpha naught divided by alpha 1.
Alpha naught divided by alpha 1, and of course lambda.
And lambda is a common parameter.
Sure.
But it looks like alpha naught plus alpha 1 appears whenever we have non-contiguous observations in the time series.
Yes.
And alpha naught by alpha 1 appears only when we take contiguous observations. So
Sure.
I wonder whether we could reparameterize it as alpha and beta and just take the sort of like orthogonal observations, orthogonal parameterization to make the estimation of
easier
beta only based on contiguous pair and alpha based on non-contiguous observations.
Oh, okay. I see.
I saw the likelihood that you gave, the distributions you gave. The contiguous pair always has alpha naught by alpha 1.
Yes, of course, definitely. Absolutely.
The non-contiguous pair always has alpha naught plus alpha 1 together.
Yes.
So that says once you go away from non-contiguous pair, you cannot the alpha naught and alpha 1 are not simultaneously estimable. Only the sum can be estimated.
That is
from
true.
Non-contiguous pair.
Absolutely. That is true. No, but the problem, I think, Bala, is that I don't know whether I'm making sense. See, but if you try to disassociate the two, but still the variables will be dependent, isn't it?
That's correct.
Yes, exactly. So that I have to see this one, that okay. I mean, what you are saying, this one, that if you are looking at the contiguous from the I think, but still you can get the estimates. Now you can see. I think you can get the estimate, but they may not be the maximum likelihood estimators.
Correct.
Yes, definitely. I think that is possible. Yes. That is definitely possible. Yes. I mean, that's the way actually we can get some idea about the initial guesses also.
Initial values. So even the starting, instead of doing the profiling, you can start with a very good initial values.
Yes. No, profiling actually, Bala, the reason actually we have gone for the profiling one, it is one of the reasons is that because if you're looking at the range depends on gamma. So that's the reason this one that we have gone for the profiling. So fixed gamma, so that your range becomes now independent of the parameter for a fixed gamma, and then you maximize with respect to alpha 1 and lambda, and then you maximize with respect to gamma. So that's the reason actually. Yes. But what you said, this one, that will be definitely useful for the initial guess, no doubt.
Starting initial iterative process.
Yes. Even in terms of gamma also, because if I get some initial guess, that will be always good. That will be always good for my gamma also. Yes, absolutely.
Correct.
Absolutely. Yeah, good. Yeah, thank you. Yeah.
Thank you, sir.
Sure.
And if there are any question, please, we can communicate to Dr. Kundu using his address and emails are available in the website. So we give our appreciation for the excellent presentation here. Thank you very much, sir. Please continue to be associating with us in years to come. Thank you, sir.
Thank you.
And now we go on to the next lecture, again by Harvard. And I don't know whether I have the qualification to chair sessions of these people, but still, my age is allowing me to do that, perhaps. So I invite Dr. David D. Hanegal, who is again an FRS and a professor and head of Department of Statistics, Vishwakarma University, Pune. And he had his BSc and MSc from Karnataka University. The very word Karnataka University brings me nostalgic feelings with Bhatt sir, that is Professor Bhatt in those days. He had his MPhil and PhD from Pune University. Now it is rechristened as Savitri Phule University. And he served in Pune University earlier. He had about 100 research papers to his credit, with 750 citations, published 2 books. He is in the editorial board of very important journals, and also he has experience in various organizing and associated with various scientific societies. And he is going to present a paper on correlated compound Poisson frailty process and using some techniques, reverse hazard rate. And I now invite Dr. David D. Hanegal, and your time will be for about 40 minutes, sir. Now it will go up to 12. So please present your paper on correlated compound Poisson fatality models based on reversed hazard rate.
Thank you for the very nice introduction. I also thank Professor Satish Kumar and his team for giving an opportunity to share my views and ideas to the audience in the conference. The title of my talk is, can you hear me?
Yes, Professor, we can hear you.
You can see my slides also?
Yeah, slides are fine.
Okay, thank you. Title of my talk is Correlated Compound Poisson Fatality Models Based on Reverse Hazard Rate. I just introduce what is survival data. It's time to event data. The data consists of some sensor data. It may be either right censored, left censored, or internal censored, or different types of censoring. Mainly, I'm dealing with right censored, random sensor data. And I start with the Cox model. Okay, the basic Cox model given by Cox 1972. Okay, that is HT given X. H0 T is a baseline hazard function. X is a vector of explanatory variables. Beta is a vector of corresponding regression coefficients. Okay, this is a basic model given by Cox, proportional hazard model, and based on the regressions. And what we see here is there is if the data is homogeneous, then you can use this model. If there is a heterogeneity inwards because of some genetical factors inward or patient's effect or some center of the hospitals, different center to center, the risk will change from family to another family. The risk of disease or whatever, that will change from one family to another family or one center to another center. It may depend upon the environmental factor also. There are several things involved. These are called heterogeneity, and we call this as a variety actually. In that case, we just extend this Cox model to adding some unobserved explanatory data. Okay. Sometimes what happens if there are too many covariates involved and we don't know whether they are important or not, how far they act on the lifetime of the distribution. In that case, we will not include some of the covariates. See, this is what happens if we neglect some covariates in the model. Sometimes maybe too many covariates considered, we don't know which one is important, which is more significant factor. Sometimes we don't have appropriate tools to measure, okay, the covariates. Researchers are not aware of influence of the potential covariates that might exist. For example, genetic risk factor or environmental factors. Not all necessary covariates are included in the model, which modify the distribution of survival time and model parameters biased. That makes the assumption of homogeneity unrealistic. That's why we introduce some heterogeneity or variety in the model. Okay, what is this heterogeneity factor? See, this is a Cox model. I just introduced some observed covariates U. That is, U is unobserved covariate, beta star is a regression parameter corresponding to this U prime. And I can write this e raised to U prime beta star as Z, that is greater than, that is a random factor that is greater than or equal to 0. Okay, U prime may be minus infinity plus infinity, and this is a Z. This is a heterogeneity factor that is called variety variable here. Now, one can relate this hazard function to survival function, okay, using this formula. Here H0 T is an integrated hazard, and you can integrate out Z you get unconditional survival function. That is ST equal to this one. This can be expressed in terms of Laplace transform of H naught T x prime beta prime. This is a univariate. One can extend it to bivariate. The argument will be in terms of H naught T1, H naught T2, e raised to x prime beta. And this is a common covariate for both T1 and T2. Okay, that is the explanatory variable. And here T1, T2 are dependent in this case. Okay, given if priority is given, then T1, T2 are independent. We are in the previous one. Okay. When it is unconditional survival function of T1, T2, in that case, T1, T2 are independent. After integrating over Z, this T1, T2 will become dependent. That is the case. And this is called share priority model. Now, what is the reverse hazard rate? You know usual hazard rate and this reverse. This was given by Barlow in 1963, Shaket, Shantikumar 94, Block 98. The definition of reverse hazard is this one. This is Ft upon the density divided by distribution function. Okay. This is the instantaneous rate of death or failure at a time given that it failed before time t. Okay. And mt delta t is the approximate probability of failure integrated given the failure before the end of the interval t minus delta naught and t in this interval. Okay. This reverse hazard rate is usually used for the left sensor data or right truncated data. Okay, that is mainly used for this one. And for right sensoring data, we use the usual hazard function that is well known in the literature. Okay, I just denote this as Z, the priority variable here, and M0 is a reverse hazard rate, and that can be written in this form. This is a baseline reverse hazard rate, and these are the X0 and X1. These are the covariates corresponding to common covariate and covariate based on T1, T2. Okay, I equal to 1 into. This is the bivariate. We can extend it to multivariate case also. And the cumulative reverse hazard rate is given by this one. And I'm just giving the notation eta naught, that is e raised to x naught beta naught, and eta ij is this one. This is a covariate corresponding to T1, T2, okay, separately. And this is a common one, covariate. I'm just identifying the two different covariates. And you can express in terms of reverse hazard rate in terms of the distribution function. That is the formula. As we see in the survival function can be expressed in terms of cumulative hazard function. And the same way you can do the distribution function can be expressed in terms of cumulative reverse hazard function. It can be done for the bivariate case also. Here in the bivariate given Zj and Xj, these two, T1, T2 are independent given Zj. Okay, you can separate it out. And when you integrate over Zj, then this T1, T2 will be dependent in this case. That is equation number 7. Okay. Okay, the first time the priority was used by Clayton, he just used unobserved random covariates. Later, Weipel and et al. In 1979, they gave the notion of priority in that case. First, it was started in 79 and 78 and 79. Okay. This was using the usual hazard function. Later on, it was used in the reverse hazard rate also. Okay. All right. Okay, what happens when you ignore the priority? Okay. If priority is significant in the model and is ignored, then the model will be inappropriate and the decision based on such model will be misleading. If priority is ignored, the estimate of the regression coefficients will underestimate or overestimate. And the model selection criteria, say AIC, BIC, DIC, that is a AKK information criteria, Bayesian information criteria, and deviance information criteria. That will increase if we ignore the priority, okay, in that case. The decision based on the model without priority will go wrong. You can do the analysis, but whatever decision you do based on this data, that will be misleading and wrong in that case. Ignoring priority effect with finite mean may result in negative bias and in the estimated time dependence. In general terms, we let heterogeneity go into error term, and this will lead into increase in the variability of the response as compared to the case when priority is included. There are different priority models already introduced in the literature. Gamma priority, inverse Gaussian priority, positive stable, power variance function, compound Poisson priority, compound negative priority, piecewise gamma priority, correlated priority, additive priority. Share priority and correlative additive priority, that will come in the next slides. Okay, I discussed about the share priority model that shares the common risk between the T1 and T2, or maybe if they're multivariate, more than 2 variables also. That is a common risk. Okay. Now, what is compound Poisson distribution? This was given by Allen in 1988 and 92. They introduced compound Poisson distribution as a mixing distribution, okay, in the survival model, which is extension to one studied by Hubbard in 1986. Okay. It's a unimodal distribution. There are examples of this compound Poisson. Death rates for cancer patients, meaning that the longer the patient lives beyond a certain time, the more improved are her chances. The divorce rates, the maximal rate of divorce, which occurs after a few years, which means most marriages are going through crisis, then improving. The population density start to decline simply because high-risk individuals have already died or been divorced in the marriage data. So henceforth, these are the things. There is one more additional feature, okay, that is a zero susceptibility in the compound Poisson priority model. The distribution is defective here. In practical terms, it means some individuals have zero susceptibility. They will survive forever, or some patients survive their cancer. Some people never marry. Some marriages are not prone to be dissolved and so on. This is in the cancer data, marriage data, and other things. In medicine, several examples of disease primarily attacking people with particular susceptibility. For instance, a genetic kind, other people having virtually zero susceptibility of getting disease. Another example is fertility. Some couples are unable to conceive children, so that the distribution times having first child birth for population of couples will be defective. These are the examples of susceptibility, zero susceptibility in the compound Poisson. You can also see the unemployment data, one can also face with fact that some people may be completely unable to get a job. In such type data, compound distribution have positive mass at zero value can be a suitable choice. Okay. And it has a closed form expression for the Laplace transform, and one can have distribution. Okay. This distribution is not only mathematically convenient, but might also be seen as natural in more substantial sense. The distribution arises as sum of the random numbers of independent gamma variables where the number of terms in the sum is Poisson distributed. This might be viewed as a kind of shock model where vulnerability of subject has been shaped by a random number of shocks, each of random size. Okay, this is the definition. Okay, X size are gamma distributed and N is a Poisson, and this is some random sum of the sum of the random variables. Okay, that is the distribution. N is Poisson distributed with mean mu. X size are independent, identically distributed. Random is with scale parameter mu and shape parameter gamma. Just Z is consists of two parts. Discrete part corresponds to probability of 0, susceptibility, and continuous part is a positive real line. Okay, the discrete part is for Z equal to 0, when N equal to 0, in that case it is e raised to minus mu. It decreases as mu increases. Okay, the continuous part is given by this one. Okay, given N. Okay, this is gamma random variable given N. Conditional on N. Okay, the Poisson random variable, that is with probability mass function with the parameter mu, is given by this. Now the density of Z is written by this one. Okay, and okay, the density of the Z is given by this one, that is here. Okay, this is a parameter set. There are 3 parameters involved now in the compound Poisson distribution. Okay. Now, what is a Laplace transform? The Laplace transform is given by this one. All right. This is Laplace transform of gamma. Okay, and Laplace transform of Poisson. I'm writing it separately. I'll join these two later. Okay. Okay, now Laplace transform of Z, compound Poisson, that is combination of both Laplace, N and Xi. The final form is here. Okay, and it can be written in this form. Okay, now it has in all 1, 2. Okay, this is the thing. All right. This is a Laplace transform. We can have mean and variance for this. The moments, okay. One can obtain the mean and variance by taking the differentiation, first derivative and second derivative. You will get second and first moment. Then variance you can obtain after this. The mean here is mu gamma upon mu. And variance is this one, okay, of Z. Now there is a problem of identifiability in the model. Okay, for that, to resolve the non-identifiability in the model, we need some restriction in this case, and that restriction is we have to modify the expected value of Z equal to 1. That is mean should be equal to 1. Under this restriction, this will be the mean z equal to 1. This leads to mu equal to mu gamma. You know the mean, okay, mu gamma equal to mu. That is this one. That is a restriction. Under this restriction, variance of z will be this one. It has now only 2 parameters. Earlier it was 3 parameters. Now it is reduced to 2 parameter compound Poisson distribution. Okay, now after the restriction, the Laplace transform is given by this one. That is here. Okay. All right. Now, so far we have seen only the share priority model. Now, what is correlated priority model? See, in the bivariate case, 2 components in a system. It may be either a pair of kidneys or lungs or any paired organs in a one body. Okay, you can have lifetime T1, T2, and there is a correlation between the two. It may be related with bivariate, what you call, priority. So far, we have taken only common risk, Z. Now I'm taking separate risk for T1, T2. That is, for T1, separate risk, and T2. T1, that is Z1 is a risk, and for T2, Z2 is the risk. Okay, and these Z1, Z2 are correlated. Okay, that is the thing. This happens mostly when there is a, see, for T1, T2, even though it is a maybe it may be twins. Okay, the environmental factor may be different. Even though they have a common genetic factor, there are some genes, they are different. See, the behavior of one twin and second twin may be different. They have some common genes, but some genes are different. That's why there is separate risk factor is there for T1, T2. That is the reason. That's why we took Z1, Z2 as a 2 different risk factors. They are correlated. And this is Z1, Z2. That is given by this one. Given Z1, Z2, this F1 and F2 are independent. Okay. And okay, here, okay. And Z1, Z2 are correlated varieties. Okay. The distribution of this random vector is need to be specified. You can have different distributions, bivariate distributions. Okay. There are already some different bivariate distributions for Z1, Z2 in the literature. That is correlated variety, gamma correlated variety, inverse Gaussian, bivariate inverse Gaussian for correlated variety, and several correlated varieties are already discussed in the literature. And one can have the bivariate distribution function after integrating over Z1, Z2. That is given by this one. Okay. Here T1, T2 are dependent because we have integrated over Z1, Z2. Okay, that is the thing. Now this is bivariate variety distribution. Now what is correlated compound variety distribution? Okay, there is a relation. There is you can have Laplace transform, bivariate Laplace transform, given the if you know the univariate Laplace transform of the distribution. The relation is given by 15. Okay, L S1 S2, that is LZ, S1 plus S2, and this is LZ for S1 and this is LZ for S2. That is the relation. Okay, and rho is the correlation between Z1, Z2. That is the thing. And this is a bivariate form of the Laplace transform. You can have, if you know the univariate Laplace transform, you can very easily obtain this bivariate Laplace transform. Once you have bivariate Laplace transform, then you can have bivariate survival function based on this. When rho equal to 1, it will lead to share priority model. When rho equal to 0, it will be then Z1, Z2 are independent. That is okay. It can be extended to multivariate case like this. Okay, multivariate Laplace transform. When rho equal to 0, then Z1, Z2 are mutually independent. And rho equal to 1, it leads to share Faraday model in the multivariate case. And this is a Laplace transform of Poisson, compound Poisson distribution with period gamma. That is it. Okay, now we take the bivariate case. Okay, that is a bivariate Laplace transform. And you can write the Laplace transform in terms of cumulative reverse hazard and other parameters involved. Okay, let's substitute here the distribution of Z, and this is for Z S1 and S2, that is this one, cumulative reverse hazard, and this univariate reverse hazard, correlation of Z1, Z2. Okay. Now we can write the, I'm sorry, this one should be the F by misprint. This should be a distribution function of T1, T2. Okay, that is here, the same equation. In terms of the covariates, eta. Okay, in terms of covariates. Earlier one was without covariates. You can add some covariates, you can write the distribution function. Okay, this is when Z in the presence of covariates, and this is when the Faraday variable is degenerate. When in the case of degenerate, when there is no Faraday, then T1, T2 are independent, and this is without Faraday model. Okay, in this case. Now I am going completely parametric approach. One can also have semi-parametric, taking baseline distribution as non-parametric distributions. I have taken 3 different baseline distributions. One is modified inverse Weibull, okay, with the distribution function, reverse hazard rate, and cumulative reverse hazard rate. Okay, this is the first baseline distribution. Okay, this was given by Devendra in 2011. The second one is a generalized log logistic distribution. I can have 2 types, type 1 and type 2. I'm just generalizing the log logistic distribution. Okay, in this case, you can generalize it with a distribution function as well as survival function. Okay, the distribution function raised to alpha, you can generalize, just like generalized exponential distribution. You can generalize taking the distribution function raised to alpha. One can also have survival function raised to alpha also. In that way, there are 2 types I can have, type 1 and type 2. This is the first one, and with the reverse, cumulative reverse hazard rate, cumulative reverse hazard rate. Okay. This is the type 2. The another one. Okay. When alpha equal to 1, this reduces to log logistic distribution. Okay. All right. Now I am proposing total 6 models, 3 Faraday models. 3 models are with correlated compound Faraday, correlated compound Poisson Faraday model, and 3 are baseline models with without Faraday, without correlated Faraday model. Okay. In all, there are 6 models. This one is modified inverse Weibull baseline, and with Faraday and without Faraday, with correlated Faraday, without correlated Faraday. And these 2 equations, okay, the distribution equation, the 31 and 32. This is a with correlated Faraday and without correlated Faraday. The baseline is generalized log logistic type 1, okay, with compound correlated compound Poisson variety. This is without one. And this is a baseline is generalized log logistic type 2. Okay, with and without correlated variety models. There are 6 models. I'm having a comparison of all these 6 models using the Bayesian technique. Okay, one can also have the usual classical methods, maximal likelihood estimators. But there are a lot of parameters involved. There is a problem with iterative procedures in the Newton-Raphson procedure and the conversions of the parameters and other things. That's why I'm going directly to Bayesian estimation of the parameters. Okay, you can have bivariate sensor with 4 different reasons when T1, T2 are observed. Okay, that means they are failed, and only T1 is observed and T2 is censored, and here T1 is censored, T2 is failed one, and both are censored for different reasons. You can have different. Okay, N1 corresponds to the first reason, number of items correspond to second, third, and fourth reason. And sum of N1 plus N2 plus N3 is N. Okay, for all these 4 reasons, likelihood function. One can have F1, F2, F3, just to take the second derivative with respect to T1, T2, and this with respect to T1, and this with respect to T2, and this is a just like distribution function. Okay, these are the 4 reasons. You can just replace it in the likelihood function, you will get the likelihood function. Then you can take, then I just go directly to simulation study. For sigma, I'm just taking the gamma distribution, the prior for the parameter sigma, and similar type of prior distribution were used by Ibrahim, Sao, Santosh, and Ajkar. And since we don't have any prior information on the baseline distribution, this one, okay, lambda 1, gamma 1, alpha, and other things, and we assume the prior distribution to be flat. We consider 2 non-prior informative priors. One is gamma and another is uniform, and we do the simulation procedures. It is presented in table 1 and 3 for 3 correlated variety distributions. I'll explain in the, okay. Okay, this is for the simulation table for the first model. That is a correlated compound variety model, and its simulation is with baseline, that is a log logistics type 1, and correlated compound variety. This is for the third one, the baseline, generalized logic type 2 with correlated compound Poisson variety model. Okay.
Sorry for interrupting. 5 minutes more. 5 minutes more.
Okay, all right. I'm going to finish it. Okay. These what we can see here is the estimates are close to true values in all these cases. Okay, and lower and upper credible limits, KVK values, P values, Gelman-Rubin's statistics is given, and this is just to check the performance of the Bayesian estimates. Now I'll go directly the data analysis as the Australian twin data that is given in Duffy and et al. Okay, and there are 2 T1, T2. Okay, that is a one covariate is there, that is for T1, T2, common covariate and presence and absence of appendicity. Okay, and this is for twin 1 and twin 2. Okay, T1, T2. Okay, 350 pairs of T1 twins. That is correct. I am just doing the fitting. Okay, case statistics and the p-values. P-values are high. That means whatever model we have chosen, that fits well with the correlated compound Poisson variety models. And I'm just doing the posterior summary for the Australian data. The estimates of different parameters, standard error, lower and upper critical limit, and p-values in this one. What we see here is beta naught, the A's. The A's that is correspond to A's, that is a significant, the model 1. Here also the A's is significant factor. Okay. In the model 3, here most of the time it's like that only. Here also beta 1, appendicity, presence and absence of appendicity, that is significant, and is also. Okay, here age is a significant factor. Here you can see beta naught and beta 1, presence and absence of heterogeneity, and age of the patient, age of the twins, you can say. The last model, that is this one. Okay, in most of the models we see the age factor is the one which is significant factor. Now I'm just comparing all these models with the previous models. Okay, these 6 models are the just now I discussed, the AIC, BIC, DIC models. What we see here is compound Poisson variety, correlated compound Poisson variety with model 5, that is generalized law logistic type 2. Here AIC, BIC are least, okay, as compared to all other models in the existing. And in the existing models also, they are higher than this model 5. That means model 5 is better than the whatever models are presented here in this paper, and also the previous existing models. That means this is a better one as compared to other models. And one can also see from the base factor also, the model 5 is better. That is doing better with other models. Here also, model 5 is better than other models. Okay, that is there. One can have graphical fit also for the survival function plots and KM survival, parametric and normal. They are very close here. You can fit very well these models to this data also. Conclusions. I think I already explained all this, so I'm just briefing. Priority variable is here, that is high. That means there is a significance. It's a priority factor is significant, that you can say. It's a sigma square is high, and there is a correlation is 0.7 in the model 1, 0.7 here, 0.67, 0.6. They are very high, then there is a high correlation between Z1 and Z2. That is, one can have correlated variety models, correlated compound Poisson variety model. And okay. The only thing is ACE is a significant covariate for model 1, 2, 3, and other things. That is, other factors are not that significant. That is the thing. Okay. One can also conclude from the base factor, the model 5 is better than all other models. Okay, that is the one Bayesian test for the testing sigma square, the base test. Okay, and model 5 is better as compared to all this. That is the thing. Thank you very much for giving your time and patience hearing, and I thank the organizers for giving an opportunity to share my views and ideas during this conference, especially to the chairman and of the session and Professor Satish Kumar. And thank you one and all.
Thank you very much, Professor Hanagal, for completing well within the time. And this is time for 1 or 2 questions maximum, because time is already 12. So you may take 1 question if at all there is. Any question?
Can I ask a question?
Yeah, correct. Okay.
In the case of modeling frailty through the proportional hazards model,
yeah,
the hazard function can be fairly flexible. It can be increasing, it can be decreasing, it can be non-monotone.
Yeah, correct.
But in the case of a reverse hazard function,
Yeah.
you cannot have an increasing reverse hazard function for a lifetime.
Most of the time it is a decreasing.
Yes.
Most of the time.
So is that a constraint? Does that put a restriction?
Maybe there are some very rare reverse hazard rates. They are maybe slightly increasing and then decreasing, but they are very rare in the literature. Most of the reverse hazard rates are decreasing type.
Right. Well, the complication is that Bloch's result says that if you have a positive lifetime random variable, the reverse hazard rate function cannot have increasing behavior.
Yeah, correct.
If it is increasing, then the random variable is necessarily in the interval minus infinity to a. It cannot be from 0 to infinity.
Yeah, correct. That is true.
That puts a constraint modeling through reverse hazard function.
Whatever I have seen so far in the literature, in my paper and some other paper also, they are a decreasing type.
Right.
Reverse hazard rates.
Right.
Okay.
Thank you.
Thank you. And there is one more person who has raised his hand. Munib Wani. Mr. Munib Wani, can you ask your question? Yes.
That has raised the AIC's back to the model.
Hello. Yeah, tell me. Your voice is breaking, I think, somewhere.
Yes. Mr. Munib Wani, can you ask the question?
Voice is breaking. There is some problem with audio.
Okay, it's already time. So you just communicate with Professor Hanagal using the email that is being provided by the website. Okay, we conclude the session and be on time for the next session. And I thank Professor Hanagal for presenting very good topic. And those who would like to consult him, please contact him over the email. And so we come to a conclusion of the 2 papers, and I thank both speakers for a nice presentation, and also I thank Satish and his team for providing me this opportunity to share the sessions of 2 very big stalwarts in the field of statistics. And let us continue with the program. Over to Dr. Satish Kumar. Thank you.
Thank you, Professor Kalyan sir, for chairing this session. Thank you, sir, for chairing this session in a very excellent way. And also, we wish to extend our gratitude to the speakers of this session for their excellent presentations, for both Professor Kuntu and Professor David Hanagal for their presentations. Now let us move to the next session. Professor Hilal Kaul is here to speak, and to chair the session, Professor David Henagel is here. Abhirami, please introduce the chair and support him for the further procedures. Please. Abhirami?
A warm greeting to each and everyone present here. Thank you in advance for joining at the 8th International Conference on Statistics for 21st Century 2022, Technical Section 3 in honor of Professor A.M. Mathai. And today, it's an honor for us to introduce Professor David D. Henagel to a very informative, interactive session ahead of us. Professor David Henagel was an emeritus professor from SP Pune University with 40 years of teaching and research experience worldwide. He has published 2 books, Introduction to Applied Statistics, Non-Calculus Based Approach, and Modeling Survival Data Using Frailty Models, addition to which he has also published 3 book chapters. Professor David has contributed to the world of statistics by being the editor, editor-in-chief, and editorial board member of many prestigious and renowned journal publications, including Indiastat, American Journal of Biostatistics, Advances in Reliability, and much more to add to the list. He has also spent his share of experience in the esteemed position as Vice President of Indian Society for Probability and Statistics. In addition to a much discussed and well appreciated 137 research papers published over international journals, and a presentation of more than 100 talks, both national and in international conferences. Professor David took his time and guided 9 PhD students and worked as visiting professor in many universities, with Michigan State University being one. He is also regarded as a valuable member of many nationwide organizations and considered as the subject expert for selection committee of competitor fellowships. Due to his rich academic and research-oriented experience, he had been presented with positions of great height in our country. Positions like Executive Council Member, Treasurer, and Governing Council Member of Indian Statistical Association. His recent researches include frailty regression model for univariate and bivariate survival data, censoring scheme, Monte Carlo method, MCMC algorithm, and many more to add, and of course, much more to come. Words really do fall short to describe you, sir, but we are fortunate enough to have a session from you. On behalf of everyone present here, I cordially welcome you. Thank you.
Okay.
Please carry on.
Okay, I have privileged to introduce Professor Kaul from Michigan State University, USA. And I just give a brief introduction, whatever I have now in the, okay. Professor Kaul did MA in Statistics at Pune University in 1964, PhD from University of California, Berkeley in 1967. He published 142 research publications, guided 34 PhD students, and his research interests are inference in stochastic processes, long-range dependence, and time series analysis, non- and semi-parametric inference, efficient adaptive estimation, reliability theory, survival analysis, weak conversions of stochastic process, and their application to statistics. He has written several monographs, weighted empirical and linear models in 1992 IMS lecture notes. Proceedings of the workshop on analysis of sensor data in 1996 IMS lecture notes, monograph series. Special issue of statistics and probability letters in memory of V. Susurla in 1919. Weighted empirical processes in dynamic non-linear models, second edition. Frontiers in Statistics, Imperial College Press, London. Large sample inference for long memory processes, Imperial College Press. Awards, he has several awards and honors. I'm just listing a few of them. Humboldt Senior Research Award in 1995. He's a fellow of IMS and ASA, elected member ISI, president IISA in 2005 to 6, president Indian Statistical Association 2010 to 2012, MSU Distinguished Faculty Award in 2004 to 2005, co-editor in chief Statistics and Priority Letters July 1, 2007 to December 31, 2013. I think with this brief introduction, I invite Professor Kaur, and he's a regular visitor of Pune University also. He usually comes every year because of COVID. He couldn't travel to Pune recently. Okay, over to the Professor Kaur, sir. Welcome.
Professor, you are unmuted. We can yeah. Click on yeah. Can place slightly, yeah. Now it is fine. Professor, whether the laptop audio switch is properly on, whether it is active. So we can, yeah, we can see the slides and all those, but we can switch on that F1 or F3. What are you? Depends on the laptop. Depends on the laptop. There is a sound audio button is there in this laptop as you in the like the last time day before, yeah. We can't able to hear you, browser. Okay, yeah. It is okay. Yeah, it's I don't know whether it is with this laptop. It's not. We can't able to hear you. Yeah. The laptop switch. Click on that laptop switch. Just light. With light. So slides are visible, no problem. Now it is okay. I think so.
Yes, it's okay. It's okay.
Okay, but we can't able to hear. We can't hear you. Can't hear you. Yeah. Can you restart, Professor? We have time, no problem, because this lunch time is there in the between. Don't bother about that. So, but can you restart it and once again? Probably it is due to the laptop. We can see the slides and your desktop also, but we can't able to hear you, mainly because from, I think, because of the laptop issue. If possible, it is better to restart, probably.
I think he has already started, I think he started.
Yeah.
I think last time also the same problem was there, no?
Yeah, there is some.
Yeah, it may be due to last time.
Mic is muted.
Okay, now can you hear me?
It is fine, sir. Now it is.
You can hear now?
Yeah, yeah. Now sound is clear. Yeah.
Okay, let me just now open the file.
Yeah.
Can you see my talk?
Not yet. If needed,
Now I'm going to do it again, same thing as before.
if needed, Nikhil will share from here so that if
No,
needed.
no, okay, I'm going to upload this one. Let's see.
Yeah, just try. Okay, Professor. Now it is coming.
Yeah, you can.
Can you see it now?
Yeah.
Now we can see the slides also.
All right.
Okay, Professor. Okay, please.
All right, thank you. Thanks, technology. Thanks for technology. And now, okay, let's see. I'll just do this go like this.
You can do full screen.
I can read it. It's okay. You can read this way, no?
Yeah.
This is the first one. Thank you for the invitation, and thank you, David, for kind words. And this talk is joint work with young colleagues here, Monica Bhattacharya from IIT Bombay, and Nilanjan Chakrabarti, who just graduated from Michigan State and is at University of Washington, St. Louis. And it's because of their energy that this talk has come to this place at this stage. All the work is theirs, but anything I say wrong is mine, or anything wrong with the talk is mine. Everything good is their work. So we shall describe some asymptotic results about a weighted L1 penalized corrected quantile estimator of the regression parameter vector and one of its adaptive versions in a sparse high-dimensional measurement error linear regression model. The measurement errors in the covariates are assumed to have linear stationary temporal dependence and a known Laplace marginal distribution. And the regression errors are assumed to be independent, non-identically distributed random variables having possibly heavy tails. The rates for the L1 consistency of these estimators and model consistency for the adaptive estimators are derived or will be presented. And a finding of simulation study that assesses finite sample performance of a proposed adaptive estimator shall be also presented. As you see, in the last 25 years or 30 years now, it has been exponential growth in this research on high-dimensional problems, where number of parameters is much larger than number sample size. Under the classical IID covariate setup, different types of lasso estimators of high-dimensional parameter and sparse regression parameter vector have been well studied, both theoretically and computationally. These estimates are shown to be successful in consistent estimation and variable selection. We can find many of these results summarized nicely in this book that came in 2012 by Billman and Sarah Van de Geer. There are numerous applications of regression models where the true covariates are unobservable. Instead, one observes the surrogates, and these models are also known as errors in variables regression models. Now, these models have been around 120, 125 years, and a lot of activity is always going on in this area. The importance of these models in a variety of fields, including health science and econometrics, is amply demonstrated in the monographs of Fuller, Carroll, Rupert, Stefanski, Crenshaw, and the references therein. In the high-dimensional errors in variable linear regression model, where regression and measurement errors are IID sub-Gaussian, a suitably modified version of the least estimator is studied by these authors. In practice, regression errors can have heavy tail distribution, and it is well known that least estimator is not robust against these heavy tail distributions. So the problem is that you have high-dimensional problem, you're trying to protect against some robustness against heavy tails. So what do? You cannot use least squares. Well, when there is no measurement error, these authors Belloni and Chernozhkov, Wang, Lu, and Wu and Li, and these other Fan and Barut propose quantile regression estimator in sparse high-dimensional linear regression model. But when there's no major error, when the regression errors are independent and have non-sub-Gaussian tails. Here, we consider sparse high-dimensional errors in variable linear regression model with moving average measurement errors with Laplace marginal distribution. When the regression errors are independent, non-identical and have possibly heavy tails. Now, the question may ask, why are such measurement errors important? This moving average measurement errors, are they really important? Do they arise in practice? Apparently, I think back in 87 and 90, discussed numerous examples from economics, social, and physical sciences, where such models do arise. Errors in variable models with measurement errors, moving average measurement errors are found useful. I mentioned two examples, how these are Hausman and Watson and Miyazaki found these models useful when modeling unemployment data and the National Crime Survey data of the USA, respectively. That's back in late 80s, early 90s. McKinsey found them useful when inferring in the presence of GPS measurement error. So there are many numerous examples out there where such models have been used and found useful in practice. For errors in variable linear regression model with P fixed, so these authors, Wang, and Zhu, introduced corrective loss function for quantile regression. See, analogy is like this. When you have errors in variable linear regression model, least square is not a good estimator. You have to correct for the bias. So there's some correction needed for that. Like that, if you want to talk about quantile regression estimator, you must correct for the bias. And they were the first one to introduce that correction. And then they, once they had the loss function defined, which is properly corrected, then minimize that to estimate the parameter. And they established some properties of such estimator. Regression consistency, and they had what they had is Gaussian, but their assumption errors, regression errors were Gaussian, IID, and measurement errors were IID Laplace, giving you some heavy tailness in measurement errors. For errors in variable linear regression model with P larger than n, these two codes considered a weighted L1 penalized version of the corrected quantile regression function. So what we are doing currently in the sparse high-dimensional regression model with IID Laplace measurement errors, and when the regression errors are independent, non-identical, having heavy tails. In this talk, we're going to extend that to the situation where measurement errors are moving average measurement errors. So with them, is a non-trivial extension and a useful one, hopefully. Okay, let's go to model. We have simple linear, not simple, multiple linear regression model. That's parameter of interest. And these P variables are the design variables, and they're non-stochastic, non-random. But we don't, and then we have this, we don't necessarily assume errors are mean, but we have quantile. Xi prime beta naught is a quantile or tau quantile of yi, or quantile of epsilon I is 0. Epsilons may have different distributions, but they have same tau quantile. Tau is given, like tau could be median, tau could be 75th percentile, things like that. So 0 is the tau quantile. Errors may have different distributions, but they have 0 as tau quantile. Xi's are not observable. That's when measurement error model comes in. Instead, we observe wi's with some error, to error. See here. And now it is eta i's. Remember, they are p-dimensional. Eta i's are p errors, and we model them to be like this. Now, what are the GI1 and VI1 and GI2 and VI2? Well, VI is each one of them moving average with known matrices. These are matrices here. Well, GI are Gaussian. Both GIK, GI1 and GI2, both are Gaussian independent. And zeta i's are multivariate p-dimensional Gaussian for both Ks, K1 and 2. Okay. Those as those variables. And age are known matrices. So the measurement error distribution, known distribution. It's a kind of important assumption here, otherwise sometimes problems cannot be identified. So in this case, everything is known about measurement errors. Now, from here, if you take linear combination of measurement errors, they have a Laplace distribution. which is the scale parameter sigma d square, delta square. And the temporal dependence on eta i's is induced by these moving average models of VI1 and VI2. So that's our main matter structure. Next, we'll define what is the loss function. So now, in this case, you see, you can't pretend that all betas are there supposed to be. Some betas will be zeros and some are not zeros. So number of non-zero beta is denoted by SNs, small sn, lowercase. Then the component is set up all those parameter values or those components of parameter for which they're zero. And the norm is element norm, so to say. Now we take this normal kernel, then this normal distribution function, first derivative, and here's a smooth loss function. If you had the ordinary quantile function, you would have just first component only, x times tau minus 1. But this is the smoothing part here. H is the window width. Now you define this psi hx like this. And these are the errors. This will be errors if the xi was wi, but now we're pretending we have the wi observed, but then there's some error, extra error there. And let's define the li beta to be this thing here. It takes this one and subtract this factor. And that's a correction suggested by those authors, Wang, Stefanski, and other people. And our loss function is this. Now, if there was beta was finite dimensional, we would not have to penalize. We are penalizing it by taking this, adding this L1 norm part. Lambda is the cost of penalty, or amount of penalty, so to say. And this is the loss due to penalty. And what are these D's? There are some non-negative numbers. Okay, I define this theta here. And these are non-negative numbers. So weight, this is then called weighted. This loss function, weighted L1 penalized loss function, quantile loss function. L1 is called the weighted L1 corrected quantile loss function. And the estimate that minimizes that is called the weighted L1 corrected quantile estimate of beta naught. Okay. So go back to loss for a minute here. This function is a smooth one here, so to say. Original loss function, in fact, only quantile regression is not that smooth. It's non-convex, so to say. And what these authors showed that because of this non-dimensional disk, they approximate this by smooth functions, these, in this sense here. This approximation of Rho is useful in quantile regression with non-stochastic predictors. But when you have measurement error, what you need to do is you really need to approximate this entity here, which you cannot do by just taking this here. So you have to correct for that. That's what these authors did. So in this sense, what we need is really, we need to have something on average value of this should be close to converge to 0. But that doesn't happen if you don't make some correction. This analogy is similar to when you try to correct least square estimate. So in the case of ideal Laplace measurement errors, these authors showed that the correction factor is this factor here. So they define this new loss function, and then it turns out the difference between that and this one on the average is 0. So this is a correction due to measurement error to the regression quantile loss function. Now, this correction works in the case of Laplace and depends on what other measurement error distributions you have. And every time you have different measurement error distributions, you have to work hard to prove that. Or it turns out this fact continues to hold in the current situation that we have. Now, a little more on notation and assumptions. So the gamma p is this AJ norms 2 squared is the largest eigenvalue of A prime A. And then the gamma p is sum of those eigenvalues. And this is tail end. This is gamma p square is tail part of that. And here are the assumptions. First one is assumption about regression errors, that they are different distribution, but each distribution has a density of 5, which is positive at 0. Remember, 0 is the median, or 0 is the quantile of quantile of errors, regression errors. And then, such that this thing holds. So in other words, Fi has to be only density of capital Fi in the neighborhood of 0. It has to be derivative kind of thing. But it has to go to 0, if x goes to 0, it's a rate. This difference. On measurement errors, we assume eta is a measurement errors, and this gamma p square is finite. That's an additional assumption. Some of this squares of eigenvalues, some of the eigenvalues of a prime, aj prime, aj is finite. And from this assumption, we can say that there is a bn such that the tail part, bn goes to infinity, and the tail part can be controlled at this rate. It goes 0 by this 1 over this rate. Remember, p tends to infinity this problem also. P and Sn is the number of non-zero betas. We allow that to infinity also, but it will be seen it will tend at this much slower rate. The Sn divided by P will typically tend to 0. Now again, I remind you what S is. S is set of all the indices for the jth coordinate of 2 parameters not 0. And Sn is the number of such cardinality, the number of such indices, a number of such parameters, number of non-zero, not parameters, components of the parameters. X is our matrix, the gamma is diagonal element, and then with a small notation here. If I take any subset of these indices, and I say take a vector delta and Rp, real vector, P is a vector, then delta sub B denotes a vector of those vector whose ith coordinate is the same as delta, the same as that of delta if I is in B, and equal to 0 if I is not in B. So I give an example. Suppose P is 6 and B is 1, 3, and 6. Then, and delta is a 6 vector. Then delta B is, so I is in I is in B, so delta 1. There's no here, so it's 0. Third coordinate, delta 3. Fourth and fifth are not 6, delta 6. So again, delta sub B denotes a vector whose ith coordinate is the same as that of delta if I is in B, and equal to 0 if I is not in B. Okay, that's an example then. Assumption says for all delta, all vectors delta, and some positive sequence tends to 0, such that this entity tends to 0. This norm, it means if this norm is approximately the same as this norm, the order of magnitude is the same, then that should imply these are similar or comparable. Order of magnitude of these two is the same. It's a technical condition. Then also we assume that our covariates are the original excises are bounded. They're all bounded over NP and I and J. Okay. And as you know, if there are tons of examples where covariance predicting variables are bounded. Okay, now with Bn and Pn as above, then we assume that define n not n. This is the entity that comes up, shows up in the rate, but we have to assume that this turns 0. So in the IID case, there will be no Bn. The rate will be something like this without Bn. Okay, so another entity we defined as D min and D max. And we assume that these are satisfied this condition. D max is bounded and D min is bound from below. Is bounded from above. Once you have those conditions, then there is a theorem that says the following. Under the setup and all the assumptions, the rate of consistency about beta hat to beta naught, in L1 norm, then we remember summation component beta j hat minus beta j naught hat, absolute, sum over all j, 1 to p. That tends to 0. If I divide that by this entity, then that will tend to 0. Now we know that n naught, n tends to n sub n naught tends to 0. So assume that, then therefore this tends to 0. But we give a rate also at which it tends to 0. Now, what problem is that one of the problems in this area is that you must also correctly identify the beta parameters that are not 0, parameters that are 0. So with probability 10 to 1, what this says, beta j hat with j in SC, that means one component may be 0, two parameter value may be 0. So the beta j hat may not be 0, but lies within some neighborhood of n naught, or beta equals 0. So what we'd like to say in this case that beta hat j is 0, probability of beta j being equal to 0.
Madam.
Okay, hence beta hat does not guarantee whether the support of beta naught is recovered, because there is a possibility of getting a non-zero component beta j for some j in SC. So here, so beta hat does not guarantee whether the support of beta naught is recovered, because there's a possibility of getting a non-zero estimate of beta j, and that is 0. Actually, beta j hat super 0 should be there. What's some j in this? Okay. So for that, we need to define new estimator. Again, we make extra assumption here. Namely, that smallest component, see, okay, here's motivation a little bit. Signal for recovering support of beta naught is minimum of these things. Higher signal makes recovery easier. So that's why this leads to the following assumption. Okay, so after that, here's how we define the adaptive estimator. We first compute beta hat, minimizing its loss function with no weights. And we define this set S hat, where all those values estimated exceeding this threshold. And sub n naught, there's 1 minus delta or 2. For some delta positive. Okay, and that delta will be same as in this assumption here. Okay, then we define this new estimator by optimizing the loss function with this DJs, but those DJs that satisfy this condition here. So we put extra additional condition weights DJs that satisfy this condition. Now here everything else is known. The CX is bound of largest value of design variables. Gamma P is the sum of the eigenvalues of AJ squared. A prime, AJ prime, AJ. SN is the number of non-zero beta J's. So lambda is the penalty amount. H is the window width, so to say. So we need to use those weights. That's why this condition. Use these weights to define beta double hat by minimizing the original loss function. Okay, and they should also at the same time, the maximum DJs in S hat should be 0. The corresponding largest weights should be 0 in probability. Okay. So then this theorem says, under these assumptions, probably S hat equals S tends to 1. Now, so remember S is the set of all components of beta vector which are non-zero. S hat is set of components of beta j hat for which beta j naught hat exceeds certain threshold. But we're showing probability of this equals this, tends to 1. So we're recovering one of the exact betas which are non-zero. And the signs of betas also recovered. And consistent rate of this estimator, this adaptive estimator, is n tilde n. What is n tilde n? Is this factor here. Okay. So this factor was there to begin with, n 0 when we're estimating using beta hat. The only difference is in this factor. Okay. So here, because by having these proper weights, we can get this here. All right. So this is called, by the way, these two properties together. Probably this happens and this happens. It's called model consistency in this area. And of course, then this usual consistency part here. Okay. And now let's see what's going on next here. Now I'll give you an example of weights that we can use that satisfy these conditions we have here. Suppose I pick up omega n, which is a sequence of numbers bigger than 1 but tends to infinity, and define this set here, set of real numbers, which are in this interval here, and raised to n naught is 1 minus delta over 2, and w and omega n times this. Omega is bigger than 1. And then these are called smoothly clipped absolute deviation weights. We define these DJs like this. If the beta j component is less than this, remember we have computed beta j at first, unweighted betas. Then if beta j hat belongs to this interval here, then we define DJ to be these weights, and then to be 0 if they are above that. Okay. Those are called SCAD, so to say, SCAD weights, smoothly clipped absolute deviation weights. Then there's another set of weights, which is called minimax concave penalty weights, which are defined as follows. You define the set Cn. Now, you see, compared to Bn, there's no difference, minus this to plus this. See, previously we had this to W and this, right? But Cn is this set here. And now we define this DJs to be these things here. Beta j becomes Cn, to be 0 otherwise. These are called minimax concave penalty weights. It can be verified that both weights satisfy this condition. And remember, n naught n tends to 0, so they do tend to 0. Okay, and if anyone interested in knowing more about these weights, they are discussed in this reference here. Benny. Now let's go to some simulation, and I'll now use examples of where this n naught n tends to 0 and so on. So what we did in the simulation, we had to get AKs, we had to know N, P, S, N, lambda naught, lambda N, H, and beta naught. All these things have been known. Okay. First, we had to see how we can get the design variables. We generated Xij's to be IID uniform minus 2 to 2 if I is between 1 to n over 2. And for I bigger than n over 2, we define them to be like this. And stand for all j's. So that's how we generate Xij's. Once we obtain such, then we kept them fixed throughout the simulation. And remember, in this case, maximum of these is 2. Absolute, maximum absolute is 2. So Cx is 2 in this example. What kind of measurement errors did we use in simulation? It's called Varma 1-1 model. Remember, measurement errors were defined the VIKs and the AJs. So VIKs are generated like this, where phi1 is a matrix this type, minus 0.5 or half raised to I minus j here, ijth component of the matrix. And this is standardization here. And we need only phi1, but we need psi 0, psi 1, and psi 0. Psi 0 is this, that psi 0 comes here, and psi 1 is this here. Remember, IP is a P by P matrix, diagonal matrix of ones, identity matrix. 1P is a vector of ones, P-dimensional vector of ones. All right. And once you have these, then we know what, remember, new IKs are supposed to be summation AJ zeta I minus j raised to k. So what is AJ? This gives you what AJ should be. So AJs are this. A0 is this. AJ is this one. For J we're going to 1. And now they satisfy this condition here. So you have exponential decay in, see, AJ2 decays exponentially in J and of the order n minus 2 here. And gamma P then here is, because this is a geometric thing here that's converges, only part is ON minus 2. And this one is then, because of, again, geometric behavior of the order, it's a constant number less than 1 raised to power Bn. But there's n minus 2 here. So then you can solve this equation to get what Bn should be like. And if you, in this case, you also allow, see, P tends to infinity, n tends to infinity, but in this example, you can allow P over n tend to infinity. So P is really much larger than the sample size. And in this, we in fact show or see that P can be chosen to be exponential power of some power of n. So this is in some sense called ultra-dimensional, ultra-high dimensional setup. So, but this gives you Bn to be log of order log P, and then you plug that into n naught. We'll come to that later, but let's do a second example. It's called moving average polynomially decaying AJs. Here AJ is like this. Then in this case, you have polynomial decay in AJ2, the sum of the eigenvalues of A2s, the AJ cross AJ prime AJ. AJ2 is itself, then sum of those will be then finite. And gamma P is of order P minus 1, yeah, because the summation is finite. And this one is Bn is of the order this. Can be seen again using these techniques. Now, you have to generate data from these time series, these moving averages, and we use in the R language, we use this program to do so. About error densities, what did we choose? We chose these error densities. They get heavy tail, so to say, both cases. And then, see, here's an example P. P is exponentially far growing in n. And this high, so it's ultra high dimension. Here, P equals n, Sn equals this. And this n's were taken with multiple 10 raised to 3 or 5, 10, or so on. So as our weights, we took scared weights. The delta equals 0.5, W omega n equals this. Okay, because delta is 0.5, and so the distance to infinity, but it's bigger than 1. And D max here is of the order of this thing here. Now, what is n naught and n naught tilde? So in this case, n naught n is this entity here, because there was this Bn plus 1, Bn is log P, so there's log P cubed there, so it's log P squared, then there's square root there. So if you plug in these values of lambda and h and all that in this, you get this thing to be of the order like this, and which is of the order n raised to minus 1/8. So n naught tends to 0 at the rate n minus 1/8. So L1 consistency rate of beta hat in this case is 1/8, very slow. But what can you expect? P is very large. And then tilde, if you do similar calculations, it turns out it's a little better. For adaptive estimator, consider is almost half, like almost root n. Okay, that's much better. So then for a second model, where n equals p or p equals n, this n naught is like n raised to minus 1/6, and n in tilde is like n raised to minus 1/6 also. In the objective function, we use above scared weights, then this and w equals this, delta equals 0.5. Yeah. Now, number of parameters we had to, what we did the following. We draw a simple random sample size root Sn from 1 to p, and denote that with pi1. Next, we draw an independent random sample of same size from uniform 2-5 distribution. Replace components of this in pi1 by beta naught by the observations from uniform 2-5. Next, we draw another random sample, simple random sample size, this one, from 1 to n, after removing pi1, and denote by pi2. Replace components of this by an independent sample from this uniform distribution, and then all other parameters in the beta are set to be equal to 0. Once we did that, we generated 1,000. What happened here? We generated 1,000 data sets from each of the above models and computed adapt to this estimator and the relevant norm using the gradient method proposed by Agarwal in 2012 for high-dimensional recovery. High-dimensional statistical recovery. Then we compute the number of false zero components and number of false non-zero components for each data set and each model. What we tabulate is draw the histogram of this entity here. We also compute the sample median of the number of false zero components, median of false zero components, median of false non-zero components. And this is the histogram, and the figure supports the tightness argument and consistency beta hat double tilde, and the table then the evidence to the model consistent of that beta double hat as both entities here, median of false zeros, median of false non-zeros tend to 0 with increasing sample values of n, p, and sm. So I'll show you a table quickly. N is 5,000, p is 2,500, S is number of non-zero betas is components 85. This number here should be literally 0. As this is increased, they do get to 0. Okay. Here is an example where p is much larger than n, and number of non-zero components 150. And you can see that in both models, ME should be ME1, ME2, otherwise ME table's mistake. So missing number false 0, 0, missing median of false zeros, and median of false non-zeros is 0 also. Similarly here, this is a ME1, sorry, yeah. Okay, yeah. ME2 is this one. Similar findings. But here you can see P is way larger here compared to N. Well, no, P equals 5, P equals N here. Throughout in this example, P equals N. Yeah. But here P is much larger. Yeah. All right, so this histogram is. Now, a final thing I want to say, what is the technical tool we have to devise and do something new about is this, what's called Massard's inequality, which was discussed in this book for non-stochastic predictors. And this is found useful in regression models with non-random predictors and when there is no major error to obtain the convergence rate of an appropriately centered loss function. That's very important in this typical area. In errors and variable model of interest here, the predictors form short memory moving averages. In this way, we also have the extension of this inequality for independent and random predictors and for short memory moving average predictors. These are two new results of independent interest. And let me just give you an idea what the Massard inequality says. In the case, suppose we have Zi Ui, Zi is real random variable, Ui is a non-random, but p-dimensional. Observe and Z and the vector of U are predictor variables, Z has independent random variables, and U has a non-random. Suppose this has any loss function, rho function, which is of two variables, satisfies this condition, Lipschitz kind of thing in second coordinate, uniform in first coordinate. Lipschitz 1. And then define this random variable here. This will be loss function, so to say. So what this Massard inequality helps to do is following. If you assume these U's are like bounded by some number G and they're non-random, then they show that this beta spread of this norm is bound, MG is boundary inequality. It gives you kind of rate of this. And this inequality we extended to the independent UIJs and UIJs which are moving average. And I think at this point I'll stop with this. Thank you for listening. Stop sharing, or maybe I'll leave it on for a few minutes if somebody's question. Thank you.
Okay. Any questions from the audience? Any questions from the audience? Okay. If there are no questions from the audience, let us thank the speaker, Professor Kaul, for an interesting and wonderful talk. And I leave the platform to Satish Kumar. What is Satish Kumar?
Thank you, Professor. Thank you, Professor David Hennigan, for sharing this session in a very good way. And also, there is some timing issues, but it is fine. And we are very much grateful to you, Professor Kaur, Professor Hira Kaur, for your wonderful talk. It's very informative and useful to the young researchers in particular. And on behalf of the organizing committee, we would like to extend our gratitude to you, Professor Hira, and Professor.
Thank you very much
for your support.
Thank you so much.
Thank you so much.
Okay. All right.
Now let us conclude this session. And the next session we have after the lunch break. We can start it at 1:45 itself. 1:45. Yeah.
Okay.
The teacher from ISI, they will organize a session, a special session with some Perumal and other team, other members from the ISI and other related groups. Okay. Let us meet at 1:45. After 45 minutes. After 40 minutes, please. 38.
Okay. Sorry, I took a little bit. Okay.
Okay. Thank you, Professor. Thank you so much.
Yeah.
Thank you. Okay, let us, if we are ready, let us start the session.
Yes, sir, we can start.
Yeah, okay.
All our speakers also joined.
Yeah. All speakers are there in the group. Okay,
yes.
Okay. Hey, Krishnendu?
Yes, sir.
Yeah, Krishnendu, please introduce the chair and invite and support him in further proceedings, please.
Sure, sir. Greetings, everyone. Let us move on to the technical session number 4, titled Statistical Applications in Business and Industry, organized by Dr. E.V. Jijo. Professor E.V. Jijo is the Senior Technical Officer of the SQC and OR Unit of the Indian Statistical Institute, Bangalore. His main research interests are statistical quality control, reliability, quality management, statistical process control, design of experiments, Taguchi methods, business forecasting, statistical modeling, and so on. He has about 50 journal publications of his own. Dr. E.V. Jijo is also a life member of National Institute for Quality and Reliability, International Indian Statistical Association, and Indian Society for Quality. It is our privilege to have you here, sir. With immense pleasure, I invite you, Professor, to chair the session. Over to you, sir.
Good afternoon. Thanks for a nice introduction. I would like to thank Satish sir for giving us the opportunity to organize a session every year. I think from first conference onwards, we are organizing this session on statistical applications in business and industry. And therefore, thanks.
Thank you, sir, for your support. Thank you. Please continue.
Thank you very much for giving us this opportunity. Therefore, these 3 papers are there in this session. So all these are basically statistical applications in different area. So we have 3 speakers today. Professor Sriranga Bhatt, Professor Perumalu, and Professor Vinaya Bhatt. Then first I will invite Professor Sriranga Bhatt for his presentation. I'll just give a brief introduction about Professor Bhatt. Professor Bhatt is working as a professor and head of the Department of Mechanical Engineering at St. Joseph's Engineering College, Mangalore. He also a bachelor degree in mechanical engineering, master degree in engineering management from Manipal Institute of Technology, and he has done PhD in Lean Six Sigma from VTU. And he has plenty of publications, and he has authoring books, and he has a wide range of interest in Six Sigma, robust engineering, reliability engineering, design of experiments, and all. So I invite Professor Bhatt for his presentation.
Thank you, sir. Sir, may I share the screen, sir, here?
Yeah, sure, please.
Sir, can you see my screen, sir, here?
Not yet.
Not yet.
Okay, sir. Sir, I'll just quit and I'll join in other browser, sir. 1 minute, sir.
Okay.
Sir, can you see my screen, sir, right now?
Yeah, now it's coming. Yes.
Okay, sir. Thank you. Good afternoon, all of you. My presentation is basically about the application of mixture design of experiment approach in material preparation, majorly from the perspective of manufacturability. So we are always having a hurdle when we are going to design a material. Most of the time we are going to opt for trial and error method, and we are going to try to design a material which is suitable for manufacturing. But in the actual scenario, however, we are going to apply this concept for the real-time application of a particular thing, then we are going to come across with the different types of hurdles that we need to ensure that its multi-responses are optimized. In the sense, we need to trade off between the different characteristics. Say, for example, tensile properties, then hardness, or flexural properties, or impact strength. In such cases, it will be very difficult for us in order to identify the best composition which will cater the needs of all the things. At the same time, it is best suitable for manufacturability. So in that front, we try to incorporate some of the statistical tools while developing the material for the betterment of industry as well as for the society. So basically, the objective is to ensure or to develop an environment-friendly, low-cost material using natural fibers which are available in abundant in villages. At the same time, to ensure better properties for the material, we have gone for the multi-walled carbon nanotubes. As you are aware, the natural fibers won't give much impact strength or tensile strength when we are going for actual application. So in order to overcome that, we have opted for carbon nanotubes, which will strengthen the characteristics. And in fact, we have approached here the design of experiment approach. At the same time, we have confronted with the different types of characteristics. That's why we have gone ahead with multi-response modeling. At the same time, optimization of it. So another objective is to develop the mathematical or statistical model, which can be used further for the research and development as well as DFM activities. So basically, we have adopted here mixture design of experiment approach. In that, we have used 3 components while designing the material: multi-walled carbon nanotube, cantella fibers, which is available in abundant in the village, and epoxy resin to keep the things together. The major objective is to identify the significant factor and their effects. At the same time, as I have discussed, to create the statistical model, basically to predict the tensile strength, flexural strength, and impact strength of the material which we are going to develop, which can be further used for the R&D activities. Then also, the intention is to identify an optimal composition based on the available data and to propose this optimal composition to the industry for the manufacture of different materials. And basically, we have kept our application from the perspective of office tables, cardboards, exam pads, switch boxes, because it has a good market value in the industry as well as in other area. So with this objective, we have started preparing a novel material. All the materials have been, the experimental materials have been prepared as per ASTME standard, which is prescribed by the American Society for Mechanical Engineers. Basically, we started with the matrix material, which is nothing but epoxy resin to keep the things together. And then we have gone for unidirectional cantella fibers. As you are aware, the fiber can be kept in different direction. As the directions are going to change, vertical, horizontal, or multiple, the strength is also going to change. So at this point of time, we have gone for unidirectional cantella fiber mats, which was prepared manually through some agencies. Then we have added carbon nanotubes, multi-walled carbon nanotube as the filling material to enhance the properties of the novel material. Then we have fixed the limit for multi-walled carbon nanotube as 0 to 1%, and for the cantella fibers 40 to 41%, and for the epoxy resin 59 to 60%, as per the available literature. In fact, we have seen if we are going beyond 1%, then the material and its bonding won't take properly as per the material science and mechanical engineering perspective. So that's why we are limited all these ranges as per the literature review. Then we have used Minitab statistical software to create the layout for the experimentation. In fact, during the time of creation of the layout, we have gone for extreme centroid technique where we are able to give the ranges for each and every mixture component. As you can see in my table, basically there are 3 components and we have fixed the ranges. The ranges have come from the ranges have been fixed from the literature review, and this table was created by the Minitab software. So based on this, we have conducted experimentation. Now for just to ensure that errors are less during our experimentation, we have gone for randomization of the experimental trials. At the same time, we have gone for 5 trials for each and every row, and its average value has been listed here. So we have taken a tensile strength in megapascal and flexural strength. We have taken megapascal and impact strength in kilojoule for square meter. In this way, we have conducted experiment, and all the materials for the experimentation is been prepared as per ASTM standard, as I have mentioned earlier. Now these are the results. So now you can see the base material which was prepared for the tensile strength and the fractured surfaces, and at the same time we have gone for flexural test, and its fractured surface you are able to see using the universal testing machine. Then we have gone for the impact testing machine. In the impact testing machine, we have identified what is the property, what is the maximum level which the material can withstand the impact properties. So after this, coming to the statistical analysis, we have gone for the Cox response trace plot for all the 3 properties of the material, that is tensile, flexural, and impact strength. And you can see there is a dotted line which is going to act as a reference point, and reference point has been specified over here. Now this indicates that the blue color line, which corresponds to multi-walled carbon nanotube, this is going to indicate that the strength is going to, tensile strength is going to increase to certain point linearly. After that, it will be in a steady state, and once again it will increase slowly. This is basically from the experimental data. However, you can see the cantella fiber, the inclusion of cantella fiber will increase the tensile strength to certain extent. There is a reference point. Then afterwards, it will decrease. The similar approach has been observed even for the epoxy resin. It indicates that after certain point, if I'm going to add the cantella fiber or even the epoxy resin, it won't affect the properties of the material. Basically, it is for the tensile properties of the material. At the same time, we have used another plot to understand how the material is going to behave statistically. So you can see here, the same pattern will be able to see even for the flexural property of the material. However, this is completely different when I have taken into account the impact property of a material. In the impact property, you can see the red color dotted line, which corresponds to cantella fiber, keep on increasing. In the sense, the more number of cantella fiber in the material will increase the impact property of the material. However, the epoxy resin, increase in the epoxy resin will decrease the property of the material. At the same time, we can also see that more CNT will lead to the increase in the properties of impact material, but it will reduce after some time. Now, this is a major problem when we are going for the actual manufacturing of a particular material for the application purpose, because we need to cater the needs of all the properties which are essential for the manufacturing of a particular product. So based on this, we are able to understand and we are able to fix the limit for the multi-response optimization. Now, prior to the modeling, we have gone for a Pareto chart, and the objective of the chart is to determine the absolute value of the standardized effects from the highest to the lowest effect. The reference line here implies the which effects are statistically significant, basically at 5% significant level. Now we are able to understand which are the factor having impact, or which are the factor having statistical significance on the material properties. We can see in the tensile, as far as tensile is concerned, the A is nothing but CNT, and B is nothing but Cantella fiber, and AB and BC and ABC all are having its impact on the tensile properties. Whereas C, its impact on the properties or significance of C, that is epoxy resin, on the property of the material is very much less, because the basic purpose of epoxy resin is to keep the things together. In the similar manner, you'll be able to see here, for the flexural, there are limited number of significant factors and its interactions. A is having effect, B is having effect, BC, AC, AB and ABC are having effect. However, you can see BC and B very close to the 5% significant line. So we can include or we can exclude based on the requirement. But the major difference will be able to see in the impact properties, where AB, A and B only having significant effect. However, BC and AC doesn't have any significant effect statistically on the impact strength. With this understanding, we are able to design the model. So before getting into the model, we have identified what is the R square value for each and every model, R square adjusted as well as R square predicted. We are able to see now tensile, for tensile, we are not able to get a very good R square value adjusted. However, for the flexural and impact property, we are able to get good property. And also at the same time, we are able to see there is a good predictability for the model of flexural and impact. So with this note, we have gone for the regression model. The regression model basically generated based on the Pareto chart, and it's significant. As you can see in the last case, only A and B and the interaction of A and B has been taken into account, rather than taking into account all the possible interaction. So this is the basis. The basis for the modeling is nothing but Pareto chart and its effect, and the predictability and R square value of it, or each and every equation has been presented at the top of this particular slide. So with this, we are able to generate a regression model for the design for manufacturability, at the same time for the next or further R&D activities for the researchers. Then we have gone ahead with the multi-response optimization. As I was mentioning earlier, we want to cater the needs of everything, and we want to make sure that it is having good tensile property, flexural property, as well as impact factor properties. So the goal is to maximize all the three properties, and lower target and upper values has been taken based on the literature as well as from the previous plot which I have mentioned over here, that is Fox-Trace plot. So taking into account these two aspects, we were able to define what is the lower limit, what should be the upper limit, and what should be the target. And this is basically from the perspective of application only. However, to make sure that things are very simple, we have gone for weight and importance, that is weightage and importance level for these three properties are same, because we would like to concentrate only on the lower and upper level along with the target as from the perspective of manufacturability. So later we have gone for overlaid counter plot for tensile, flexural and impact strength. The objective of this plot is to visually identify a common feasible region. You can see the common feasible region is nothing but the gray area over here, which will assist in optimizing the mixture component to cater the needs of all the three responses. This was basically developed by specifying the optimization parameters. The optimization parameters are over here, as you can see in my table, from the perspective of industrial application. Now, this will help us to understand in an overall manner where the feasible region for this particular optimization exists. However, we are not in the position to categorically identify what is the optimal combination and the best response for this. So region, we are able to see the region over here. So to overcome this, we have gone for multi-response optimization. So in the multi-response optimization, as you can see here, we have gone for the optimizer plot, and here we have taken into account two very important aspects. One is individual desirability, which we will evaluate how the settings of the optimization of a single response will take place. Then altogether we have taken composite desirability, which is been specified by D, as we can see over here, D, and small d is nothing but individual desirability. D is equal to how the settings to optimize a set of responses overall, and which is being used to determine the best possible solution and maximize all the responses. And multiple optimal solution, which is also known as a local solution, has been taken into account. Now you can see here in the response optimizer, the best solution is nothing but carbon nanotube should be 0.9091, cantella fiber should be 40.09%, and epoxy resin should be 59% by weight. However, the different options have been given over here. So to quantify it, we have gone for the table. From the table also, we are able to see the same. Basically, we have gone for 4 solutions. Among these 4 solutions, we are able to see maximum composite desirability is there for the composition, as we have seen in the response optimizer, where multi-wall composite can be 9% and 40% for cantella fibers and epoxy resin. So based on this, we have freezed our material to cater the needs of all the 3 properties should have this composition. That is by weight percentage. So this was the final optimal solution which we have gathered from the multi-response optimization. So once we have come across with this optimal value, we have developed the material once again. After developing the material once again as per the given properties, we have gone for the testing of the tensile properties, flexural properties, and impact factor properties. 5 responses have been taken, 5 trials. Its average has been given over here. Then we are able to identify absolute deviation from the fit or else outcome. So we are able to see maximum deviation is observed only for 2.3. Rest of the things are within the limit. And there is a good confidence interval and predictive intervals as far as the properties are concerned. However, we can say that 2.3 deviation might be because of the level of predictability which we have seen, which was very low, 77% earlier. And it also might be because of the moisture content or the sonication process, where we are going to mix the multi-wall nanotube. Might be because of that, there is a small deviation of 2.3% compared to the prediction. So this has helped us to ensure that the material which we have prepared and the model which we have generated is more robust, which has the predictability for the rest of the research and development activities. So conclusion is, the chosen component blend, that is cantella fiber, multi-wall nanotube, and epoxy resin, act harmoniously to develop a novel composite material for sustainable manufacturing and from the environment perspective. Also, the novel material provided good mechanical property. We are able to normalize the things, in the sense not statistically, from the perspective of application, we are able to cater the needs of all the properties, tensile strength, flexural strength, and we have got a good strength over there. And composition was 90% of multi-wall carbon nanotube can be used, and cantella fiber should not be more than 40%. However, we can limit the epoxy resin less than 59%. And also we have observed that the multi-wall nano tubes improves all the 3 mechanical properties. However, it's not the same when I'm going to consider the when I'm going to consider the natural fiber in this particular material. Besides, it was clear that flexure and impact strength are improved due to the unidirectional laying of the cantella fiber. Now we are doing the experimentation taking into account multi-directional cantella fibers and the the multi-wall nanotubes, so that we'll be able to understand if there is a difference. And we are also going for sandwich type of materials, where the upper material will be different compared to the lower material. So there also we are able to use a mixture design approach, which will optimize the sandwich material, the top layer as well as bottom layer at one go, rather than going for n number of experiments. So eventually I can say that with the 7 number of trials, 7 into 5 times the trial which we have taken, 7 materials and 5 trials for each material we have taken, with that much amount of materials, we are able to culminate our findings, and we are able to get the material done. However, in most of the cases we have seen earlier, people are using trial and error method, where number of material required to complete or to identify the best composition is much more. Usually more than 100 samples they need to identify the best composition, as well as to identify the model for that. However, in our case, it was less than 25 samples with which we are able to get the things done. Thank you for the opportunity. This is all about mixture design application in material science as well as mechanical engineering field. Thank you.
Yeah, thank you very much, Dr. Bhatt, for giving a nice presentation. Any questions to the speaker? Any questions from anybody? If there are no questions, let us thank the speaker, and then we'll move on to the next talk. The next talk is by Dr. Vinayambiga S. Bhatt. Dr. Bhatt is working as a professor and head of electronics and communication engineering at Mangalore Institute of Technology and Engineering in Mangalore. She has received BE degree and MTech degree, and she has completed a PhD from Manipal Institute of Technology. Her interest includes advanced control engineering and robust control engineering. So, invite Dr. Vinaya Bhatt for the presentation.
Thank you, sir. I'll share my screen.
Yeah, sure.
I hope my screen is visible to all.
Yeah,
it's
fine.
visible. Yes.
Yeah. The topic for today's presentation is like application of statistical and computational methodology for robust controller design. So the purpose of this article is to design a robust control algorithm which is of industrial applications. So in the present study, I have considered a industrial scale distillation set, which is a multi-input, multi-output system. So whenever the system is having multi-variable, that means multi-input and multi-output, the controlling that is multiple tasks, multiple parameter in the system, so that we can effectively control the system for the better outcome. So we are considering here the several control and noise parameter for the design. So the intention of the article is to work on the multidisciplinary, like also been performed, and the system considered is a chemical engineering domain, which is a process is a distillation column, and design of experiment is been implemented here to identify the optimized approach goes like this. So even though the distillation column is a multiple input, multiple output system, in this present study, we have considered only 2 input and 2 output system, which is called as TTO. And we are considering the transfer function model of the distillation column. So we know that any system we can design a model for that. So the model can be continuous or discrete or in any other form. So here in this study, we are considering a transfer function domain, which has 2 input and 2 output. So how did we design this 2 input, 2 output system? We have conducted an open loop experimentation. Based on that, we have obtained the 2 input, 2 output transfer function model of the distillation column in the study. So here there are mainly 3 parameters actually in the design, but in the current study, we will be considering 2 parameter because delay is not in our control. So which are the 2 parameter which you are considering is a time constant and the steady state gain are the 2 parameter which is considered during the design of the control system. And both simulation, statistical analysis, real-time and chemical analysis is being performed. Simulation is to understand what is the optimal parameter. Statistical analysis is supporting to that, which is proving that yes, this is the optimized parameter of PID controller. Once it is being designed, then we have verified it with the real-time experimentation. Once the experimentation is done, the outcome, as we know, the distillation column is nothing but you're giving some impurity into the system and you'll be getting a product, purity of the product can be analyzed as an outcome. So that is been analyzed using the chemical system. That is, chemical analysis is performed to check the robustness of the proposed control algorithm. And also this system is being verified, the performance is being verified using servo and regulatory response. Generally speaking, the servo means without disturbance, regulatory means with disturbance. Whenever a sudden disturbance is added into the system, how the system is performing, that is also been analyzed. So moving on to the setup. So this is my experimental setup. Actually, the experimental setup journey goes like this. So this is how we had actually fabricated this experimental setup in the laboratory scale. And once it is been fabricated, this is the design what we could get. This is the experimental setup what we have. I think there is some. This is the binary distillation column experimental setup. So input here we are giving input which is a product of water and isopropyl alcohol. It's a mixture of both. So it is impure in nature. So our aim is to get a purified product. So what happens here is when in the distillation column, when we heat up through the heater using the solid state relay, the vaporized component, which is lighter in nature, that is being collected in the condenser, and the heavier component is being collected at the bottom of the distillation column. And you can see this is interfaced through a computer where it is being connected to a data acquisition system. And we know that the temperature, once it is measured in degree, we it in of voltage. So we are using V2I converter for the conversion of the input, that is current to voltage. And this is a block diagram what I have considered for the study. In presentation mode, I'm having some issue. So this is the block diagram. As I told, this is a 2 input and 2 output system what I have considered. So these are because 2 input, 2 output means we'll get a 2x2 matrix in the transfer function form. And accordingly, I have 4 controller here. Now, this is the first order. How did I design this? As I told you, this is a transfer function model. So individual block is a first order transfer function. So we are going with the first order transfer function. So this is the time constant, this is the time constant, and this is the time delay. So the structure goes like this. Now, our aim is to design the controller. As you can see, this is what is been designed using the open loop control algorithm, the mathematical model. Now, we need to design the controller. So, the PID controller is most commonly used in the process industry because the understanding and controlling aspect is, and its functionality is significantly easier in comparison to any other platform. And this is the mathematical model which is been identified, which is a 2 input to output. T5 is nothing but the temperature of the top of the tray, and this is the bottom of the tray, and L and Q is nothing but reflex and the reboiler. Reflex means we are giving a cold water input so that the vapor will cool down and you'll get a condensed output. And Q means we are heating it up. That means reboiler. So the heavier component will be collected at the bottom of the distillation column. So this mathematical model is being considered here for the statistical analysis and computation. So the steps involved in the computation goes like this. First is to determine the performance characteristic and process parameter. So in the present study, any plant, it is having 3 main parameters. One is constant, other one is time constant, and other one is time delay. Then we have 3 parameters which has to be controller, that is proportional, integral, and derivative controller. So all these are considered as a control and the noise parameter. Then we need to identify the number of levels of the process parameters. So that is been identified, and here is to find the appropriate OA and assign the process parameter to the OA. Then conduct the experiment based on this arrangement. Then we need to find the optimal setting of the control parameter. Then multi-response optimization is to be done. Computation analysis and validation here, we have used the MATLAB as the simulation tool here. MATLAB Simulink we have used to analyze in the simulation mode, and once it is been analyzed, it has been implemented in the real time. Using that optimized controller, what is the end result? That is been validated using the liquid chromatography, which is a process to verify the purity of the product. So this is the noise parameter and level for experimentation, which is being considered here. So as I told you, delay is not being taken into consideration because delay is the one thing which is not in our control. That is what, based on the literature, the effect of that is not having much impact on the design of the controller. So what we have considered is process gain, that is constant, and time constant, only 2 parameters. Even though we can see here there is a delay 0.03, 0.03, 1.22 and 0.03 are the delay values of different input output combination, but we have considered only the gain and the time constant for the design. And here this is the nominal value based on the identified process parameter. Then we have based on from the literature is say that you can consider a uncertainty of plus or minus 10%. So I've considered a lower plus or minus 10% as my lower and upper limit. Then this is the process parameter. Now our next step is for the controller parameter and level of experimentation. So the controller parameter here being considered as P and I. That is, in a PID controller, P and I plays a major role. That is proportional gain and integral gain. Proportional gain means the present gain, present error, what is it is going to accommodate. Integral means, as we know, it is going to accumulate. It is going to sum up. So that is also plays a major role in the study. So again, we have fixed a range here, the minimal to maximum based on the algorithm. Then the nominal value, then plus or minus 10% is being considered for the lower and upper limit. So this is the experimental layout using. So using a Pareto chart of standardization effect, this is the analysis here. The controller performance is being analyzed using 4 performance parameter, that is integral absolute error, integral time absolute error, integral square error, and integral square absolute error. But in the current study, I have considered only two parameters, that is one is performance parameter, one is IAE, that is integral absolute error, and other one is ITAE, integral time absolute error. The reason why I have considered only two of these is like distillation is a long process. It takes long time. It is a continuous and long process. So whenever the system is running for a long duration in order to achieve the certain result, the error will get accommodated. So we need to minimize that error as early as possible in the initial stage itself. Otherwise, over the period, this error is going on, getting added up as a time lapse. So that is the reason why I have considered IAE and ITAE as the two performance parameter which need to be optimized and which needs to be as minimum as possible. So you can see the effect of that with respect to the control parameter here, which is with respect to two error here, IAE E1 and E2 is corresponding to the first input and the first output. IA2 corresponding to the first input and the second input and the second output. So this is the optimal parameter for the individual responses what we have received with respect to integral absolute error and integral time absolute error. And these are all the target and different upper weight performance which is achieved with respect to the multi-response optimization. These are all the best fit what we could achieve with using this multi-response optimization. So finally, we could achieve this value, that is PI value, proportional and integral value with respect to first input, and this is with respect to first input, first output, first input, second output, second input, first output, second input and output. So that is how totally we will have 8 combinations. So P with respect to P and I value. So 4 KP values with respect to combination 1, 1, 1, 2, 2, 1 and 2, 2 and I values. So this is how we are getting the optimized parameter of all the, which is optimal among all the responses. So this is the response what we have received for this value when we executed in the simulation using MATLAB. You can see the proposed method. Then I have also considered Davison, integral model controller and integral model with decoupler. So all these been considered here. So both main response and interaction response is been recorded. This is using the experimentation. So this has been done in the experimentation for the same design controller we have implemented in the real time. So this is the actual output. Then this is the controller values of reflux and reboiler. You can see here T1 and T5. Bottom tray and the top tray is the output. And finally, the product, whatever is being achieved here, that needs to be analyzed using HPLC, that is chromatography experimental setup. So we have analyzed that outcome, how purity it is, what is the percentage of purification we can achieve using this optimized controller that is also been tested here in the research lab, and we could achieve. See, this is a pure IPA. 6.133 is the IPA value. It's a chromatography level. That is, it is IPA in its. Then this is with respect to that bottom and bottom. This is the input what we are giving IPA, and this is along with the impurity we are. This is the level of the pure IPA, isopropyl alcohol, and the bottom and the top product, how it is been the purity is been achieved. That is been compared with the spectral plot. So chromatography is the one which result in this spectral plot, which through this we can analyze that we could achieve a 90% of the purity with the proposed control algorithm. And this is distilled water, that is a distilled product, spectrography. And this is a predicted and observed response of proximal mixture component, which it could achieve with respect to the two combinations of error. And these are the references what I've referred to work on this article, and there are few more. I only major references source only is been tabulated here. Thank you for giving me an opportunity.
Thank you very much for the nice presentation. Any questions to the speaker? No questions. Okay. Then let us thank the speaker and let us move on to the next talk. Next speaker is Professor P.K. Perumalu. Professor P.K. Perumalu has more than 40 years experience in teaching and industrial consulting and related activities. He was a senior professor in ISI, retired a few years before, and still active in the field of academics and industrial activities. So I invite Professor Perumalu for the talk.
Good afternoon. Thank you, Jiju. I'm audible?
Yeah, very much.
Yes, audible, sir. Very well, Professor. Sorry.
Yeah. I'll just share my presentation. Top management will see? Yeah.
Not yet.
No, not yet.
Not visible. Yes. Wait.
Document verification.
No, the top management sir planted. Shall we start top management, sir? Oh no. I have some listening. I'll come back. I have to make some presentation here. Okay, I will see. I will come. I think there is some problem with this.
Not able to share it?
Yeah, I think I have some problem in this.
So then you can just mail to me, I'll share it.
Now you can see?
No. Yeah, now it's coming.
Okay. Now I have to adjust this. Yeah. Now it is okay? You can see my screen? Hello?
Yeah, it's okay now.
Yes, it is okay. It is fine.
Yeah. You can put in the presentation mode.
Yeah, but presentation mode, if I put, I think the problem is other things are not coming.
Okay, not a problem, not a problem. Okay.
Is it okay?
Yeah, it's okay, fine.
Good. Okay, so my presentation is related to the modeling. One is by forecast methods that we use, different models. And these models, what we use for forecasting for different objectives. Many times it becomes as successful, but sometimes we may have some failures also. So I want to highlight the one success story where it has been tried out and where the results were very good, and the other story where the results were not so appreciative because there are some genuine problems in that. So what were the factors which resulted into that situation? I just also want to highlight that in this paper. Okay, so I start with this, the mathematical modeling, which is used for forecasting and predictions. Like nowadays, the gurus, astrology gurus, every day I see in the TV that they make predictions. This type of, if you are born in this period, you get this type of success, failures today, be careful, if you do this, your failures can be avoided, kind of things, they make a lot of predictions. So this paper, I try to highlight a success story and a failure story, and the issues considered to which will lead to success, or to ensure success, what are the things to be taken care when we are doing some modeling. So one success story is about a flyover bridge, about a tunnel project, underwater tunnel. It is done in one of the project where there was already some projects were there, some bridges were there, and they want to use one more new way of transport to cross the river. So that was the issue. So I will detail about that particular issue, and then how the predictions were done, and what are the factors considered and how they were addressed. And another one is a flyover bridge where the predictions went totally wrong, and there was a lot of congestion in the traffic, and the flyover was made to reduce the congestion, but it didn't help much. So, and then I try to critically analyze and see the factors which led to the success or failure.
All right.
Yeah. So the tunnel project is about in a particular place, there are two bridges to cross the river, the water body, and they thought of coming out with another underwater tunnel. And there is, in addition to these bridges, there is a ferry service also to cross the river or the water body. So a lot of vehicles pass through every day. So the underwater tunnel is expected to ease the traffic congestion and also helps to gain some revenue. So prior to the initiation of the project, the government or the company which are going to invest in this, they want to evaluate what is the feasibility, and if it is feasible, then what are the infrastructure to be built in, like how many toll booths are to be kept, and what will be the revenue per day. So whether the cost that you are going to spend or the investment they are going to put up, how much time it will take to get back that money. Okay, and all these things, because all of us know that the population is increasing everywhere, so the number of amount of traffic or the vehicles moving on the road will also be increasing. So if you consider after a few years, we may take the project, plan the feasibility, and complete the project after a few years. Then after that, another 20, 30 years, they want to see that for 30 years, this project can still help or meet the demand of the traffic. That's what they wanted. After 30 years, what is the demand, and whether this particular project what you take up can ease the traffic at that peak traffic intensity. That is what they wanted to achieve. Not for immediate another few years. After 30 years also, it should be possible to reduce the congestion. So that is what they expect. So average per day total traffic we require to estimate, and to estimate that, because the period in which the traffic will be there, it has its own, like, in some festival seasons, there will be more people crossing the river. In the other seasons, regular traffic will be depending on the people who are the other side of the river. They are staying this side and they want to go other side, vice versa. So there can be some kind of a fluctuations day to day. In one day it can be less, another day it can be more. So it is not that constant all the days. So that's why we require to do some kind of a prediction, and this prediction should be done for a longer period, considering the data from a longer period. So they have taken up for past 3 years data, and from that the government authorities for each of the bridges and the ferry. So they have collected data from the government data. Government data is very reliable in that area. So it is considered as the things that can be based on which you can make the predictions. So the traffic in tunnel was restricted to only certain type of vehicles like cars and minibuses, not heavy trucks are not permitted. And of course, in our places, generally we see one-wheeler to six-wheelers to 12-wheelers, all types of wheelers can pass. But here they restricted that only four-wheelers, cars and minibuses, all four-wheelers only. And then we have to forecast the amount of traffic expected to move in this tunnel, new tunnel, what we expect. Because already there are 2 other bridges available and there is a ferry. In addition to that, there should be some more people they wanted to cross, whether they can use the tunnel. So how many people will be using the tunnel? That we have to make a prediction. And how many, see the number of vehicles passing through this water body, through the tunnel, how is the seasonal fluctuations, or how much is per day people crossing, whether day in the day also, it is peak hours and lean hours, how much traffic will be there in the peak hours, so that when it is in the peak hours, of course the tunnel can be used, but only thing is if there is we are collecting the toll booth should not keep the people for a long queues. So we have to also plan for those things. And you have to use appropriate models for that. So what is done is forecasting models for decomposition or exponential, double exponential, Winters method, ARIMA methods. There are the different methods, as all of us know, are available. So they are tried out for the data, 48 months data, daily traffic. So one of that seems to be good, and certain measures are taken for each of these. Whenever you use a decomposition method or exponential or double exponential, any method you use, you measure the MAP, MAD, and MSD, and another measure used as the Taguchi's ascent ratio. Because Taguchi ascent ratio, it considers the ratio of average to variance. So that is not available in the other 3 measures. So this is another measure where we thought that it can throw us some extra light on the or usefulness of a particular forecasting model that we use. So these are all the different methods or measures are used to find out which model will be best suitable. And among these comparisons, when it is made, we found that additive model is found to be, that is decomposition additive model is found to be more appropriate, considering all the measures. Then total traffic volume estimates for 30 years after building the tunnel. After 30 years, what can be the expected traffic? Up to that is predictions are expected by the investor. So the traffic of cars and minibuses from among the total traffic were estimated, means out of total traffic moving in these bridges and ferry, so how many vehicles were moving, and out of that, how many are cars and minibuses? Because only cars and minibuses can pass through this tunnel, not others. So only how many cars and minibuses are passing every day or in a month, or all those predictions are made, taking the portion of only these type of vehicles. Many other new projects were also planned by the government. So when this project gets completed and it's going to run for 30 years, within this period of 5 years plus 30 years maybe, so there can be other projects. Government is also already having some plans for other new projects. So experts' judgments are collected from the different experts from government as well as private. So to see how much these impact the investment or the revenue expected from this tunnel. because you have another project. Suppose this is a new project, so initially 2 bridges plus 1 ferry, now 1 more tunnel. Yes, there will be a lot of traffic. But if some more new projects come up, then the intensity of the traffic movement on this tunnel can be less. So what is the effect of those new projects which are planned can have on this? Also, some experts' judgment is collected. As the traffic will be shared with the present available bridges and ferry, the preference of the customers to use the proposed tunnel that is collected by doing a customer survey. Because all people may not prefer to go by tunnel. They want to see maybe the sea. So they want to go by bridges. So what will be the customer preference to use the tunnel? How many would like to, if there is a tunnel, how many people would like to use the tunnel? So customer survey was conducted for that. Then to estimate the income, how much the investor can get the money back, the preference of the customer to use the tunnel for the two-way travel, that is going to the other side and also returning from that. So considering the proposed toll costs was also obtained in the survey. That is one way going or two ways going. So somebody may go in one way and somebody can use both the ways. Then if somebody is going to use both the ways, then the amount of traffic can be more. So that's what we wanted to guess that estimate of that. From these estimates, the total average per day expected income was estimated. Project was found at the end very attractive by the investor because the amount of income expected seems to be quite good. So they were quite happy with they thought that this investment is worthy of getting good returns. So this is the per day traffic. So many days it is taken, 48 months, month-wise. And then you get this traffic increasing, decreasing, some kind of a, as you can see, some seasonal fluctuations are there. But as an overall trend indicates, that green line indicates that over the period of the years, 4 years, there is a gradual increase in the total traffic. Of course, there is about the average, there is a peaks as well as troughs. So peaks are in the peak seasons and troughs are in the lean seasons. So there is a seasonal kind of effect is there. So considering that, so we use the decomposition method, and then we use the additive method, not multiplicative, additive method. That was fitting quite well. So these are the accuracy measures we got here. Compared to the others, these are found to be more matching to the actuals. So red is the one which is fitted and black is the actual. The black is the data and the prediction is the red one. So tunnel traffic estimation is done, bridge 1, bridge 2, and then the tunnel. So decomposition methods, different methods are given here. Multiplicative method, additive model, and then single exponential, double exponential, Winters, multiplicative, additive, and then ARIMA model. And we can see different measures here, all the 4 measures, what I told you, for bridge 1 and bridge 2, and then which is fitting to well to that. So that model we should use and then say, yes, we predict. And that is, in the past 4 years, we see that traffic is like this, and we expect using this, whichever model fits, using that model we predict for 30 years. And this is what is expected in the bridge 1, bridge 2, that is the total traffic. Out of this total traffic, a portion of that traffic will go, expected to go through the tunnel. That is depending on the customer's preference. So using the customer preference, we can proportion, okay, if it is so much traffic, out of this proportion or percentage of the traffic will go through the tunnel. If that is the case, then that traffic also will have the same fluctuation, like whatever the model suggests, seasonal fluctuation as well as the trend. Using that, we can predict for 30 years how much will be the intensity of the traffic. Using that intensity, we can actually calculate if you have some prices fixed for that. So those prices, we can see what is the return or the income from the traffic which is going through that, what you can collect. So that is the methodology adopted. So in the different methods, you see that here. So additive model seems to be quite well fitting among all the things. Because one is the SN ratio, highest SN ratio is the best. As you see here, SN ratio model is giving the highest value for the decomposition additive model. So that model was considered as the most suitable or best fitting to the data. Now, looking at the total tunnel traffic.
Sir, you are changing the slides. Nothing is changing, sir.
Pardon?
Sir, not changing.
Changing?
Not changing.
Oh, slides are not changed.
No, it is standing in the first slide only.
Oh, wait a minute. That's what I was expecting. Now it can be seen?
It can be seen, yes.
Yeah. I think that is a problem. If I put the total screen, then it is not changing. So I have to put only this much.
Okay, take it.
I think there is a problem with this. Yeah. So it will be not so big as a full screen. It is a half screen. Okay. So here you can see that the different models and the different performance measures. There are two bridges, bridge 1 and bridge 2. And using that, the model which is best fitting to the traffic is found out. And we see that decomposition additive model is having the best fit to the data. So that model is used for prediction. And then we have to see the different category of vehicles that move through this, or what type of composition is there in the traffic. And we require only we can take only the cars and minibuses. So as you can see here, that orange and green, only that much portion only are aimed to pass through this tunnel, not total traffic. All vehicles are not allowed in the tunnel. So how much proportion is there out of total? So total traffic, out of that cars and minibuses, how much proportion? So that proportion is taken, or whenever we make the prediction for total traffic, we will say that that much only can come for the tunnel. And again, this 100% of this traffic, whatever you say proportion, may not be through the tunnel. It may be through the bridge 1, bridge 2, and tunnel. So how much proportion can come, or how many proportion of the customers prefer to go by tunnel? That proportion is estimated, and from this, let us say this is around 70%. Out of 70%, some percentage is preferred. So what is that percentage? From that, what is the intensity? That is the methodology used. So cars and minibuses, as you see here, it is 51.7% cars and another 2.9% the minibuses. So it's around 54, 53.6 or 54%. You can go somewhere or here. Okay. So 53.6% of the total traffic is comprising of cars and minibuses. So that much is the one which is allowed to pass through this tunnel. So if you look at the preference by the customers, when they did the survey, the customer preference for using the tunnel came out as 63%. Means that 63% of the customers have told, yes, we prefer to use the tunnel instead of the bridges. So that much proportion is taken from that 54%. Total 54% of the total traffic is cars and minibuses. Out of that 63% only is the expected traffic through this, expected. But out of that again, some more can be less because it will be shared by the bridges also. So preference for both sides as well as only one side are again collected, that information. When they said both, yes, both the sides they will use, it's around 36%, only for going or only for returning, and we don't want. So that proportions are taken. So you see that both the sides coming using that is 36% only. So that is used an estimate to see the people go and then come back. Suppose you give some discount for two-way, then so many people will be using that. 36% are willing to use that kind of a discount. Then you can see, okay, so number of traffic, so many people go, so many people will be back, plus some additions. Okay. So it can be used for that predictions. Okay. So then using that model, additive model, so we make the predictions for 2011, 12, etc., up to 30 years. So 30 years it is supposed to grow because population is growing. Population, how much population is expected, or vehicle population is expected to grow. That is taken from the government predictions. And from that predictions, we have seen that this much is the total traffic. So how much traffic can come through the tunnel? As you see here, it is two-way customer preference after the effect of related plans. Means the government has another plans for some more projects. After considering those effect of those projects also, we can expect that so much two-way customers can be there. So year on year up to 2030. Then this is a monthly figures or on an average figures. So now this traffic will be every day. There will be some fluctuations because there are some peak hours, there are some lean hours. In the peak hours, so many vehicles will be coming as a group, and then when you have a toll booth, there will be long queues waiting to give the toll and then move. So that also has to be considered, because if more jams are there in the toll booth, then people may prefer the other way. So preference can change. So that's why you have to fix the number of toll booths required, but that should be based on the peak traffic, not on the lean traffic. So how much is expected the peak traffic, or what time it is expected the peak traffic? So for that, half-hourly traffic volumes were estimated by actual conduct of a survey of the number of vehicles using the bridges and ferry services. So total traffic, hourly it is distributed in a day. 2 working weeks data was collected and analyzed using the decomposition method, again additive model. It was fitting best to that and did hourly, half-hourly working. I mean, how much is the traffic? Half-hourly variations from the day average was estimated from the peak hour traffic. This traffic was considered for estimating the toll booths requirement. Okay. So a number of surveys were involved to collect this data. As you see here, this is what is that data that was what was used. So different, these are class 1 and class 2, some arrival and departures, okay, AVR and additive models. So using these and different measures, accuracy measures are computed. And you see data was quite well fitting to this. 2 weeks data was collected, half-hourly. So half-hourly means it is every day you got 48 results. 48 results for 48 results into 2 weeks. So much of data. So this is the time wise. So I think there is no support, right? Yes, there is no support. So one way going, the other way coming. So in both the things. One way going is this, and both the ways they use is this. So different timings. So 7 to 7:30, 7:30 to 8, etc. And you see there's sometimes there's a one way from A to B. Crossing one side to the other side is more. In the evening, the return is more. So total traffic is distributed among these. So 3 types of toll booths were again planned: OGS, automatic, and KGS, card usage, and cash payment. And you have to see that number of arrivals were considered as 40, 40, 20 of the maximum of the peak hour traffic for each of these 3 types of toll booths. This is again some estimates based on their experience, experts' experience. So average service timings of 3, 5, and 10 seconds were considered for booths respectively. That is 3 seconds for OGS, and 5 seconds for card usage, and 10 seconds for cash payment. So considering this, the MMS model was taken, and how many number of booths are required so that your queue length will not be very high, very long. Okay? Waiting time is not too much. So 2 number of booths for each were found adequate to meet the demand at the allowable queue length and waiting time. So using that MMS model, the queue length, and it was found that this can be adequate. So the tunnel traffic you expect, and the amount of investment you can calculate from that. So using these booths, so arrival rate and service rate, length of queue, all are taken here. For this 222 model, this is the timings, and this meets the requirement. So heavy traffic congestion at one of the very busy injection flyover bridge. Okay. So this was the thing, and this was suggested to the investors, and they accepted that yes, it is okay. And it is seen, this was done quite a long back, and it was seen that yes, the project has been completed, and the investors are quite happy with the predictions made, and they were coming quite close to what predictions are made, and actuals are matching to that. It was that way. It is considered as a success story of estimation. Another story is there. There was a flyover bridge that was planned. In that flyover bridge, because of heavy traffic congestion in the city, in a particular busy junction, they thought that they should have a flyover bridge to reduce the congestion. And here it is not because there are no toll booths or something. It is only to reduce the congestion. Means, so traffic jams should be less. So traffic data was computed from, again, a team was assigned the job to collect data of how much traffic moves through that junction. So one side to the other, and different roads are there. Some 5 roads it is a 5-road junction. In the 5-road junction, each how many sides from one side to the other, how much traffic is there, and what kind of vehicles, how many vehicles, and the mix of the type of vehicles. All that data is supposed to be collected, and this data was collected and given to the planners. The end result was bridge was constructed and used as a one-way bridge from one side to the other side. Some 2 different roads were connected, 3 roads were connected by the bridge. So it is expected to reduce the congestion, but congestion still remained after constructing the bridge and usage. Still the congestion was there. To reduce congestion further, it was thought the bridge to have a traffic light on the top, because supposed to be used 2 ways, but instead of that it was planned as a 1-way, because that is what the planners have got. The traffic moves from this to that. So you only plan that bridge for the traffic moving one side to the other. That's all, not from the other side. The result is a traffic signal put on the flyover bridge. On the flyover bridge, there is a traffic signal has been installed, because it is having 2-way traffic, not 1-way traffic. So
Sir, another 5 minutes.
Hello? Yeah, okay.
Within 5 minutes.
Yeah. So it was thought of that, yes, we have to put a traffic signal on the top of the flyover bridge. And then what happened? Matter was published in a news magazine that this is the only flyover bridge in the whole world where there is a traffic signal on the flyover bridge. So then the people woke up and they said, okay, we'll make it as 2-way. So they made some alterations and put it as a 2-way bridge. Now the congestion was slightly less, but not the extent that is expected to reduce, but yes, it is now less. But then this gives an idea to look at what went wrong. Why the 1-way bridge, whatever planned, didn't work out. What were the factors? If you look at that, the statistical samples were very small, and data was generated Later on, it was found artificially by simulation. Means they collected some data for 1 day, maybe half a day or something, and then simulated that and projected that for 2 weeks it is this. And the direction in which traffic moves, the type of traffic it moves, so that was also not properly estimated. They are studied for only a part of the day, not full day. So if wrong data is fed, the result will also be wrong. That's what happened in this case. Lack of forecasting of the rise in traffic intensity in future, that was not done. At that time, what was the traffic intensity? That was only considered, not the future expectations. Type of traffic also not indicated correctly. Other plans in traffic movement. The government will have other plans for reducing the traffic, or they will make one-way roads, or they may put some more arterial roads. That was also not considered. So with all this, the shortfalls of the lessons learned, inaccurate data. So you require accurate data for any predictions to be successful. False data generated, it will be putting the entire project off guard. All variables are not considered. Future variables to be used in planning are not considered, like, no more for future projects that the government may come up for reducing congestion. They are not considered. The trial run to take care whether something error is happening. Always we go for a learning data and then use that for proving the data is the model is correctly implemented, showing that variations in the data. That was also not done properly. So with all these lessons learned, I think the future projects, I see that it can be better. So the point I wanted to highlight here is, when you want to use predictions, you should always consider that all possibilities and then make the prediction to suit to those possibilities. It was not done, you will result into a very failed project. So there's a point I wanted to highlight. Yeah, I think that ends my presentation. Okay, so any questions?
Yeah, thank you very much. Any questions to the speaker?
Here on one date, you send August.
Okay.
Yeah, if there are no questions, let me thank all the three speakers for completing the talk on time. And then thank you very much, Professor Satish Kumar, sir, for organizing.
I also thank Mr. Satish Kumar for giving this opportunity.
Yes.
Thank you, Doctor.
Thank you, sir. Thank you.
Thank you, Professor. Thank you.
Thank you very much. Thank you, sir. Over to you.
Yeah.
Thank you.
In fact, we are very much grateful to you, Professor Jijo, for your support to our activities through organizing groups of people and very interesting sessions. And your speakers are also very special speakers. In fact, they are experts in the area. They have given excellent lectures. In fact, benefit to several researchers in our group. Anyway, we are very much grateful to you, Professor Jijo, as well as the speakers of the session, Professor Perimalu, Sri Rangabat, Dr. Vilayambika Bhatt. Okay. We expect your support in future also. Once again, extending our gratitude on behalf of the organizing committee of the conference. Let me to thank you all. Thank you so much.
Thank you, sir.
Thank you, thank you, thank you, thank you. We expect your continued support.
Sure, sir.
Thank you. Also, those who have any doubts, you can directly contact to the speakers. Their email IDs are available, or even their details are there in the website. Okay, now let us move to the next session. Before moving, what about the we have some more time, because next session is 3:20. Begins at 3:20. So we have 10 minutes time. By that time, we can. I hope anyone to interact with others. Or hi, Kajan, President Kajanjay.
Hello.
Yeah. Yeah.
Yes. So we can wait
Very,
for
very
10
good, sir.
minutes.
Good afternoon.
5, at least 5, 6, 7 minutes we have to wait.
Yeah, it's
Otherwise,
3:10.
probably, yeah, this
So-
is a platform. Some people are there probably to join for this.
Yeah, yes, we can wait.
Yeah, let us wait.
Hello, Dr. Jijo.
Good afternoon, madam. Very nice to see you here.
Yeah. How are you doing?
Fine, madam.
Good. It's nice to see people in conferences and
Yes. Yeah, same here.
so are you going to Calcutta?
No, I am not going. I am afraid of that cold. It will be
Calcutta
very
is
cold
not
now.
that cold.
Reasonably colder.
Yeah, colder than Bangalore.
Yes.
Here it's very cold. Chandigarh is very cold.
Okay. You are going, madam?
No, I am not. Even I am not going.
Okay.
We have to finish our course for the semester exam.
Okay.
So I told Prasananda that I would not be coming. He called me, but I said, no, it will be difficult.
Yeah, this is after 2 years is organized, right?
Yes. I wanted to go, but again, because of winters, flights are very unreliable from Chandigarh.
Okay.
So it's sometimes very stressful. So I told him I'm not coming. But IISA is in Bangalore, so you must be attending that?
No, actually, that day I am not there in Bangalore.
Okay. Okay. I'm not traveling this time.
Okay.
So even Cochin one, my daughter is coming from Hong Kong, so I'm not going.
Okay. ISPS one, right?
Yeah. Hello, Professor Arivarignan. I think I am pronouncing your name correctly.
Don't worry, Pranav. Even in Tamil Nadu, they do not pronounce it correctly. So no problem. We can simply call Ari. That's okay. ARIB. Ari.
Arivarignan.
Arivarignan.
No, I think that sound will never come from us now.
Yes. You can simply use first 4 letters. Arif. That's okay.
Arif, okay. Because I was thinking it's a difficult name.
Even in Tamil Nadu, even Tamilians find it difficult to speak it.
Gunasilan. It's Gunasilan?
Gunasilan father name. Father name.
Yeah.
See, we do not have the family name here. In Tamil Nadu, we have only initial. My father name will be initial. G. Arivaringa.
Okay.
We do not have any family name.
Yes. So you are in Madurai.
Yes.
Meenakshi temple. I visited Madurai long time back. Almost 20 years ago.
Oh, 20 years back.
Yeah. So, how are you, Professor Satish? Busy?
Yeah.
It's, I think, really great on your part that you keep organizing conferences. There is so much work, but really appreciate it.
Thank you, madam. Thank you for your nice words. Professor Gopal is asking you.
Gopal.
Yeah, Professor.
And he gets up very early in the morning. I think sometimes 4:30 you get up.
Before that, you someday.
I have seen 4:30. You send a message. Every day, good morning message he sends. Very nice messages.
Yeah, he is very prompt in all this. And
Yeah,
all his
yes.
all his conferences, hundreds of papers will be there.
Yes, yes.
And even
That is there.
that heavy COVID time, he didn't stop all this.
Yes. That is there. Actually, now we don't feel like traveling to attend conferences. We want that it should be online only. So that's a good thing. Cochin one is offline now, totally offline.
Yeah, it's offline, Cochin offline. ISPS this time ISPS conference holding offline.
I was about to ask them, do you have hybrid mode? Online as well as offline.
Yeah, now in fact, while we are shifting to offline, it's better to in the hybrid mode. Thereafter to offline, if in future. In fact, it is difficult for us to avoid the online business in future. I think so. So you have to depend on online.
I want to come and visit Padamnath temple.
Padmanabhaswamy, yeah, you are most welcome.
So let's see when can I visit.
Professor, for people like me, 71 years, how can I travel all the way?
Yeah,
Online is
traveling
a
now
tool.
seems difficult. So it's good. I think online is good. I missed Professor Balakrishna's lecture in the morning. I had my classes actually. I wanted to attend his lecture. Professor Somesh is also
Good morning, good afternoon.
Afternoon, sir. So we can start in 2-3 minutes.
Kharagpur also very cold, isn't it?
Not very cold, it is cold, but it's okay. Not as in the Punjab.
Okay.
Here it's quite cold now.
Yeah, I had been to Jalandhar last week actually. So
okay. Even Kanpur is very cold.
Yeah, Kanpur is cold. Yeah.
Okay.
Professor Vijay Mishra was here.
On 10th he has to give a lecture. Actually, I was there on 8th. I went to Ropar. I gave a lecture on 8th. On my way back from Jalandhar to Chandigarh airport. So I halted there and gave a lecture.
Good afternoon. Good afternoon, Kanchan ma'am. Satish sir.
बढ़िया आपकी तो सर्दी हो रही है आपकी पहचान
Yeah, it's very cold here in Kashmir.
Yeah.
During the night it is -3, -4, and during the day it's little bit.
Snowfall हो रहा है?
No, yet it has not started, but in the upper regions it has started. Snowfall has started few days back.
श्रीनगर में तो अभी डल तो नहीं अभी वो हुआ ना freeze?
हाँ, डल थोड़ा सा फ्रीज हो गया है, स्टार्ट हो गया है फ्रीजिंग.
Okay.
So we hope you people will visit Kashmir this winter.
विंटर में तो हिम्मत नहीं होती. समर में आएंगे.
Actually, one of my cousins, he has gone to Gulmarg, Sonmarg. He put some photographs there. So they are doing skiing and then on that sledge.
Yeah, in Sonmarg there is actually a regular snowfall from last 1 month.
Yeah. So I saw his photographs. Very good.
Yeah, it's a nice place to be visited in this winter. Winter is very good for this skiing season.
Yeah.
So 1 minute is left with me.
Yeah.
For 1 more minute.
Yeah. Okay, I think
I can see a number of persons online.
Yeah. Where is Neha? Neha.
Sir, I'm here.
Neha, please introduce our chair and please do the needful for further proceedings of the session.
Okay, sir. Warm greetings to all. Now we move on to the fifth technical session. This is a plenary session to be chaired by Professor Kanjan Jain. Dr. Kanjan Jain is a professor of Department of Statistics, Punjab University, Chandigarh. She is an elected member of International Statistical Institute, Netherlands, and the National Academy of Sciences, India. She is also a fellow of the Royal Statistical Society, UK. Professor Jain received Excellence in Research Award by the Indian Association for Reliability and Statistics on the birth centenary of the living legend, Professor C.R. Rao, and was also selected as a distinguished woman researcher in statistics under the science discipline by Venus International Foundation, Chennai. She has a work experience of more than 42 years. Her areas of research include reliability, survival analysis, actuarial statistics, inference, measurement error models, income inequality, and biostatistics. Dr. Jain has published a lot of research papers in reputed journals. Once again, I humbly invite Professor Kanjan Jain to chair the session. Over to you, ma'am.
Thanks, Dr. Neha. Thank you, Dr. Satish. So welcome. I welcome everyone to this session, which is technical session number 5 and plenary session 2. There are two distinguished speakers in this session. First one is Professor Arif. His name is too difficult. Arif Riganan. And he said, you can call me Arif. So I think Professor Arif. And second speaker will be Professor Somesh Kumar from IIT Kharagpur. So I invite Professor Arif Riganan. He is actually a senior professor retired from Madurai Kamaraj University. He worked there since 1990. He received CSIR Emeritus Scientist Award in 2016, also UGC Emeritus Fellowship, and all his research interests are stochastic modeling and applied statistics. He's also a fellow of the Tamil Nadu Academy of Sciences and Royal Society, Statistical Society, UK. So I welcome Professor Arif for his talk on an inventory system with postponed and retrial demands. So welcome, Professor Arif. Please go ahead with your talk.
Sir, you have to unmute. Professor, please unmute the mic. Unmute the mic.
He is muted.
Thanks for correcting. This is the usual mistake I commit at every online meeting. I thank Professor Satish Kumar for inviting me to speak here, and to Professor Kanjan Jain for introducing me. I will. Here we go. Oh my goodness.
Yeah, he's coming. Yeah.
But unfortunately, what happened is, yeah.
Sorry for interrupting.
Yes,
Professor Arif, you have 40 minutes, 35 minutes for your talk and 5 minutes for questions.
Okay.
Thank you.
Now I will make my screen full. Control L. So that I can see only my screen.
Yeah.
It's okay, sir.
Okay.
So if you want to say something, do not raise your hand. You interrupt by audio. Okay, anyone?
Sir, I think you have to maximize your screen again.
Yeah, I will maximize this. Okay. But that what happens is I'm seeing only my screen. That's the problem.
Okay, sir.
What I do is. What about this? Is it okay?
It's okay, Professor. It's fine.
Yes, sir. Yes.
Or okay, I will maximize. This work is with my student Rajkumar, my colleague B. Shivakumar. Both were working in Madurai Kamaraj University. And I want to say at the outset, this is something different from statistics. But though it's on probability and stochastic process, mainstream of the paper presented in this conference is on statistics. What happened? Sorry.
So you can go ahead. It's okay.
Yeah. To avoid infinity error, why?
But here it's okay.
It is okay, Professor. Here we can see the first slide. Whether it is any problem with the moving?
Yeah, not moving. Yes.
Yeah, that you can minimize in that case if it is difficult. Move the full screen.
Maybe using arrows can help.
What about this? Is it not? Is it visible?
Yes, sir.
Yeah.
No.
Visible, Professor. It's visible, but not. Yeah. Now it is full screen.
Yeah.
Now we can move whether it is moving or it is not moving, but the screen changes, size changes.
It's okay.
It's okay, Professor.
Is the table of contents. The only thing is I am seeing my screen, but not the participant. So organizers and the chairperson, please, if you want to interrupt me, do not raise your hand. Just use the audio.
Okay. Thank you, sir.
So this is the table of contents. Now I told you my work is on stochastic process on logistic system. This is something like my logistics system is only inventory system. And whenever a demand occurs, the item will be removed from stock. So the stock is reduced. When there is a supply, it goes up. So this work belongs to stochastic modeling and performance analysis of inventory models. And this is a part of OR and applied probability. For more references, please see the Icstc times Jipkin. The problem becomes very difficult when you specify how do you deal with the demands that occur during stock out. Otherwise, it's simply a queuing problem. Something comes, something goes out, like that. So when there are no items in the stock and demand comes, so you can either forego it, that is total lost sales, or you ask them to wait, and whenever you replenish your stock, you backlog it. That is satisfy their demand. Third option is only partial backlogging. That is not all demands that occur during stock out period are met. Only few, according to some criteria. Now, recently, there are two types of handling demands that occurred during stock out period. Postponed. So the people who are coming and asking for items will be asked to wait in a pool. That is something like a bench, as used to say in software industry. There is a pool, people will be kept there. Another one is a retrial. They will be asked to go out. They will be going out and orbiting somewhere and come back again for their item. So now these orbiting customers will form a second source of demands to the system. First is the usual demand. Berman et al. 1993 introduced the concept of postponed demands. Whereas after Joe in 2006 introduced the retail demands. Please note that a postponed demand means they'll be asked to wait in a pool. They are the priority. But when they go out, they are asked to retail means they are not considered in the system. They are outside the system. Whenever they come back and ask for a new item, it may be considered according to availability. So the postponed demands is considered by Krishnamurthy and Islam in 2004, Shivakumar and myself 2008, Val Manuel and myself 2007, Shivakumar and myself in 2009. We considered the pool with the different assumptions. One is customers are selected from the pool by an exponential distributed log. Another one is demands are occurring according to Markov-Harville process. I will come back to it later. First step. So this is quite general structure. The third one is positive and negative demands. Positive demand means they come and ask for an item. Negative demand means they discourage existing customers. So the item will not be removed. Actually, the waiting customer will be removed. So, in the case of retail demands, Usha Kumari 2006 considered a retail inventory system, Shivakumar 2008, Paul Marvel and myself in 2008, and Shivakumar 2009, they considered a perishable inventory, it's a new item with a retail demand. So, I simply give an illustrative picture about my model. Then I will go to the other assumption that makes the problem very difficult. The left side, the y-axis indicates the level. Initially, the level is capital S. Whenever demand comes, one item is removed from the stock, so that is given to a demanding customer, so level goes down. So at a particular level, we call small s, we call a reorder level at the time. We place a replenishment order, that is, it is going on down, it becomes zero at some time, so you will not be able to meet the demands after when it reaches to zero. So to prevent that thing, and we place an order at this level, and note that this is a lead time that is random. So it may come immediately or some little later. When it comes, it goes to some level. I made a mistake of drawing here as going to capital S. It's not so. During the stock out period, when a demand comes, that is, sorry, this is inevitable becomes zero. This is the replenishment point. In between, no items in the stock, we call stock out. When a demand comes, with the probability P, they are asked to go and sit in a pool. With the probability Q, that is 1 minus P, they are sent out to an orbit. They can come back at a later time point according to some probability law. So, as you've seen here, the postponed and data are combined together in this paper. What is the example? In a retail store, some customers register the demands and are willing to receive their items at a later time point. They may not be sitting in the bench, but they register, we will be informed with them later. Whereas some other customers leave the system and try later. This is the case of orbit, this is a pool. Now the point is, there are demand points, retail is initiated, and customers are sent to pool and orbit, and we may select the items, we may select the customer from pool only when the stock is above small s. But whereas the orbit people, whenever they come, they will be treated with regular customers. Therefore, they will be considered for disbursement if there is an item. But if the items are more than smallest, then only we consider selecting customers from the pool. So it's going to involve many processes. One is the regular process, and customers are selected from pool, customers are retried from orbit, and so on. So there are many process and distribution are working on. Their pooled time points will be a confused state of stochastic process that we are going to make a system assumptions, and we want to have Markovian property. So with that, we are going to model it. So before that, I want to say what is space type. Just consider a exponential random variable. We write the density is lambda in t per lambda x. It can be approached or defined in many ways, but for our work, I would consider a one state absorbing process. The process initially at 1, after some time x, it reaches 0. Now it got absorbed. Now think of the case taking the process to state 1, redo it again, restart it, reset the system. So whenever an absorption occurs, that will have a exponential distribution. And whenever the absorption occurs, a new initiation is considered. So there is a count number 1, count number 2, 3. So this is a very simple idea of looking at the exponential distribution as a time taken to get absorbed in one single state. So this idea is expanded. Think of two phases at the state, two phases for our later discussion. Initially, a process is at 2. After some exponential time, it moves to 1. Then after exponential time, it goes to 0. It got absorbed. So for every 2 transition, it gets absorption. Of course, we will reset it to 2 again. So this is absorption. This is home state walk-up process. Now I'll show you. For this, there will be 2, 1, 0. I don't want to. I didn't say here. This is only 2 states, but actually 3 states will be there. 0 will be absorbing state. Now that is I am giving an exercise here. At time 2, phase 2, phase 1, phase 0. So it moves from 2 to 1, 2 to 0, 1 to 1 got 1 to 0. It got absorbed. So this is a 2-state absorbing process, and I partition in such a way that the last row is 0. When you have one row is full of 0, that row is an absorbing state. Now, this square matrix is given by T. This column vector is T0. So by writing alpha, I will say start at 2, not at 1, not at 0. This can be relaxed. So with this, we can write down the density function T0, 0, 0. Let us say there is a R by R, because here I considered a 3 by 3. You can consider R by R matrix. This is a square matrix. You are starting at R at 1, R at 0. This is the extension R I may consider. So the idea is you can start from anywhere. You are moving to this one or any state that is given by T. When it goes to 0, it got absorbed. As usual, you restart it to some state. Further, the probability is given here. So the phase step process is defined by this. Now, if you take r equal to 1, then you get back to exponential. This can be extended to having two matrices. This is T, this is T0, that is this one. By this way, I got two square matrices. The ijth entry will give you a flow of rate from I to j when an arrival takes place. D suffix 0 means there's no arrival. So this is a generalization of your exponential process to have more phases that's happening behind the scene. So the abstract is this, and I don't want to repeat here again. I will come back to it. So the maximum inventory is capital S. Unit demands occur according to map, Markov and arrival process. I told you that it's a matrix, square matrix. This is another square matrix. When you add these D0 and D1, you will get a D matrix, that is the rate matrix for a absorbing Markov process. Now D0, ijth entry will be giving you the rate of flow from phase I to phase J. Here also phase I to phase J. But the only thing is here, this is associated with the arrival. This is not associated with the arrival. That is the only thing. So this is a quite generalization of the exponential process. Now we are assuming that the demands are occurring according to Markov arrival process, MAP. Then the ordering policy is smallest capital. I told you at smallest you place an order. The difference capital S minus S is the order in quantity. Article is Q. The time taken to deliver the ordered item is called lead time. I call the phase time. This is the initial probability. This is the square matrix I showed previously. This one. This says transition among states, and only when transition to this last row, the absorption occurs. So that time the demand or the lead time takes place. So this is this indicated by this symbol. I'm not giving full details. The only thing is alpha is the initial transition, initial probability. You started again. T is the transition among states. What about the absorption that is given by T0? T0, that is from I to last state, last row, 0. That can be always obtained by just adding total sum is equal to 0 for a rate matrix of a Markov process. So when I specify T0 is immediately obtained. Yes. Initial probability and transition probabilities. When you make a summation to make it 0, you get another vector T0, that is the probability for absorption. Now, the demands that occur during stockout period enter either a pool of finite size, I would keep it as M, or an orbit of infinite size with the probability P and Q respectively. So the demands of the pool are selected one by one, provided if there is sufficient stock, and the time between two selections is exponential, and that parameter depends upon the number of items in the pool. The orbiting demand that goes outside and I attempt again, the time between two successive attempts are distributed as exponential with the parameter theta. In addition to this, the items may perish. The lifetime of a unit is exponentially distributed. It's perishable with the constant failure rate gamma. So there are so many processes are working on it. So at any time point, there may be a demand from outsource, that is according to workover and process from orbit, or maybe selecting from a pool, and there is a lead time or item may perish and so on. So I am going to denote this by x2 of t, number of customers in the orbit. I have taken this first, initially the second state, but later I noticed that this can take value 0, 1, 2, 3 up to infinity. The next level is next process L of t, that is short for inventory level. It can take value 0, 1 to capital S. X1 of t, number of customers in the pool. I am going to have a finite pool, so 0, 1 to n. J1 of t, the phase of the arrival process. I told you that the MAP, Markov arrival process, will have a hidden or some sort of some Markov process, and according to that Markov process, process is going on. Only at some point the arrival comes, at some point no arrival. J2 of t, the phase of the lead time. The lead time is again, as long as it is going on a transition from within 0 to M2, when it goes to this 0 is missing, yes, missing. 0, actually the phase are only 1, 2, 3, M2. When it goes to 0, it got observed, immediately it comes back to any one other state. So there's no need to specify 0. But this particular variable will come only when the inventory level is below S, otherwise it won't come. So 1, 2, 3, 4, 5 processes are going on, and sometimes only 4th process. So the state space is this. I1 represents the number of customers in the orbit, that is 0, 1, 2, 3. L of inventory level 0 to small s, here S plus 1 to capital S, because when inventory is S plus 1 to capital S, you won't have the lead time. So X1 of t, the customers in the pool, J1 of t, the phase of the arrival process, J2 of t, phase of the lead time process. So the state space is given here. So I am going to consider here 1, 2, 3, 5 process, markup process, 5 component, 5 a vector process, I simply call it Z of t. The red matrix has to be written. So I am going to write like this. Why? First, the left one is 0, 1, 2, 3, top 0, 1, 2, 3. It state from state I to I, it will remain. No arrival. When there is arrival, I goes to I plus 1. When demand is given to the customer, he leaves the system. So from I to I minus 1, I could have write here, if you think of this particular place, this is a I. When new customer comes, the inventory X2 or T goes to I plus 1. When the item is given to him, he leaves it. So this is only a tridiagonal structure. Now, there are another 4 components have to be taken care of. So I am going to consider, yes, submatrices. So any entry here will have another submatrix of level 0 to capital S, that is S plus 1 rows, S plus 1 columns. Any entry here will have another submatrix 0 to n. What is n? N is the number of the size of the pool. Again, any particular entry here will have either this form or this form. This is actually the arrivals. Sorry, for any item, any entry here, I have another submatrix. It is says m plus 1 to m plus 1. This represents the phase of arrivals. Then for any entry here, there is another submatrix. So you can think of a matrices, submatrices, and so on. And this submatrix will arise only when inventory level is less than or equal to S. Therefore, here you can think of this area 0 to small s. For that, this will not occur. For the remaining area, this both will occur. Now, it may look very difficult, but with the practice and using certain simplified assumption of the exponential Markovian property, I can write this. So this one says that from 0 to this, a transition occurs. Customer in the orbit 0. This means customer in the orbit is going to 1. So here it takes only a 0 level in the inventory, and otherwise this will go back to this. So only at inventory 0. Then when you consider this particular submatrix, it has a main diagonal element and lower diagonal element. So this can be written with a simple trick about it. D1 is the matrix explaining the transition among the Markov arrival process. Here the same thing, but the only thing is when they are equal, that is, this goes to the Q is asking it to join the orbit. So this is a simple structure, and you can write about all the other matrices. They have done this. So the matrix A0 I written here, and A2 means, what is A2? This is this one. There is any I2, I minus 1. 2 means, this 1 means goes to 0. This represents going from 2 to 1. So A2 is the number of customers in the orbit is going down. Sorry, that one, this one, yes. So at that case, the inventory level will go down, because when we are moving from customer is leaving from the orbit, it means he gets around items, the inventory level is reduced. And when I write this, there's a very simple thing is, already one transition has occurred. Please note that this is a very important property of Markovian process. So this I matrix, because no change should be there in any other process. Using this, I can write this, and I list all this. Okay. Now here afterwards, I'm going to consider only the rat matrix. I'm going to call P. This. So my process has 5 components. T greater than or equal to 0. No. In order that the Markovian process with rate matrix P, that is, I have already given tridiagonal matrix, it has a limited distribution, limit probability that Z of T equal to a vector Z, given that Z0 initially it has a level Z0. This is a vector. This is a vector process. So this limit is divided by 5. We are going to find out this, and we are not going to actually compute it. We are going to give a algorithmic solution. So first thing is, I want to have a irreducibility. A Markov chain must be irreducible. Now, if you look at this process, look at the thing, from any state, there is a 5-component process. For any one, you can reach any other 5-component, because this is a physically realizable inventory model. So every state reached by from another state. So it is irreducible. That we can verify in another way also. But I want to, for the discussion purpose, I'm saying this. So we can verify that the Markov process under study is irreducible. Another point is, look at the P matrix. It's a tridiagonal. Suppose this I throw, it will lift, it is drifted to the right hand side or left hand side. So this is an observation you can make here. So if you are going to make more right-hand side of the drift, then you'll be going towards infinity. So your process will not be stable. So the simple idea is the drift towards left must be greater than drift towards right. So for that I use this trick. Actually, this proved by Newt's, but for discussion purpose, you consider a matrix A, that is A2 plus A1 plus A0. This happens to be a red matrix of some other process, some suitable Markov process. I call A, then I find the invariant measure or Stationary distribution of A, that is I call phi. The interpretation for a stationary distribution is phi of z gives that fraction of time the process visits state 0. Whatever the state you give here, it gives the fraction of time. So if you drift to left side, that is given a phi a to e. The left side drift is given by phi. This is the stationary distribution of A that tells you what is the fraction of time you reach any state. You multiply with the A2, that gives you particular state of this level. Then you make a sum. So this gives you the total drift towards left. This gives you total drift to the right. So it should be greater than. If you make this assumption, then the process will not go down, it will be always going up. This idea is proved by Newt's. So that the result is Newt's work 1984, this algorithmic numerical analysis of matrix geometry method. You can easily check the book. It is very quite famous. It appeared in 1984. You can always easily find the reference in when you Google it. So now let us come to the point. I am making a sum A0, A1, A2 is A, and the matrix I already given. So that is written here. So I want to compute the phi A. This is the invariant measure. So this vector of 5 components, I am going to suitably partition.
Professor
So
Arif, sorry
yes,
to interrupt you. Please sum up.
Okay, sure. So with this, now I am giving an algorithmic solution procedure for my process. The phi is given by phi q index of phi q. The phi q can be found with this equation. Then I told you about this matrix, this condition. This given by 1984 is the first edition, 94 is the second edition. Here it has been proved, but I gave you a justification for that. So you see this, I get this. This actually reduces to lambda by less than mu in the M1 cube. Now, the limited distribution I'm going to find out using these are various derivations. I do not want to discuss now here. The only thing is I am giving the main result. The phi j, that is the j equal to 0 to the customer in the orbit, it is expressed in terms of phi 0 rj. R is a matrix, square matrix, and please note that this analogous to your M1Q, that you have got pi j equal to pi 0 into a power j. A is a constant here, matrix. That matrix is a solution of this, and using this equation you can find out. Now I have to prove the existence of this inverse and how to compute R. Because at no stage I have given explicit result, so I need to prove or does these two issues. That's what we do here. The first observation is the R is having a structure of A0. Already I told you A0 has only few non-zero rows. Therefore, R matrix will have only few non-zero rows, others are 0 rows. So using this iterative way, you can compute using MATLAB or using Python, you can compute this. So finally, the structure is like this, and I am going to everything depends upon I r suffix 0 power inverse. So the whole thing reduces to a few vertices. We compute the system performance measure. No, I am not going to compute it because I am giving algorithm solution for phi, and later I construct the total expected cost rate with some suitable cost, and I am not giving any numerical result here because this it takes a lot of time. So I am going to consider only minimal result. Okay, and now this problem is involving 5 component. Of course, there are other problems. We have considered even go to 7 component vector pieces, and then the whole thing is algorithmic. You can't get a finite complete solution. It is computationally you can get the solution. We are giving algorithms. That's all we can achieve in this type of problems. I stop now.
Thank you, Professor Arif.
Okay, thank
Any
you, sir.
quick questions? Your talk was quite interesting.
Thank you, bro.
Any questions from the audience? I think no questions. So they can get in touch with you later?
Yes, madam. Thank you. That's a good idea.
Yes.
We do not have much time. So they can easily search my name in the Google, get my email ID because my name is unique. So even Tamil Nadu or India, I am the only person. You can always find my email ID. They can contact me.
Thank you, Professor. So our next speaker is Professor Somesh. Dr. Somesh Kumar is a professor at Department of Mathematics, IIT Kharagpur. His research interests are statistical decision theory and inference, methods for directional data, combinatorial designs, quantum information and computation, and classification procedures. He has total research experience of 37 years, a number of papers in refereed journals 97, book chapters and conference proceedings 16, and he has presented almost 90 papers in conferences. He has developed 4 courses under NAPTEL project of MHRD and also developed modules in engineering mathematics. So he has guided 11 PhD students, visited a number of other institutes outside India, and is also on the editorial board of some journals. So over to Professor Somesh. He will be talking on bootstrap likelihood ratio test for two-way crossed ANOVA.
First of all, thank you, Professor Jain, for introducing me. And I thank Professor Satish Kumar for inviting me to deliver a lecture in this international conference. I have seen it is a very full, like you have people from Kashmir to Kanyakumari and from east to west, and also from various other countries. It's a huge conference and it requires a lot of effort. So thank you, Professor. And let me share my screen.
So Professor Somesh, you have 40 minutes, 35 minutes, I should say.
Sure. Okay. So I will be speaking on the two-way crossed ANOVA. So we have developed actually bootstrap likelihood ratio test for this. Let me just ask whether you can see my screen properly.
Yes.
Yeah.
Okay, so this is actually the work of my research scholar, Anjana Mandal, and we have a collaborator also from TU Dartmouth University, Paavo Sattler. So let me, we will talk about the test and So the likelihood ratio test involves finding out the maximum likelihood estimators under the null parameter space as well as under the full parameter space. So we have developed algorithms for obtaining these things. And in order to implement the test, we have prepared a parametric bootstrap algorithm. So I will talk about that. We have also proved that this parametric bootstrap is actually asymptotically accurate. So that's a theoretical proof. And then we have carried out a simulation study to study the size and power performance of this parametric bootstrap likelihood ratio test. We have also looked at the robustness property of this test. That means if we are looking at the non-normal distributions, then what happens to the performance of the test. And finally, we have implemented numerically on 2 data sets. The data sets we have considered on our own. So let us consider a two-way cross design with alpha levels of factor A and B levels of factor B. So suppose I consider the observations in the form Xijk. So the model then we can describe. So here in the ijth cell, we have Nij number of observations. So we have I is equal to 1 to A and J is equal to 1 to B, and then the number of observations is Nij. So we have K from 1 to Nij. So the model can be then described as Xijk is equal to mu plus alpha I plus beta j. And then we introduce the interaction factor, that is alpha beta ij. Sometimes it is written as gamma ij in standard textbooks, etc. And then the error term, that epsilon ijk. So mu is the general effect. Alpha I is the effect due to the ith level of factor A. Beta j is the effect due to the jth level of factor B, and alpha beta ij is an effect due to the interaction of the level I of factor A and the level j of factor B. So we assume here that the errors are independent normal 0 sigma ij square random variables. So we have considered in general that sigma ij squares are completely unknown. That means in general they may be unequal, and of course equal variances will be a special case. Now you can look at this. This is a complete heteroscedastic case here. So here cell variances themselves may be different. We have the standard estimability conditions like sigma alpha is 0, sigma beta j is 0, and sigma alpha beta ij is 0, and sigma alpha beta ij over j is also equal to 0. Now, of course, testing for the homogeneity of row and column effects is widely used in experimental studies in engineering, biology, agriculture, social sciences, clinical trials, etc. And historically, the classical F test is used for testing equality of main effects against their natural alternatives. So that means we test that whether alpha i's are all equal against that whether at least one of the alpha i's is not equal. We test whether all beta j's are equal against whether beta j's at least one inequality among the beta j's, and similarly about the effect of the interactions also. So classical F test is available. We do that thing. However, this it has been observed that the test is actually not robust under heteroscedastic variances. So there are several studies. I have just listed few of them. For example, Zhang and in 2012, Zhu et al. In 2013-15, Pauli et al. In 2015, Batke et al. In 2018, Sattler and Pauli in 2018, Naguchi et al. In 2021. So they have actually shown that this classical F test is not robust, and then they have proposed alternative tests for this problem. However, I mean, there are many real-life experiments in the two-way interaction model where heterogeneity of the cell variances is actually present. Now, for example, if we study the effect of gender and physical activity on the blood cholesterol levels, similarly, if we study surveying the growth of crops on different type of crops and fertilizers. So there are some references. I have just mentioned one of them. For example, Benjamin in 2003, they have mentioned certain examples. So Ananda and Veerahandi in 1997, they have proposed a generalized F test. We call it GFT for testing the homogeneity of main effects in the presence of interaction in a heteroscedastic two-way ANOVA model. And they have further extended this test for testing hypothesis of the type alpha I plus alpha beta ij is equal to 0 for all ij. Then Bao and Ananda, they have considered the in presence of interaction effects, they have compared the classical F test and the generalized F test using simulations. And their study shows that GFT actually performs better than CFT. Actually, whenever the heteroscedastic variances are there, the classical F test becomes very liberal, and therefore it becomes unreliable in terms of power performance. Although we have seen that both the tests are robust when we deviate from the normality. However, the GFT is actually complicated and time consuming to implement. Then Zhang has proposed an approximate degrees of freedom test. And here the distribution of the test statistic is actually approximated by an F distribution, where the degrees of freedom of the denominator needs to be estimated from the given data. In a two-way ANOVA model with interaction effects, when the number of rows and column factors are large, and that means the levels are high, then the Wang and Akritas, actually they have proposed some asymptotic tests for testing equality of main effects and interaction effects against their natural alternatives. These tests are observed to be robust under non-normality and heteroscedasticity. Zhu et al., they have pointed out that the size values of the generalized F test are much higher than the nominal size values when the number of levels of row and column factors are assumed to be large. And they actually proposed a parametric bootstrap procedure for testing hypothesis of homogeneity of main effects as well as the interaction effects. In fact, their tests are seen to perform satisfactory for arbitrary number of levels. And when interaction effects are seen to be present, they considered testing alpha I plus alpha beta ij is equal to 0 instead of the standard alpha i's are all equal. So these are all actually testing the homogeneity of main effects against the natural alternatives. But there are many practical applications when we have prior information that either homogeneity is there or there may be ordering among the treatments. And there are such examples where we have dose response experiments in biomedical experiments, and several other experiments are there in agriculture, engineering, equipment, manufacturing process, etc. So I have put some references here. Boyd, Rome et al., Ruberg, they have given such examples. For example, if you consider engineering design of an engineering equipment, so at each successive stage of the design modification, the quality or the efficiency or the performance actually improves. So therefore, the natural alternative will be like θ1 less than or equal to θ2 less than or equal to θ3, etc. So actually, if we utilize the ordering information, we can actually develop more efficient test procedures. There are actually interaction models. So one model is like one-way model where you have ordering, but even in the two-way model when we have interaction, there also actually ordering has been observed. So if we consider a new drug for a disease, then the dose response trials are conducted where we determine the exact dosage of the drug for patients of various age groups. And here the amount of drug and the age groups actually it is present there. And therefore, we have to see that in the presence of the interaction effect, whether the increased doses of the drug, they increase the rate of cure. So there is some reference I have put here. Similarly, if we study the effect of different nutritional values of soil on yields of various crops, then you can see that between different variety of crops and nutritional value of soils, there is an interaction factor. So there is some reference here. Now the problem of testing against ordered alternatives in one-way ANOVA model was first studied by Bartholomew in 1959. And Sharrock in 1967, he extended this test to two-way models without interaction and with homogeneous error variance and one observation per cell. So he actually developed the likelihood ratio test for testing homogeneity of effects against alternative hypothesis that alpha is follow an ordering. And he also developed LRT when alternative hypothesis natural one, and that is at least one inequality. And non-parametric tests were also proposed by him for both types of alternative hypotheses. Recently, Mandal et al. Have proposed likelihood ratio test and another test based on pairwise comparison for testing equality of treatment effects against alternatives in one-way ANOVA model with heteroscedastic error variance. And these tests are actually seen to be robust under the departure from normality. Then Caligari and Aketas, they have considered a two-way ANOVA model with interaction in a complete non-parametric setting. And the main and interaction effects have been defined in terms of averaging of cumulative distribution functions. And they have proposed rank-based tests. And they have considered trend and umbrella alternatives. Then Zhu et al. In 2013, they have pointed out that in the presence of interaction between factors A and B, the main effect alpha E does not truly represent the effect of ith level of factor A. So this is due to the fact that the ith level of factor A also depends on the level of factor B which contains this. So they considered the hypothesis H0 alpha I plus alpha beta ij is equal to 0 for I is equal to 1 to A and j is equal to 1 to B against the natural alternative of at least one inequality. So if you look at this 1.2, we were actually considering this, that if we put ordering here, then how we will get this. So motivated by this, we have considered testing the above null hypothesis against the alternative of the trends, that is alpha 1 plus alpha beta 1j less than or equal to alpha 2 plus alpha beta 2j less than or equal to alpha a plus alpha beta aj, and j is equal to 1 to b. So there are b number of hypotheses here, and with at least one strict inequality for each j. Now we note that there are no existing studies in a parametric setup for testing against trend in a two-way ANOVA model with interactions and heteroscedastic variances and unbalanced sample sizes in the cells. So this is so here we provide a systematic approach to utilize the ordering information in developing LRT and tests based on multiple comparisons. And an important part is developing algorithms for evaluations of MLEs under null and full parameter spaces, as I mentioned at the beginning. So we have this H0 and H1 here. This is H0 and this is H1. And we will consider the likelihood ratio test. So let us look at the null and the full parameter space here. So if we define mu ij is equal to mu plus alpha I plus alpha beta ij, then we define the xi naught vector as mu beta 1, beta 2, beta b, sigma 1, 1 square, sigma 1, 2 square, sigma ab square. Of course, since we are putting it as a row vector, so actual vector is represented as a column vector, so we put a transpose there. And xi is consisting of all the terms, that is nu 1, 1, nu 1, 2, nu ab, beta 1, beta 2, beta b, sigma 1, 1 square, sigma 1, 2 square, sigma ab square, and so on. And the parameter space under the null hypothesis for model 1.1, so that is given by xi naught beta j belongs to R, sigma ij square is positive for all I and j. And the full parameter space for this model, that is nu 1j less than or equal to nu 2j less than or equal to nu aj, beta j's are reals, and sigma ij squares are positive. So what is our aim? We have to find out the maximum likelihood estimators of all the parameters under omega naught as well as under omega. So firstly, let us look at this problem. So maximum likelihood estimators under omega naught, when we have to consider, we develop an algorithm. Let us look at this. So let us call beta j prime as mu plus beta j. And then we observe that under H naught, xijk follows normal beta j prime sigma ij square. So if we define uij as nij divided by sigma ij square, yij as the mean of xijk, that is the cell means, and qij as what the means of the sum of squares of the ijth cell. So we can reduce the likelihood equations as summation uij yij minus beta j prime is equal to 0, j is equal to 1 to b, and sigma ij square is equal to qij minus twice yij beta j prime plus beta j prime square. Now substituting the expressions of sigma ij square in 3.1, we get the following equations. So these equations we consider as equations in beta 1 prime, beta 2 prime, beta b prime, which is written as this sum of certain rational functions. So basically this becomes that each of these above equations become odd degree polynomial equations in beta j prime. So that means each of them has at least one real root of beta j prime. And if there exists more than one real root of beta j prime, we take the values of beta j prime as MLE which maximizes product of sigma ij square for j is equal to 1 to b. The corresponding value of sigma ij square, which is calculated from equation 3.2, yields the MLE of sigma ij square. This method is complicated to implement for higher values of a and b because so many equations you have to solve for higher degree of polynomials. So what we do, we propose an iterative approach to find the MLEs in this particular case, that is under omega naught. So the algorithmic procedure is given in this particular fashion. So we define yj bar as the means of yij's and sij squares the variances of the cells. And then we choose the initial values as beta prime 0, I write as beta 1 prime 0, beta 2 prime 0, etc. That is the means of this y1 bar, y2 bar, yb bar, etc. And similarly, we take the cell variances as the initial estimate of the sigma square vector. So that is S11 square, S12 square, SAB square. Now using this representation for uij n minus 1, we consider the nth iterative point from beta prime as, so we call it beta prime n, and these are the components. So beta j prime n is sigma uij n minus 1 yij divided by, so this becomes a weighted mean of the yij's here. Now the nth iterative point of sigma square is then given by sigma 11 square n, sigma 12 square n, and so on, where we have replaced this yij by this beta j prime n square here. So that becomes the next iteration for sigma square. And we will stop at the nth iteration if the maximum difference between this beta j prime n minus 1 to beta j prime n, it is less than or equal to certain level of accuracy. Like if I say I want level of accuracy up to 3 decimal points, 4 decimal points, and so on. So we put here m. So basically you can consider this as an extension of the standard Gauss-Seidel iterative procedure. And we have actually shown that by certain argument that the sequence of solutions actually converges. So as the family of distributions is regular, the solutions actually will yield the MLEs of beta prime and sigma square, because we are dealing with a family of distribution that is the normal distributions which satisfy all the regularity conditions. Now we consider the maximum likelihood estimators under the full parameter space. Now if we consider the ordering here, then this problem becomes difficult. She in 1994, he has proposed an iterative procedure and also proved its convergence for finding the MLEs of the means and variances of m normal populations when they are ordered. And then similarly, Shi and Jiang in 1998, they have given an algorithm for deriving the MLEs of the parameters when the means of m normal populations are given to be ordered. However, there are no studies on the MLEs of parameters in two-way cross model under order restrictions on the treatment effects. So again, we develop another iterative procedure to evaluate the MLEs of the parameters under the full parameter space. So we also show that under some conditions, the procedure actually leads to the true MLEs. So we have this as the likelihood function, and now we have to find the solution subject to nu1 1 less than or equal to nu2 1 less than or equal to nu a1, nu1 2 less than or equal to nu2 2 less than or equal to nu a2, and so on, where sigma beta j's are taken to be 0. Now when beta j primes, beta j's and sigma ij squares are taken to be known, then the maximization of the likelihood function is equivalent to the minimization of L star, where I define this L star subject to these conditions. Here we can consider C, because here we are having log of this thing. So we put this particular term where L star we write as summation of Lj star. So we can actually minimize each of them. Here we take each term Lj star and we minimize that. So now if we consider this inside quantity, that is Lj star, this we can write as the sum of these two square terms here. Now the problem again becomes because here in the first case I am taking sigma ji square to be known, then this particular term is fixed. So I am looking at this particular term. So if you look at this particular term, this can be represented as sigma uij vij nu ij minus yij minus beta j square, subject to the order restrictions. So if we define certain quantities like nu dot j vector, xj prime vector, and wj vector, then this is nothing but the isotonic regression of xj prime omega j for each j. So there is a method of giving the isotonic regression here that is called the pool adjacent violators algorithm, which is proposed by Barlow et al. So we can actually implement that on this. So that means when beta j's and sigma j square are known for each j, the MLEs of nu I dot j's, that is nothing but the isotonic regression of xj prime omega j. So now what we do, we find the MLEs of beta j's as functions of sigma ij squares and nu ij. So again, it's an iterative procedure. So now using this, again, we write the log likelihood function as this particular term. So here you can look at this particular. Here this beta j's are not appearing, here beta j's are appearing, and here summation beta j term is coming here. So if we consider the likelihood function del L by del beta j is equal to 0, the equation becomes this particular one, which we can represent in the matrix form by defining the matrix Q as the diagonal u dot 1 up to u dot b minus 1 plus 1 b minus 1, 1 b minus 1 transpose u dot b, where 1 b minus 1 is a b minus 1 dimensional vector containing only ones. So if we define beta tilde is equal to beta 1, beta 2, beta b minus 1, nu is equal to nu 1, nu 2, nu b minus 1, and nu j is equal to this, then we can represent the system of equations, this 4.5, as a q beta tilde is equal to v. And therefore, the solution can be obtained as beta tilde is equal to q inverse v. And the likelihood equation then del L by del sigma ij square is equal to 0. This gives the MLE of sigma j square. So therefore, what we have done, again, we have got it in an iterative procedure. So first of all, we have proved that under the restrictions 4. And 4.3, the MLEs of the parameters exist. So that is proved in this theorem. I am not presenting the proof here. The MLEs of the parameters exist with probability 1 under the constants 4.2 and 4.3. That proof we have done, but I am skipping the proof here. Now then, second question comes that the finding a sufficient condition for the uniqueness of the MLEs of the parameters. We have certain notations here, and these notations are given in the terms of A1j, the nu dot j 1 head. Okay, so I will not read each of these things. We have the following theorem here. For I is equal to 1 to a, j is equal to 1 to b, if Sij square is greater than the maximum of these two terms, then the MLEs uniquely exist. And also under the condition 4.7, nu head beta head sigma head square is the MLE of nu beta sigma square if and only if nu head belongs to A tilde, that is this set, beta head belongs to B tilde head, that is this set, and sigma head squares are positive. And the likelihood function L nu head beta head sigma head square, that is the maximization of this particular quantity. This condition is of course not a necessary condition, and there may be some weaker conditions also under which this may hold, but that is an open problem that we can mention here. Based on the above description of the procedures and the theorems 1 and 2, we propose the iterative procedure for finding the MLEs of the parameters under omega. So this is a thing like we firstly choose the initial values of nu ij's, beta j's, and sigma ij square, and then using that we obtain the next iteration of nu dot j at the nth level by using the isotonic regression of xj with the weights wj n minus 1. And then using that we derive the nth iteration of beta tilde, which is obtained as a solution of this q n minus 1 inverse nu n. And then using this we find the next solution for the sigma ij square. So we have a stopping rule here. And then again we establish that the sequence of points, this one actually converges to the true MLEs uniquely under the condition 4.7, which is given in this particular theorem. So after settling this issue of deriving the maximum likelihood estimators using the under omega naught and omega, we are now ready for the likelihood ratio test. So the likelihood ratio test statistic turns out to be the product of sigma ij square omega head divided by sigma ij square omega naught head to the power nij divided by 2. So these are the maximum likelihood estimators which I just now mentioned here. And the likelihood ratio test will reject H naught if lambda is less than the critical point that will come, which is basically the alpha quantile of lambda under H naught. since the distribution of this cannot be determined in a closed form, we use a parametric bootstrap procedure. So for parametric bootstrap procedure, we generate the samples Xij from the original distribution, that is normal 0 sigma ij squares, and then the bootstrap samples are generated from normal 0 Sij square, and we calculate the parametric bootstrap likelihood ratio test statistic in this particular fashion. Now, after calculating this, we arrange them in the increasing order, and we consider the alpha quantile here, that is the lambda alpha h. This is the critical point which is calculated using this bootstrap procedure. Then Pauli et al., Konishke et al., etc., they have shown that this respective permutation and the bootstrap statistics, they converge to the null distribution of the corresponding statistic. So we also show here that the bootstrap procedure here is valid. That means the conditional distribution of the bootstrap statistic lambda star given the sample approximates the null distribution of lambda as the sample sizes increases. So this is stated in the following theorem, that if lambda star given x is the conditional distribution function of lambda star given the observations, and lambda f lambda h denotes the null distribution of the lambda, then the maximum distance between the distribution functions goes to 0 as minimum of Nij tends to infinity. Since time is short, I will not be reading the proof of the theorem, but of course it involves several steps. We have made use of the concept of Kullback-Leibler divergence, and using that we are actually able to prove this one. So I am skipping the steps of the proof here, but however we have observed that validity using the size and the power calculations. So we have done an extensive simulation study for assessing the performance of the proposed test, and we take several combinations of the sample sizes and the parameter configurations. So we use a two-step simulation scheme to estimate the size and power values. The method is as follows. So given sample sizes n11 and so on, the parameter values, we generate samples xijk from normal mu ij sigma ij square, and we generate this something like say 5,000 times. We calculate the test statistic values and the corresponding critical values for each generation, and then the critical values of the tests are estimated using the bootstrap procedure which we described just now, and then the power and the size values are estimated as the proportion of the times the null hypothesis is rejected. In case of the likelihood ratio test, the number of times the test statistic values are less than the critical value. For size calculation, the new ij's are taken to be 0, and for the power calculations, new ij's are taken to be ordered. We have chosen several combinations of sample sizes and the parameter configurations. We have chosen like very small, small and highly unbalanced sample sizes, high variances, small samples with large variances, etc. We have considered moderate, unbalanced, equal sample sizes, etc. And variances are small, large, and so on. So that means all types of combinations are taken to show the validity of our test procedures. And so let me read out the outcomes here. Of course, you can see from here, like few values you can see. So these are the simulated sizes. If I have taken the nominal size to be 0.05, so here you can see like 0.041, 0.052, 0.045, 0.045, and so on, 0.052, and so on. So taking into account the simulation error, you can observe that these tests are behaving almost as exact tests. Like here also you can see for different settings like 0.048, 0.050, 0.0544, 0.057, 0.053, and so on. So for various settings, we have actually carried out the size estimation. So we conclude that the likelihood ratio test, when implemented using a parametric bootstrap procedure, behaves almost as an exact test. Like you can see here, 0.0507. So these are all almost. So now you see, we have then carried out the power studies, and we have again chosen the configurations in such a way that as C increases, the difference between the hypothesis, the alternative hypothesis points increases. That means you can see the effect of test in discriminating the effects as the differences increase. And here you can see easily, like the first one, C is equal to 0 corresponds to the size. And if we take C is equal to 1, 1.5, and so on, immediately you can see that the power values becomes very good. In fact, just after some time, it becomes 1. Basically, it means that the discriminatory power of the test is very good. So you can see here also in all the cases. So I have taken large number of configurations of the sample sizes, of the variances, and of the effects. So for all the configurations, we can observe that the test function behaves very well. Then the next one is we have also looked at the robustness of the test, whether the likelihood ratio test is robust. As I mentioned that in one of the studies that Mandal et al. In 2022, where we have considered one-way analysis of Mandal, and we have implemented the likelihood ratio test using the parametric bootstrap, we observed that this test is extremely, very, very robust actually. So we wanted to study here also. So we have chosen non-normal distribution, negatively skewed exponential, and rectangular distributions. So for all these things, I will just mention what distributions we have considered. We have taken a T distribution with the degrees of freedom 3, Laplace or double exponential distribution, a Weibull distribution with shape parameter 2 and scale parameter 1, a gamma distribution, exponential distribution with location 0 and scale 1, and a log normal distribution. So then we calculated the size and power values of these tests for considering all these non-normal distributions. The generation of the sample is similar. Only thing is that the initial sample is generated from the non-normal random variables, and then we standardize so that we can compare with the powers of the normal distribution, because we have to keep the same mu ij's. The configuration should be same for the purpose of the comparison. That means same mean mu ij and variance sigma ij square for each distribution. And again, we have calculated all these things. You can look at the simulated sizes here. So for like T distribution, you can see that the performance is not very bad. For size, you can see in many cases that the performance is almost the same, like exponential distribution, gamma distribution, Weibull distribution, Laplace distribution, log normal distribution, etc. However, in some cases we have seen, like when we considered A is equal to 3, B is equal to 4. See, if A is equal to 3, B is equal to 3, almost in all the cases the performance is quite good. But if we go to, say, for example, A is equal to 3, B is equal to 4, then you can see that if I'm looking at, say, exponential distribution, the size becomes too liberal. For example, here you can see 0.1, 0.08, 0.08, and so on. Similarly, for the Weibull distribution, you can see. So only for the symmetric distribution, like a T distribution or a double exponential distribution, the size is much better. But in the skewed distributions, the performance becomes not so good. So that means when the level of factors increases, the likelihood ratio test robustness becomes not so good for skewed distributions. So these are the results that we have presented. Finally, we have implemented the result on certain data sets. So what we have done, we have actually gone for the wholesale price index values of the cereals like paddy, wheat, jowar, and bajra from 2011 to 2020. The original data set contains the wholesale price index values of several other crops which are available. So we have taken from certain government portal, it is called Data Link 1 and so on. So from the data set, we have actually done the sampling. See, each period has 24 WPI values for each of the cereals. And we have taken only 5 paddy, wheat, jowar, and bajra. And we have taken these periods like 2011-12, 2015-16, and 19-20. So 3 time periods we have taken. And we have randomly selected observations with cell sizes 17, 19, 21, 18, 18, and so on. So we have done the sampling on our cells, and then we have tested whether the normality assumption is applicable or not. So we have followed the standard methodology of using QQ plots. We have tested about the homogeneity of the variances, so that is rejected. So we have carried out all those things, and therefore the procedure that we have developed can be implemented. So WPI is the response variable. The factors are serials, that is factor A, which is present at 4 levels. The time period is factor B, which is present at 3 levels. So it's a two-way model. And the interaction factor is present. We are getting 0.04 as the p-value. We have applied the parametric bootstrap test of Zhu et al. For the interaction. So if that is so, then we implement the test procedure here. And when we implement here, you can see that the likelihood ratio test statistic value turns out to be certain thing multiplied by 10 to the power minus 25, and the critical value is 10 to the power minus 3 into something. So therefore the test rejects. That means the wholesale price in values of these are strictly in the increasing order. That is what we get. That is Zwar, wheat, paddy, and bajra. We have considered one more implementation, that is
Professor Sumesh, sorry for interrupting.
Yes, I will just I'll take 2 more minutes. Yeah, just 2 more minutes.
Okay.
Yeah.
Thank you.
So, so out of the total suspended particulate value, we look at the respiratory suspended particulate matter, that is RSPM. That is the fraction of the TSPM which is readily inhaled by humans through their respiratory system. So again, we have taken the random samples of RPSM values from the cities of Varanasi, Noida, and Kanpur for the years 2006 and 2011. And we have used certain data link on the portal.gov.in, that I have put data link 3 and data link 4. So the factor A is the different cities of Uttar Pradesh, that is at 3 levels. And factor B as the years, which is present at 2 levels. And RPSM values are the response values. So here again, we implemented the test and we got that the test statistic value is 10 to the power minus 24 into something, and the critical value is 10 to the power minus t. So the likelihood ratio test rejects the null hypothesis. So, so again, we have seen that the RPSM values are in the strictly increasing order. We have again implemented using the test, that means which we have developed. So actually, we have developed the R package for this thing, and it has been uploaded on the GitHub using R. We have developed this. So anybody who has a data set, he can actually use this one. So that's all. I think these are the references. Thank you.
Thank you, Professor Sumesh. It's a very interesting talk. You included a lot of mathematics, applications, simulations. So in one package, everything is there.
Yeah,
so
we have developed actually the package for implementation also. Like if you have a data set and you want to check whether the test can be implemented and get some results, so you can do that. Straight away, you can open the link and like an Excel sheet, you can put the data and you can...
what is the name of the package?
Yeah, it is there actually. I have not written it in the slide. It is Anjana Mandal dot something. I'll just, if you want, I can give you actually that.
Okay. Thank you. Any questions from the audience?
Thank you, Professor Somesh Kumar, for your nice talk. Myself, Gopal. I have a small doubt.
Yes, sir.
In one place you mentioned ML exists with the probability 1. Therefore, which theorem in probability theory you invoke here?
That is under the regularity conditions. Actually,
you mean almost surely condition. Almost surely it exists.
Yes. Yeah, the initial theorem which we teach generally. So there certain regularity conditions are there. So that one we have implemented there. Yeah.
So, no, any concept of almost surely comes in here.
Yeah, we say actually with probability 1. That is the statement. Like
you mean a general sense?
No, with probability 1 actually that is the statement given. For example, even in the C.R. Rao's book, where the regularity conditions are given and they state the theorem. There they say MLE exists with probability 1. That is the statement that is required.
Okay. Thank you.
Yeah.
Okay. Any more questions? Good questions. So if no more questions, we thank Professor Somesh for a very elaborative talk. Thank you, Professor Somesh. And thank you, Professor Satish, for giving me this
Thank you,
opportunity.
Professor Jain, for your nice chairing. In fact, both the speakers are
Yes,
an
the
excellent
talks
job
were really
and
good.
very interesting work. In fact, we are very lucky to have these people. And on behalf of the organizing committee, we would like to extend gratitude to Professor Sanjay for chairing the session, and Professor Sarashma for their excellent job. Thank you.
Thank you.
We hope you let us move to the next session. This time. Next session, we have Professor Sunday is here today. Gautam, please introduce the chair and maybe we need to for forward and help you with the chair to please.
A warm welcome to everyone. I hereby welcome you all to the Technical Section 6 with the session chair, Dr. Ramakrishna Rao Shinde. He obtained BSc, MSc and MPhil in Statistics from the University of Pune and received his PhD in Statistics from Sardar Patel University, Anand. He is currently working as a professor and head to the Department of Statistics at Kavitri, Bahina branch of North Maharashtra University. He has guided 6 candidates towards PhD in Statistics. His research areas include statistical process control, stochastic mortality modeling, public health statistics, actuarial statistics, distribution theory of rank, scans, and patterns. He was a visiting professor at the University of Calgary, Canada, and a life member of the Indian Association for Productivity, Quality, and Reliability, the Indian Society for Probability and Statistics, and the Indian Statistical Association. He has played a major role in the development of the curriculum and has organized a multitude of academic events, including National Conference for Research Scholars and College Teachers. He has published more than 20 research papers, including Modeling and Forecasting Mortality using the Lee Carter model for Indian population based on decade-wise data, and Catastrophic Maternal Healthcare Expenditure in India. We are really lucky to have you with us, sir, chairing the session today. Without delaying it further, I once again extend a warm welcome to you on behalf of the organizing committee and kindly request you to take over the session. Over to you, Professor.
Hello. Good evening, everybody. I'm Professor Shinde. So I have responsibility to chair this session, particularly technical session number 6 of this conference on first day. We have 3 speakers in this session and we are a little bit late. So I request all 3 speakers to be strict in terms of time because we have around half an hour each, 25 minutes to speak and 5 minutes you may spend in the question answers. So our first speaker is Professor S. Satish, Mahatma Gandhi University, India. His talk on comments on Lucas 1980, characterizations by zero regression. I hope he's already there in this.
Yes.
Screen. So I request you to start your presentation, sir.
Okay. Thank you. Am I audible?
Yes.
Okay. I hope everybody can see the slide, right?
Yes.
Yeah. Okay. So, good evening, one and all. Let me thank Professor Satish Kumar for giving me this opportunity to give you a brief talk about one of the earliest researches I did investigations I did sometime back in 1986. That is about 36, 37 years back. So Professor Lucas, in this paper, 1980 paper, he illustrated his method for characterizing distributions using constancy of regression. He used two distributions to illustrate his method. The one was on the set of non-negative integers. The other one was the set of positive reals. So at that time, I was just out of curiosity, I just tried to work out the case of Laplace distribution whose support is the set of real numbers. So apparently, I bounced upon a lacuna in his methodology, the conditions that he has specified for his method to be working. So recently, I published that in the Journal of Indian Statistical Association. So I thought I will give a brief about that here. It is very focused, though the method is rather broad, or the method of constancy of regression is rather broad. This methodology and my talk is focused on his paper and what I have done, my humble contribution or addition to that. That's all. So, so we have this definition for constancy of regression of one random variable on the other, assuming that expectation y is finite. So when expectation of y is 0, we say that y has 0 regression on x. Now we briefly sketch the method given by Lukács and then go over to illustrating my case here. So y has constant regression on x if and only if expectation of y e to the power of itx is equal to expectation of y into expectation of e to the power of itx, that characteristic function. So basically it is this lemma based on which that method is developed. So whenever expectation of y is equal to 0, we have y has 0 regression on x. So his method is subject to the following conditions. It applies only to characterization by constant regression, assumed that the distribution function to be characterized depends only on a finite number of parameters. So here is the lacunae, because if it is fully specified, then the number of parameters, unknown parameters, is equal to 0. Whether that case can be handled by the same methodology or whether we need any additional condition, that was my curiosity while applying this method to Laplace distribution. The existence of certain moments of the distribution function is necessary because we will be differentiating the characteristic function, so that should be justified. The differential equation obtained by differentiating the characteristic function has this particular form. So all that is required there is I have given there. I am not just simply reading it out. The assumptions, everything is given there. I just copied this part from his paper. Now here the summation is taken over all integers s1, s2, etc. sp, and those conditions are there. The coefficients are free of the parameters, all the parameters, as well as t, the argument of the characteristic function. R is the order of derivative of the characteristic function, so that we can eliminate not only the k parameters but also all expressions which contain the variable t explicitly from the differential equation obtained. So suppose the case or the lacunae that I found while trying to work out the case for the Laplace transform is, I took it as 1 over 1 plus t square, that it is fully specified. So in that case, there was some deviation from the method he has specified, and the characterization didn't result. So that is the turning point for my investigation in this context. To justify the differentiation of the characteristic function, we assume the existence of a sufficient number of moments for the distribution function. We also have this relation And if x1, x2, etc., xn is a simple random sample of size n from a population, and with those assumptions and notations, we have the expression 1.3 also. From equations 1, 1, 2, and 1, 3, Lukács arrives at the equation expectation of s e to the power of it lambda equal to c, where s is that statistic, to conclude that the statistic S has constant regression on lambda. And conversely, assuming the same thing, we can retrace the steps to reach the differential equation. Sorry, to reach the characteristic function of the distribution by applying the conditions needed for the characteristic function. So the examples Poisson and exponential considered by Lukács are characterizations by zero regression, that is c is equal to 0. The discussion and illustrations in Lukács appear to implicitly suggest that his method is applicable in the setup where the distributions have at least one unknown parameter. So it is rather implicit. He never explicitly stated that. In this note, we illustrate that the method is applicable when the distributions are fully specified, that is, all the parameters are known. But our focus is on the structure of the distribution function obtained so that the statistic S having zero regression on lambda is generated. Equation 1.1. So we are looking at this that structure of the differential equation a bit more closely in the case where the distribution is completely specified. So we start with the illustration given by Lukács himself. So for the Poisson distribution, when lambda is equal to 1, the distribution is fully specified, and we have the distribution differential equation that Lukács obtained. And this array of equations are there. And to make possible use of the differential equation obtained, we consider the linear combination of the terms on the right-hand side of the array to get this particular differential equation, so that 2.1 can be incorporated in that to equate it to 0. Thus, the statistic S having zero regression on lambda is generated. The next example is that of exponential distribution considered by Lukács. And when we put theta is equal to 1, it is fully specified. And we have this differential equation given by 2.3. However, this cannot be made use of in any manner, considering linear combinations, so that it could be equated to 0, and the statistic S having zero regression on lambda is generated. So in this case, it is not generated when the exponential distribution is fully specified. And in other words, the method fails here. As the third example, we considered the Bernoulli P distribution, and we have that particular differential equation for that when P is equal to half. Again, in this case, the statistic S having zero regression on lambda is generated. So we have in the illustrations considered here, where 2 out of them are from Lukács himself, where the distribution is fully specified. In one of the cases, that of exponential distribution, the statistic having zero regression on lambda is not generated, whereas in the case of Poisson and Bernoulli, the statistic having zero regression is generated. So that prompted me to have a closer look at the differential equations 2.1, 2.3, and 2.5, and make a statement or make a conclusion about that. The sum of the exponents of non-constant factors in each non-zero term is the same in 2.1 and 2.5, while it is not so in 2.3. A kind of homogeneity in the sum of the powers of non-constant terms. So I am proposing this as an additional requirement for the method by Lukács to be applicable, or to extend the method by Lucas to be applicable in the case where the distribution is fully specified. Now here I am giving the instance where I chanced upon this possibility or this lacuna in the method given by Lucas. For the Laplace distribution, this is how it appears. When lambda is positive, that means the parameter is there. We have one differential equation. When it is fully specified, we have another differential equation that does not satisfy the condition that I had just stated. That means the statistic is not generated when it is fully specified. Now, in the case when we consider normal distributions, n01, n11, and n mu1, we have the same differential equation. Notice that in n mu1, we have one unspecified parameter, whereas in n01 and n11 are fully specified. But the differential equation is the same. It satisfies the restriction that I just stated, and thus the statistic having zero regression on lambda is generated. Now, the differential equation obtained for n02 lambda is this one, which also satisfies the restriction that I just proposed, and the statistic in this case, though normal distribution having a variance parameter unspecified variance parameter, the statistic is different. So that's all that I have to present before this audience. I thank the editor and the referee of GISA because they gave a direction to the way in which I should present my idea. And I am also grateful to Professor T.S.K. Mutadu and Professor Srihari, my professors, for some fruitful discussions I had on this topic. That's all. Thank you very much. So this is Professor Lucas' paper that I referred, the one and only reference here.
Thank you, Professor Satish, for nice and short talk.
Okay, sir. Thank you. Thank you very much.
Any other comments or questions on this talk from audience? If you have any quick question, you can ask. We have time. Sir, any I have a small question.
Yes,
any
sir, please.
relation with geometric infinite divisibility or infinite divisibility in this connection?
As such, I didn't see anything like that here.
Oh.
This is basically
Only characterization.
Yeah, this is basically extending the method by Professor Lucas to the case of distributions that are fully specified, but we require the additional condition that I just stated. That's all.
Okay.
I didn't look at other structures that might have possibly contributed here.
Okay, thank you, sir.
Okay.
For this nice presentation. Let us move towards the second.
Thank you once again.
Yes.
Thank
sir.
you very much. Okay.
Second speaker is Jinke Zhang.
Hello.
I think. Oh, yes. Okay. Yeah.
Presentation on semi-Markov geometric renewal processes. Am I right?
Yes.
A semi-Markov model with geometric renewal processes. So
Yes.
you'll get around 25 minutes for presentation and 5 minutes for question answer. You have to keep.
Okay.
You may start your presentation.
Okay. So. Hello everyone. My name is Jinqi Zhang. I'm from the University of Technology of Troyes in France. And today I will present you a semi-Markov model with geometric renewable processes. And this is a work in collaboration with Mitra Vladirad from Central Marseille and Nicolaus Lumineux from the University of Technology of Compiègne. My presentation consists of 6 parts. First, the introduction,
and then the model of a mechanical system, and then the semi-macro precise, and the reliability and related measures, mostly the dependency related to the semi-macro precise, and we use the results in a numerical example, and finally a conclusion.
Sorry, Jinke, we are not able to see your screen.
You can't see it? Sorry. Can you see it now?
Yeah,
Sorry.
Yeah.
Yeah.
Can you see it now?
Yeah. Yes.
Okay, sorry for before. It's the summary I talked about, and this is the topic, and I will begin with my introduction. Semi-macro precises is an important tool in modeling real-world systems in very large numbers of domains, such as reliability, survival analysis, Turing theory, and etc. In our work here, our starting point is the article of Behe Orgon and Dohe Gastro. In this article, these authors model a repairable system with internal and external failures, and the original part is that they take into account the performance decrease of the system by modeling the lifetime with geometric renewable process. But their calculation is based on transform of Laplace. This can be a limit because for real systems, there is a good chance that they don't have one. Therefore, in our work here, we do an extension of the state space by splitting up each state into two parts, one up state and one down state, so that we can use the theory of reliability measures of the book of Mr. Limnius in 2012 directly. And then I will present you the model. Here we consider a system with only one component in two states, one up state followed by one down state. We consider that in up state, the system is in operating, and in down state, while the system is under repair. And here are the basic assumptions of the system. And this is the figure present the failure of the system. The system can fail in two ways, internally or externally. When an internal failure occurs, it is always non-repairable. It means that the lifetime of the system is over with an internal failure, or an external failure occurs, follows by a homogeneous Poisson process with parameter lambda. And we use Bernoulli trials to define whether the external failure is repairable with a probability P, or being non-repairable with a probability Q equal to 1 minus P. And 2, all failures occur independently of each other. And 3, the system can have a replacement when a non-repairable failure occurs, or we replace it directly after n repairs. Also, we consider the replacement is instantaneous and perfect, and the system goes back to its perfect states by the replacement. And here is the original part of their article, and they set UI at the lifetime of the system after its I repairs, and the F is the distribution function with the finite mean before the repairs. So we define the lifetime with a geometric process. So Fix is equal to F of A times I multiplied by X. And here A is the operational factor. If we take A bigger than 1, it means that every time after each repair, the lifetime is shorter and shorter. And by the same way, we set Di at the repair duration after its I failures, and so G the distribution function with finite mean of the first repair for the repairman. So GIX is equal to g of b times I multiplied by x. And here b is the repair factor. And normally we take b is smaller than 1 so that after each repair, the repairman gets more experience and it takes less time for next repair. And 6, ui and di are independent, and each one of both frequencies is independent but not identically distributed. It means that they are ii but not iid. For a is not equal to 1 and b not equal to 1. Because if a equal to b equal to 1, it is an iid. And 7, the state space E is from 0 prime, 0 to prime until n primes. And these are the division of each state into 2 parts. And for the up states in operating, it is from 0 prime to n prime, presented in the graph here. And the down state and the repair from 0 to primes until n minus 1 to primes. And the down state follows an up state. And here are the transition. And because after n repairs, the system is replaced directly. So there is no n2 primes. So finally, we have two times n plus 1 states in state space. And then I'll present you the Fermi-Markov precise. Let's consider a ZT, the Fermi-Markov precise, with finite state space E, and the embedded Markov renewable precise Gn and Sn, where Gn is the embedded Markov chain, and the Sn the jump times that ZT changes its states. And the time is S0 smaller than S1 until Sn, and the time begins at 0, so S0 equal to 0. And then we have Zt equal to Gn for time between nth jump and n plus 1 jumps. We also define the Fermi-Markov kernel Qij of x is the probability that the process is from state I to state G, and the jump time is less than the time x, and this is for Ij from state space, and the time is greater or equal to 0. So we can see that Qij is a sub-distribution function of the system, and it begins from 0 until value less or equal to 1. And we consider here the standard Fermi-Markov precise with Qii x is always equal to 0, which means the matrix of the kernel, the diagnosis is always 0. And I put it explicitly in this standard form. And we divided it into 4 parts. Q0, Q0, Q1, Q10, Q01, and these are the transitions. Q0 for upstate to upstate, 1 downstate to downstate, 0, 1 upstate to downstate, and 1, 0 downstate to upstate. And in the kernel here, finally we change the first line, because here before this is Q0 prime, 0 prime, and we put it in 0. And the only term changes here is Q0 prime, 0, 2 primes. It is divided by 1 minus P0, 0 prime, 0 prime, 0 prime. And this is the limit of Q0 prime, 0 prime, with the time t goes to infinity. And I will present every term of the kernel explicitly. To lead from state I prime to state I2 primes, the system must fail externally and it must be repaired. So this is presented by the integration of time from 0 to x. and there is no internal failure occurs, and it follows homogeneous Poisson process, and it occurs an external failure, and it can be repairable with the probability p. And this is for the state from 0 to n-1. And then to return to its initial perfect state, we have to replace the system by a new one, which means it can fail in two ways. An internal failure, the lifetime is over and there is no external failure, or there occurs a non-repairable external failure. So no internal failure and external failure with the probability of non-repairable. And to get to the state I plus 1 prime, a repairman turns to the system, and we can take the geometric process directly after ith repair. So it is g of b times I multiplied by x, and also for the state from 0 to n-1. And for the system, we replace it directly after n repairs, whether it is an internal failure or external failure. So here, internal failure, and here, external failure. And then I'll present the embedded Markov chain, Gn. It gives the successive visited states by the Fermi-Markov process after nth jump. The transition matrix P is equal to Pij for state ij from the state space E, and it obtained by this formula. When the time goes to infinity, the kernel Qij tends to a value. And here we have the transition matrix. And we also divided it into 4 parts as we divided by the Fermi-Markov kernel, P0, P1, P10, P01. And we also define the stationary law rho equal to 0, and we divided it into 2 parts, one upstate, rho prime, and one downstate, rho 2 primes. And for the upstate is from 0 prime to n prime, and for downstate is 0 2 primes to n-1 2 primes. It defines when the system become stable, the probability that the system stays in state I. And then I will present the reliability and the related measures. For the moment, we have essential terms about the Fermi-Markov process, but still we need other terms, and I will define it here, such as the initial law of the Fermi-Markov process. As before, this is a line vector alpha, and we divide it into upstate alpha 0 and downstate alpha 1. And this is the probability of the system begins at state I. And the distribution function of Sejun time is h bar t, and we take it into 2 parts too. This is a clone vector, h0 bar t for upstate, and we take directly 0 for downstates. And this is from h0 prime bar until hn prime bar. And we express it explicitly with this formula. It is 1 minus each line of the kernel of the state in the state space Qij. And we also define the mean Sejun time, m, a vector, a clone vector, and also in 2 parts, upstate m0, downstate m1. Also the expression of the upstate. It is the integration from time 0 to infinity of the hi bar. And we also define the state-just convolution of a function by Q as this formula. It is the sum of the state in state space E of the integration from 0 to t of the kernel from state I to j in the within time ds multiplied by the function in state j of time t minus s. From this definition, we also have the n-fold convolution of Q by itself. So Qij times n of convolution size is equal to Qij of times n minus 1 convolution of Qij itself. And we use this function here to define this function. And especially Qij of times 0 is equal to the indicator in the domain R plus of time t multiplied by delta Ej. And delta Ej here is a canonical symbol, which means delta Ej equal to 1 if I equal to j, otherwise 0. And the convolution of Qij of time 1 is Qij itself. And we also present the stationary distribution pi of the semi-Markov process Zt as follows. It is equal to rho I, the stable probability of the system states in state I, multiplied by mi, the mean siege runtime of the state, divided by m. And the m here is the mean siege runtime of the system, the sum of each state of rho I multiplied by mi. And we will also use the semi-Markov kernel of its derivatives in random Nicodim way. So the small Qij is equal to the derivative of the kernel Qij directly. And we also define the Markov renewable function phi t is equal to the inverse of I minus Q in the convolution size. And we also put it in block matrix form as we presented before, in 4 blocks, up to up, down to down, up to down, down to up. And until here, we have all the terms to use the reliability functions presented in Mr. Liminius' book in 2001 directly. And here, first we will use the reliability function. It is alpha, the initial law, multiplied by the inverse of I minus Q0 in the convolution size, convolution of H0 bar. And the reliability function defines the system whether it's reliable or not. And it's the probability, so it has a value between 0 and 1. When it is near 1, it is more reliable, and unreliable otherwise when it is near 0. And the same for the instantaneous availability. And it's equal to alpha, the inverse of I minus Q in convolution size, convolution of H bar. This is also defines whether the system is available at time t or not. And it's also a probability, so have a value between 0 and 1. And there are other measures such as mean times. Here, the mean time to failure, and the mean time to repair, mean uptime. And here this is the clone vector of ones, and it is of R dimension. R here is the number of up states. And the mean downtime, and here is also the D minus R dimensions. D here is the number of states in the state space, R the up states, so D minus R the down states. And we also have the rate of occurrence of failure of this function. And with all the function and all the terms we defined before, after algebra convolution calculation, we have some final results presented here. So reliability, availability, stationary availability, mean time to failure, mean time to repair, mean uptime, mean downtime, and specifically, if the system begins with its perfect state, so it begins at 0 prime, which means alpha equal to 1, 0, 0, 0 for other terms. We have the reliability equal to H0 prime bar directly. So we can see in this function that it begins when t equal to 0. It is 0, so the system is totally reliable. And when with the time tends to infinity, it tends to 0. So the system became less and less reliable with time. And here is the function of availability. And mean time to failure is equal to m0 prime. And the rate of occurrence of failure of this function, and when times goes to infinity, it has a value here. And then we put it into a numerical example by MATLAB. And we have taken the lifetime of the system, follows a phase-type distribution with presentation alpha 100. A is the operating vector bigger than 1, 1.25, and of matrix T, and beta 1, 0, 0, B the repair factor 0.9, and the S the matrix. And they have taken lambda equal to 0.02 per hour. It means that it's about every 500 hours it occurs an external failure. And the external failure has the probability to be repairable with a value of 0.87. And we take n equal to 3, so 7 states in total, 3 down states, 4 up states. And finally, we have all the values here. This is for the stationary law, mean time, mean sequence time, and the other terms. And especially, we have drawn a graph of reliability with its perfect initial states. As we evaluated before, it begins with time 0 and is equal to 1, and less reliable with time. And this is more interesting because the availability of the system begins at 1, so the system is totally available at the time begins, and it decreased very fast, and it grows here until a value of the stationary availability, and it become stable. And the same thing for Rogov, the rate of occurrence of failure, and it stabilized at a value 2. And this is for the reliability with uniform initial law. It's just for comparison, and also have the same sentence. It's just the time that it stabilized has a difference. And finally, the conclusions. In our work here, we did an extension of the state space, and it allows us to obtain all reliability indicators in a standard way. The way of convolution algebra used here allows us to obtain closed-form solution for reliability and non-stationary indicators. But in our work here, we didn't consider the duration of time of replacement, and there's injury that with every replacement, we replaced this system entirely, includes the component and a repairman. So for the future work, it can be an interesting point to take them into account. And these are the bibliography, and that's all for my presentation. And thank you for your attention.
Thank you, Jinky. Any questions from participants or delegates? Very good point-to-point presentation by Jinky. If you have any questions from participant, you may ask. If no, let us thanks to Ms. Jinky, and let us proceed to next presentation.
Thank you.
So our third speaker in this session is Avenue Kiffel. He is going to talk on comparison of local powers of some exact test for common normal mean with unequal variances.
May I start now?
Yes, yes, sir.
All right. Okay. So good afternoon, good evening, and for us, it's morning. Good morning. So let me share my slide.
Just ask the earlier speaker to stop their sharing.
I think so, yes. It says another person is sharing.
Ms. Jinky, you may stop your sharing. Hello? Okay, you can start, sir.
Yeah, okay, thank you.
You may briefly introduce yourself before starting.
I will do so, okay.
Yeah, okay.
One moment. I don't know.
Okay, start now.
Okay. Can you see my slide?
Yes.
All right.
It's
Okay.
fine.
So to introduce myself, I'm Iheno Kifle. I'm assistant professor in the Department of Mathematics and Statistics at the University of Maryland, Baltimore County here in USA. And I did my PhD in 2013 at the University of Ghent and University of Hasselt in Belgium. And then I was served as a faculty member in South Africa at the University of Limpopo. And then after I joined University of Maryland, Baltimore County as a visiting professor in 2018. And then after in 2019, I continued as a tenure track assistant professor. And it's first of all, it's a great honor to be invited in this the 8th International Conference on Statistics for 21st Century, which is organized by the Department of Statistics, University of Kerala, India. And the work today I'm going to present is comparison of local powers of some exact tests for a common normal mean in the univariate context. Okay, where following my presentation, my mentor, Professor Bimal Sinha, will present the extension of this in a multivariate setup, which is a common mean vector problem. And overall, this work is under, it's conducted together with our PhD student, whose name is Alan Molu, who's a PhD here at UMBC. So this is this comparison of local powers of this invariant common mean problem. This work has already been published in the Methodology and Application of Statistics, which is a Springer volume dedicated to the birth centenary of the known Professor C.R. Rao. And the editors, I see that already, Balakrishnan and Professor Arnold already, I saw them in the list. Yeah, so this book is edited by them. So this is the outline of my presentation. I'm going to first introduce you the problem of this univariate common mean problem. And this is in the context of statistical meta-analysis. Then I will review some available commonly used exact tests. Some of them are p-value based. Some of them are directly using the test statistics like TNF. And once I introduce you this different methods of combining results from different studies, then when you have so many tests like this, you want to compare them, and because you cannot use all of them simultaneously, you want them someone which gives you the highest power. So we're going to first derive the local power of these different tests. 4 of them are p-value based. The last 2 are directly using their test statistics. So we're going to see their local powers. Once I showed you their local powers, then we'll be easily able to compare them, so that we'll see which method or which approach is giving us the highest local power. Then I'll conclude my talk by showing you reference of the work. All right. So as an introduction, so this statistical inference problem of this common mean problem of several univariate normal population, you don't need to know the variances, unknown variances, and possibly these are unequal. This is one of the oldest problem, and interesting because still, once upon a time you see a paper published in this area. Okay, so this is you'll see some of the reference that even goes back to 1915, but still you'll see that Will Manage also published work in this area even recently. So you can see that this problem is still active. So, but this is in the context of statistical meta-analysis. I will say a few words about this, but most of you in statistical meta-analysis, we talk about effect size. And when we talk about effect size, we talk, usually it means that mean difference, risk difference, odds ratio, correlation coefficients. But here we're talking about a mean, a common mean. That's why we say this is a special kind of statistical meta-analysis. Maybe for a graduate student who are attending here, what is meta-analysis? What is meta means? Meta means nothing but is more, additional, or further. So meta-analysis means further analysis, more analysis of the already conducted or published work. Okay, metadata, whenever we say metadata, means more data about the data itself. So let's motivate you this using, as I said, this goes back to the time of Paul Meyer, even in 1953, when he was approached to draw, conclusion about the mean percentage of albumin in plasma protein. And the experimenter gave him these 4 results. Like they conducted 4 different experiments to detect what is the percentage of albumin in plasma protein. And the first experiment with a sample size of 12, and the other is a sample size of 15, 7, and 16. As you can see them, these are not large sample sizes where we can apply asymptotic procedures. So here, as you can see, the mean of the first experiment is 62. The other is 60, and the experiment C is almost 60, and the other one is, let's say, 61. And you can think of that this process is, coming from a kind of distribution with a mean of, let's say, around 60. Okay, but if you see the variances of the first experiment is 12, very good. With the second experiment, the variance is 7.8, but you can see, yeah, that's you expect also, like you see for experiment C, you see that it's 33.4. So using, this heteroscedastic variance, you cannot test whether these means are equal with some common mean mu using the classical ANOVA procedure because of this heteroscedastic procedure. So it was not easy, like immediately how you can combine and test whether, let's say, the mean of this process is 60 because of the heteroscedastic variance. Even Eberhard in 1989, similarly also, he was asked also to analyze these 4 experiments of selenium content in a non-fat milk powder. Again, here we have 4 different methods, okay, with these small sample sizes, almost very close mean. But you can see like the range from 2.7 up to 85.7. This is the range of the variance. So very heteroscedastic variance. So you want to test whether these different results come from a common mean process or not. Can we use like the classical ANOVA here? No, because of also, so we need a method by which we can combine this kind of experiment, okay? So as I said, these all are independent experiments. We have results, so we want to do further analysis of these already conducted experiments. Not only these two that we can apply this common mean problem, you can also apply whenever you want to meaningfully combine data from different sources. For example, upon identifying a hotspot in environmental data analysis, you might send different samples simultaneously to different labs, okay? And then you'll get results. You want to test whether, the mean of that sample is some number or not. But you might get different variances. You never know. The variances, as we have seen before, might be heteroscedastic. So in that case, what are you going to do? Even the same thing here, in Census Bureau application, you want to draw inference about average wage of college graduates in a specified age group in a certain state. Okay, let's say we are now in the state of Maryland. So, in the state of Maryland, we do have different counties. Below state, you have counties. So you're going to collect county level information. Maybe you might select via just simple random sampling. And then under a model-based approach, you want to test whether the mean, you want to test whether the common mean at state level is this amount or not. Mind you, you're going to get a county level information, but you might also get heterogeneous county level variances. Again, this is another possible application area. So another one is also in the, in the regression context, where you have a response variable collected from n subjects. You have, let's say, p explanatory variables, and you're going to have this multiple linear regression model, and you want to test whether, the common beta equals to beta naught, or some linear combination of the betas. And you can, of course, test this using the f-test. We're using this regression mean square by error mean square, which follows an F distribution with P and N minus P degrees of freedom under the null. Okay, then you reject if this F calculated is greater than some critical value. Now the point is, you might have data from K-independent population, and then you want to test whether not the common mean, but now you're going to test a common regression vector beta. So what you're going to do, you're going to have not one F, you're going to have K-independent F statistic. So how are you going to combine and test one hypothesis? But mind you, we are not assuming equal variances across these studies, okay? So these are all application areas. Now, why this problem is still, exists, and it's still, active research area in the context of statistical meta-analysis, this common mean problem. So let's see here. So we said that we do have K-independent normal population, where we're talking about common, univariate common mean problem in the context of normal distribution. So we do have K-independent normal distribution, and let's say that the I's population follows a normal distribution with a common mu, not mu I, common mu here, but the variances can be any. I mean, it can be unequal. That's why we give a subscript I, sigma square I. And we're going to take a sample from the I's population, a sample of size Ni, and we have X bar I and Si. And we know that since we are sampling from a normal population, of course, X bar I follows a normal distribution with the mean mu, and this is the variance of X bar I, sigma square I by Ni. We know that this is, so Ni minus 1 by Si squared by sigma square I. This follows a chi-square distribution, and X bar I and Si squared are mutually independent. Now here, how many test statistics do we have? Okay, how many statistics do we have here? We have k x bar I because we have k samples, and at the same time we do have also from the i's sample we do have s square I goes 1 to k. So I have here 2k statistic, which is minimal sufficient statistic for mu, 1 mu, and sigma square 1 up to sigma square k. As you can see here, I have k plus 1. Here I have 2k. So I have 2k statistic for a k plus 1 parameters. So this is nothing but this is a curved exponential family, which leads to lack of completeness. So because of this, you cannot have uniformly minimum variance unbiased estimator for the common population mu. So you can get infinite number of unbiased estimator. So because of this, you can propose so many test procedures. That's why you can see now there are a number of test procedures. Then of course we want to compare them based on their local powers. Okay, so this is the general setup of the problem. Okay, so now what do we have? So as we said, we do have a sample of size ni from the ice population, but mind you, we have k of them like that. But we have one hypothesis to test. We want to test a hypothesis about the common mean mu, whether that common mean is equal to mu naught or that common mean mu is not mu naught. Okay, like in the example of the wage example in the Census Bureau, let's say that the common salary or the common wage of college graduates per hour, let's say, is $15. Okay, so we want to test one hypothesis, but we do have so many k-independent information or sample. So if this is just, if we think this as just one sample, of course, we have a small sample size, sigma unknown from a normal population. So then we can use the classical T test. Yeah, so Ti follows T distribution with Ni minus 1 degrees of freedom under the null. Okay, but we do have k of these. We have T1 up to Tk because we do have data from k-independent populations. So now the question is, how are we going to combine these k-independent T tests? Okay, so we can think of exact procedures because we are talking about, as you have seen in the previous examples, like in the Pollmeyer and the other example, you have seen the sample sizes are small. Of course, we cannot go for the asymptotic procedures. Okay, so I will show you exact procedure and asymptotic procedure. And then after, I will show you how the different expressions of the local power. But I will start with the asymptotic procedures, combining of these different K information. Okay, let's start with the, the easiest one, and let's assume the strongest assumption that we know that the population, the K population variances are known. Okay, so then life is easy. We can estimate our parameter, the common mean, using the weighted, linear combination of the x bar I, the weight being the inverse of the variance of x bar I. So we can have the estimator for the common mean mu, and finding the variance is also very easy. And this is MVUE under normality, even its best linear unbiased estimator, even without assuming normality of our population. So once we have this, we have the estimator together with the standard error of the variance of the estimator. Then we can use, of course, the classical Z distribution or Z test to do the hypothesis testing. This one, we can test now this hypothesis. But the thing is, do we know the variances, the K variances, the population variances? No, usually we don't know those. So we're going to estimate those using the sample variances. So then we're going to use this, the known Grable-Deal estimator, which is again, everything is the same, except that the population variances are replaced by these sample variances. And these are the variance of U hat GD, expected values of this ratio here. Again, this looks nice, very easy, but the thing is, now the variance of U hat GD, finding exact expression of this is very difficult. And even if you manage to come up with the exact expression of this variance of U hat GD, it's not directly easy to, it's not easy to implement. And even that's Katri and Sa, even in 1974, they come up with exact expression of this variance, but it was not easy implemented. So then what are you going to do? Then you go to a sort of approximation, reasonable approximation. Okay, so I will show you that one. Okay, so this is the approximation here by Professor Bimal Sinha, who will be the next speaker on the multivariate context of the same problem. Okay, so he did the variance, the approximation of variance of U hat GD like this. Okay, this term here, and which is a very similar expression, which was also proposed by Paul Meyer, the same thing, even though they follow different approach, like Professor Sinha followed a chi-square identity. But you can see that except here ni plus 1, here ni minus 1, of course, we are talking about approximation large sample. So these are very close anyway. And these are the two approximations, but there are also another approximation, variance approximation 3 and variance approximation 4. This is due to Hartung in 1991, but this is the most classical one, only taking the first term. As you can see here, this is the first term. This is the first term. And this is in most softwares, you can have this one. So then once you have the variance of U hat GD, even though it's approximated with your estimator, then you can calculate your Z statistic, and which follows standard normal. And then you can reject the null if the calculated value is greater than this cutoff point. Or even you can form approximate confidence interval for this common mean in asymptotic framework. So now, so this is asymptotic, but as I say, what we are working on is in a small sample size context. So the central focus of then this paper is to critically examine some of the exact tests which are available for this common mean problem, but we're going to compare them using their local powers. So what are those ones? I will show you the different exact tests available to combine this different k-independent information. Just before I go there, let me introduce you some of the notation. So this is the t calculated, which is observed, okay? And we know that we reject if this is large. What is large? Greater than in absolute value, greater than this cutoff point from a t distribution. Or we can use the p-value counterpart. We can calculate the p-value and we reject if the p observed is less than the level of significance alpha. But now we're going to study their power and size of these different tests. I want to convert them. This is in a random variable kind of term, so that then I'm going to have this capital X bar and S, which is a function of the data, X bar and S. So this is T random, then I will have P random, okay? And this P random is uniform, 0, 1 under the null. And then I will be using T random and P random to study the power and the size of these different tests. Okay, so just to recap what I said before. So we have this common mean hypothesis. We want to test whether the mean is equals to mu naught, or we want to test against this two-sided alternative. We have one hypothesis, one common mean hypothesis, but what do we have? We have, in one case, we have k different test statistics, independently distributed t statistics. Sometimes we can think of like here identical if we are talking about all of them are with equal sample size. Or sometimes in a linear regression context, okay, we might have, as I showed you, we have F1, F2 up to Fk, which are independently distributed again. Or we have P1 to Pk, of course, these are identically and independently distributed p-values under the null. So I want to combine this. Some of them are the starting, the information I have is a p-value, or sometimes I might have k f statistic or t statistics, which are k of them, So then I want to combine them. If I have the p-values, I will use a p-value based exact test like TPET, Wilkinson inverse normal Fisher exact test, or I can directly use a method which is a modified T exact test where I'm going to use the different T statistic, or I can use the modified F exact test where I'm going to use the different F statistic value. So we're going to have 4 p-value based tests, and 2 of them are directly using either T or F as a statistic. So just quickly to go over with what are these different exact tests, I will quickly show you. So in here in TPET, so what we have from these K different studies, okay, we do have K p-values, okay, but you're going to test one hypothesis, okay, that is H naught equals to, H naught is mu equals to mu naught, again, mu is different from mu naught. So how are we going to do that? Just order them and take the smallest one, and if the smallest one is less than this cutoff point, okay, 1 minus alpha raised to 1 by K, then reject the null. Okay, so this is very simple and easy to apply. And by the way, the smallest p-value is equivalent to the largest t. So that's why this is also equivalent to this procedure which is proposed by these 2 statisticians, okay? But in any case, here, TPET is very easy. Just order your p-values, take the smallest one, compare against this. If your smallest p-value is less than this one, then reject. Otherwise, do not reject the null hypothesis. A generalization of TPET is Wilkinson exact test, okay? But in Wilkinson, we have different orders, 1 to K. So Wilkinson of order R is, now again, this is the order statistic of the p-values. So reject the null if PR is less than dr alpha, okay? So this PR follows a beta distribution with these parameters under the node. You can easily calculate this cutoff point from this distribution. But mind you, R goes from 1 to K. So when R is 1, we directly go back to TPET. Okay, then you will have order 2, order 3, up to order K. Okay, so you need to specify your order when you work on the Wilkinson exact test. And the other one is inverse normal, as the name implies. So what we are going to do, we're going to convert each p-value into the corresponding standard normal score. That means here, we take the inverse of the PIs, then we're going to get the ZIs, and then we sum and we divide by the square root of K. And if this value is less than minus D alpha, then we reject the null. Otherwise, we do not reject the null. And the other one is Fisher inverse chi-square test. Again, this is another popular way of combining this K-independent information or p-values, which is we take the product now, is of the p-value, then we use the connection between uniform and chi-square. And then if -2, the sum of the log pi, is greater than this chi-square cutoff point, again, we reject. Okay, so we've seen TPET, we've seen Wilkinson, we've seen inverse normal and Fisher, that all uses p-values directly of K-independent studies. This is how we can test the common mean hypothesis. And the other 2 are directly using the T or the F test statistic. So this is, again, this is long time. The fair weather considered like taking just the weighted linear combination of the TI. So here what we're doing is, since this is a 2-sided test, we're taking the absolute values of the TI, but we take the weighted linear combination of the absolute values of TI, where the weights being the inverse of the variance of TI, and this is the variance of from a T distribution. And now we can calculate, the D1 alpha from this expression. Since we are taking, weighted linear combination of this T test statistic, then we're not going to have a ready-made distribution for T1. Okay, so because of that, you have to get D1 alpha by simulation. And the same thing here. We're going to take a weighted linear combination of F, and we reject if this is greater than this D2 alpha. Again, W2I is nothing but the inverse of the variance of F, okay? And again, D2 alpha, we can easily compute by simulation. So you have seen what? 4 plus 2, 6 different exact tests. So which one are you going to use and why? Okay, so that's why we're going to compare them. We have all these ones, so we want to compare them, and we want to compare them based on their local power. When I say local power, what is the power to detect a very small difference from the null? Okay, we want to detect a very small difference, close to 0. Okay, this. So what we did here, we derive the expression of the power of the test under the alternative. Okay, and then we carried out its Taylor expansion. And because of the two-sided nature of this test, the first term vanished, and we end up with only terms, to the power of delta squared, delta raised to 4, delta raised to 6, and the like. And those higher terms are almost 0 because the delta is almost close to 0. We expanded around 0, and then we came up to the local power expressions. Okay, so I'm going to show you a local power expression of these 6 different exact tests under 2 scenarios. First, I will show you a general case where we're considering equal sample size of this K independent study. So let's assume that we take a sample of 10 from the first, the sample of 10 from the second, all equal sample size. So the degrees of freedom are equal. So this is a special case, okay? And the general case is, okay, what about unequal sample size? So the degrees of freedom are different, okay? And mind you, whenever you see psi in this term, in the expression, this means that the sum of the inverse of the variances, okay? So before showing you the different expression, using the null, the distribution of the p-values under the local alternative, okay, we came up with this lemma, which is very crucial, mainly for the p-value based local powers. Okay, so the probability that p greater than some value c under the alternative can be approximated by 1 minus c plus n delta square by 2 sigma square psi nu c. So what is psi nu c? This is based on non-central t distribution. Okay, so you can see that you integrate from minus t nu to t nu of the second derivative of a t distribution, a non-central t distribution with no degrees of freedom and non-centrality parameter delta. So we have this lemma, but let me show you the different results. By the way, the detailed proof, it's a long paper. The detailed proofs are available in that book, the one I showed you at the very beginning. So now this is the local power of TPET. So the first one is in general case. So always, I try to show you different colors here. So whenever you see blue, this blue is common in all the other tests too. This is a general case where we don't assume equal sample size. Okay. Now, when you assume this is the local power of TPET, okay, alpha plus some term. If delta is 0, of course, we reduce to alpha the size of the test. So now, the thing is, if we assume equal sample size, this will be common. It will be n. This will be out. Okay. So it's not anymore nu I because we have, this is a function of the different degrees of freedom. So this is also will be common. So we end up with the sum of 1 over sigma square I. So then that will be psi here. So in the special case, you have this one and another term here. So, I mean, what are psi nu t and all, you can see it here. But this is the local power of TPET and the special case and local power of TPET in the general case. The same thing also the local power of Wilkinson test in the general case and in the special case. As you can see here, alpha plus delta square by 2, the same thing here, alpha plus delta square by 2 for TPET. Okay, so this part is common. Okay, for again TPET and Wilkinson, we have this a combination of k minus 1 by r minus 1 sin u w. Now it was t for TPET. Okay, we have dr minus 1 by dr alpha. So this is from, it's from the beta distribution. So we have all this. Okay, and you can see that when r is equals to 1, this thing will reduce to the TPET. And the other one is this is the local power of inverse normal test. we are able, in the general case, we are able to write in this form, okay? And this is in the special case, local power of inverse normal in the special case, okay, alpha plus n delta square by 2 psi, again, this term. So what are the different terms are expressed here? And this is the local power of Fisher again. I will summarize all this in one slide, okay? As again, general case and the special case. This is the local power of modified T in the general case and in the special case. The last one is local power of modified F in the general case and in the special case. So now, since I showed you so many expressions, let me summarize them in one slide, okay? So this is, first I will show you the special case. So this is Tippett, this is Wilkinson of order R, inverse normal, Fisher, this is linear combination of T, and this is linear combination of F. What is the purpose? The purpose is not to come up with the absolute figure of the local powers. The purpose of this paper or this study is to compare. In any way, we want to rank them. Rank these different tests based on their local powers. So if that is the case, if I want to compare them, you know, I don't need to consider these blue parts. I can because the blue parts are common for all. So I can compare them based on their black parts here, you know, this part. So what is the advantage of doing so? So the advantage of doing so is now I'm avoiding psi. What is psi? Psi is this is a function of the population variance. Psi is the sum of 1 over sigma square I. So that means the implication of this is we can compare these different tests in the special case without considering the population variances. So that's a good result of this study, okay? And we did that, okay? We did that also. I mean, don't focus on the absolute figure of these numbers. The only thing we want is to compare them. So here, this is a special case. So we compare them, you know, just without this blue part, okay? So this is like when we have information from 5 independent studies, each of them are with sample size of 15. We compare them and we found that modified F and modified T are giving us the highest local power. Again, with 25, the same thing with the sample size of 40. And we even increased K, the number of studies. Okay, and you can see it almost, you know, modified F and modified T are uniformly giving us better local power of the second term without this term in the second part, or let's say without the blue part. Okay, but now you can ask that when you see Wilkinson here, this is k is equals to 5. Now, if that is the case, you can have Wilkinson order 1 up to order 5. So which one is this for k is equals to 5? When k is equals to 10, of course, you can get Wilkinson up to order 10. So which one? That one. So here we did that. So like first we tried to identify for k is equals to 5, which one is the highest local power of the second term again. Okay, so this is like the second one. For k is equals to 10, you'll see the third order. When k is equals to 15, the fourth one. So you can see that almost the highest value obtained for square root of k, like around here, square root of 5, square root of 10, 3 point something. You can see around 4. So these values are the one that you can see here. For k is equals to 5, 0.633. This one here, again, we took only n is equals to 15. For k is equals to 10, n is equals to 15. As you can see here, 0.0412. This one, okay? So now, what about the general case? So this is now all the local power expressions of the general case. Of course, we can also compare them under the general case. General case means unequal sample size of each sample of the k independent studies. Okay, the only thing here is we lose that thing that we don't need to worry about the population variances. then you need to have some information about the population variances if you want to rank them. Okay, so that's what we did for some K. We tried to do so, but as you can see here, the sample size are not equal here. Then, the cost is we have to specify also the population variances. So we tried to put some arbitrary values and try to see, again, also modified F is giving us, the highest local power. So this is the local power curve of these different exact tests. Mainly, we use psi equals to 1, and this is n equals to 50, this is k is equals to 5. Then using that, this is the actual local power, okay? So the local power will be reduced to alpha when delta is 0. As you can see here, we didn't take these large values of delta because we did the Taylor expansion around delta. That's why we are talking about the local power, okay? So this is for Wilkinson. As I told you, for k is equals to 5, we get the highest Wilkinson power for square root of k around 2. So this red one is giving us the highest power. So as a conclusion, so as I showed you, we are able to perform, a uniform comparison of local power irrespective of the values of the unknown variances when, in the case of special case, equal sample size. Then during that time, in that case, we showed that, modified F and modified T performs the best throughout the parameter K and N. And we did also some limited computations for the local power of unequal sample size, but the cost here is we have to specify also the population variances. And we found also a similar result that modified F and modified T are giving us the highest local power. Okay, so these are references of this work. Okay, as I told you, now next to this talk, my mentor, Professor Bimal Sina, will talk about inference about a common mean vector from several independent multi-normal populations with unequal and unknown dispersion matrices. I thank you very much for your attention. And yeah, this is the end of my presentation. If you have any question, any comment, you are welcome. Yeah.
Yeah, Professor Shinde.
Yeah, so there.
First speaker concluded in a little time before the time, as briefly given his talk. We have taken some more time is there. You can interact. In fact, anyone has any clarification needed, please. There is time for discussion. Our next session only start at 6:35. Why? Because probably some people join at that time only. So
did I took much time or did I finish very quickly?
Yeah, you finished in time, I think so. Professor Shinde, please, can communicate.
Yes, I was disconnected. Sorry.
That network issue. Yeah.
Very good presentation by Dr. Avenue Kefal. Point to point, he has presented everything nicely. This was very interesting problem of real life situations are discussed. All three presenters in this session have presented in time and very clear presentation they have made and discussed their work in detail with earlier work and references, background studies, and they have presented with problems, examples, and real life applications related with their topics. So I was very happy to going through all these three presentations. I hope all participants in Google Meet as well as on YouTube might have enjoyed these three presentations and taken something for their research work from these presentations.
Yes.
So thank you very much for all three presenters, and thank you to organizers, Professor Satish also, for giving me an opportunity to go through these three presentations as a chair. Thank you very much.
Thank you very much.
Thank you, Professor Shinde, for nicely you are chairing the session in a very nice way, and also the concluded session within the stipulated time. But we have time, in fact, remains. So, any discussion on this part of the presentation of the Professor Kifle?
If participants have any particular point or questions on these three presentations, they may ask some questions in general. We have 3-4 minutes extra. Otherwise, Professor, you can proceed for next session.
Professor, we have to wait for some time because we have scheduled the session as per the time schedule. Probably some speakers, some participants from different parts of the world are waiting for listening Professor Sinha's talk. They will probably join by 6:35. Because this session is up to 6:25, and we have put 5-10 minutes in between because that will not affect the next speaker's talk.
Oh, I see.
That is why. Yeah. And we have more than enough time. So you can, or someone can interact. This time we can use for interaction. While in offline conferences, we get more time for interaction. But here in online conferences, it is very rare. Yeah, Professor. Yes.
Okay. So now that you have some time, so I can make a couple of comments. Okay.
Okay, Professor. Please.
It's not all of us,
Yeah, most welcome.
Long time back, when I was a faculty at the University of Pittsburgh with C.R. Rao and Krishnaiah.
Oh, yeah.
So I'm talking about 1980, 1982. Around that time, I had one American student, and he was studying engineering. And statistics was at the level of Hogg and Craig. It was one of the required courses to get his degree in engineering, His mind was not in stat, naturally. He was studying engineering. So he was in my class. Very smart otherwise, but stat was not his cup of tea. He was doing very poorly. I said, "Oh, what's going on? You're so smart otherwise." They say, "Yeah, but I don't like stat. I like you, but I don't like your subject, You're a nice man, but the subject is very dry and I don't like it." And he started getting very bad scores, this and that. And I thought, wow, this is really sad. Then the first midterm exam, he got a 0. Second midterm, he got a 0. And I felt very bad. Otherwise, he was very nice boy. Then in the final exam, I looked at his exam, nothing Page after page blank. On the very last page, he wrote something. The question was, define type 1 error and type 2 error. I did the basic testing of hypothesis, So that was the question. Define type 1 error and type 2 error, and something else. Now, this is his defining. Type 1 error. I made a mistake by signing for this course. Type 2 error. I should have dropped it, but I hang in there. That was his definition of type 1 and type 2 error. But it's so unusual, it's very unusual. And I thought, wow, that's a very smart way of looking at what we teach. So I called him up and I told him, okay, all right, so I'll not let you fail. What is the passing grade? Passing grade is like a C, So I gave him a C and he was out, But there's a nice way of defining type 1 and type 2.
Yeah.
Professor Filippo is also there in the group just before.
Is Thomas Matthew here?
Yeah, Thomas Matthew is speak. In fact, immediately after your talk, Professor.
I know.
Whether Thomas
No.
Matthew is yeah.
I don't see him.
No, not yet. Okay.
Yeah.
Oh, it's a bit early for us, but that's okay. It's almost 8 o'clock. I'm sure he'll be up.
Oh, okay. Professor Kanjan Jain? Professor?
Thomas, are you up?
Dr.
Oh, really? But you have not joined yet, right?
No, I have not joined yet. I'm going to do that.
Okay. All right.
Yeah.
Okay.
What time is your talk?
It's now in about 5 minutes. Yeah.
In about 5 minutes. Yeah.
Yeah.
I'll join.
Okay.
Okay. Yeah. Okay. Yeah. Bye.
Yeah. So Dr. Matthew just called me and he's going to join soon.
Oh, okay. And in the morning time, in fact, is it?
What's your time now? It's 6.
Here it is 6:22 p.m. here in India.
Oh, okay. For us, 7:52 a.m.
Oh, okay. 7:52. Okay. Also, Professor Sinha, you can give some advice to the youngsters. So he's calling someone. Yeah. Professor Shinde, do you want to add anything for the benefit of our young researchers?
I just want to comment on this online conference. It is
please.
Even though you are organizing online conferences from last 3 years in pandemic, also it was continued, and physically organizing conference is somehow simple sometime, because organizing online you have to keep all IT resources ready, as well as you have to keep contact with all experts in time. Last time I forgot to join for chairmanship talk also. So I was very sorry for that purpose. Last conference, I forgot. That was major problem from my side. But it is interesting to see all these online conferences. One can very clearly listen these lectures, and all these presentations I have seen from mornings. I have missed 1 or 2, but very clearly I can go through all those lectures. Voice was also clear and presentations were also clear. So that is advancement in terms of online conferences.
Professor Shinde, where are you from? You are from
I am
which
from
school?
North Maharashtra University, Jalgaon. It is around 400 kilometers from Pune. I graduated
really?
from
Wow.
Pune.
Okay, pretty far.
Yeah.
In fact, Professor, as mentioned by Professor Shinde, it is true that those who are interested in attending the session seriously, these online conferences will give more benefit. Yeah. In fact, in several situations we have, we are also in the parallel. There's a YouTube streamline also there. So some people are there in that group also.
Yeah.
Without, yeah.
Morning, I did not get the link Google Meet, so I was there in YouTube.
Yeah. Some people have, it is difficult for them to join. Those also there. Others, yeah.
So you are in the department or at home?
Yeah. Now I just returned back to my quarters. I'm staying in the campus itself, university campus.
Yeah, good.
So here the university quarters are there.
I am also staying from last 27 years in campus only. University quarters.
Okay. Okay. While I'm in the department, also it's better for me because at any time go to department and return back.
2 minutes you can reach, and you can give more time for department as well as university.
Yeah. I know you are missing last time because you are having some
My
other
wife we were in a hospital, and I totally forgot that this event was there due to that her illness. So you are coming to Cochin also?
Yeah, we will be there. Yeah. What about you, Professor?
Yeah, I am coming.
You are also.
Yeah.
Okay.
I suppose we can start now. Am I right?
Yeah.
Hi, Professor Thomas Matthew.
Professor, good evening to all.
Good morning to you, Professor. Good morning. Hi, Professor.
Good evening, Professor Bemal Silka. Professor, good evening. I am from Tirunelveli, near Tamil Nadu, near southern part of India.
All right.
Professor, adjust your camera. We cannot see the face. Okay, thank you.
Is it okay, Professor? Shinda.
Good.
So, Arivaranjan, good evening, Professor.
Yeah, now it is fine. Now the camera is okay. Okay.
That's fine. Professor Gopal, good evening.
Sir, good evening, sir.
Professor Gopal sir. Hi. Okay.
Yes. Did you call me?
Since hello, it's possible. So, since we can take some for the introduction, in fact, for introducing the chair and the speaker. I think we can start from a few 2-3 minutes before itself. Or three, now it's 6:30. Yeah? It is better so that they can take some time for the introduction, and thereafter that will not affect the talk, the actual time of the talk. So if everyone are okay, now I hope others will join by the time. Bhagyalakshmi.
Sorry, sir.
Hello, Bhagyalakshmi. Now I
Sir,
think
it's
that
Amina.
yeah,
May I
you
take
can.
this opportunity
You
to
can.
welcome our session chair?
Yeah.
Yes, thank you. So, good morning, good afternoon, and good evening to all the participants. We are moving on to the technical session 7 of Icstc 2022, which is a special session in honor of Professor KCS Pillai, chaired by Dr. K. Sentamarai Kannan, the senior professor and head to the Department of Statistics, Manoenmaniam Sundarna University, Tamil Nadu, India. Professor Kannan specializes in stochastic processes and their applications. He was awarded doctoral degree for his dissertation on general bulk queues, the results of which have been referred and cited by many scholars and attracted a number of young researchers to this field. Dr. Kannan has published more than 200 research papers in various national and international journals, authored and edited 10 books, including New Methodologies in Statistical Research, Data Mining for Outlier Detection in Digital Images, as well as Recent Advances in Statistics and Computer Applications. He has supervised the research works of more than 40 research scholars and completed 10 research projects funded by various national and international agencies. In particular, Professor Kannan has collaborated with academic experts from New York for a research project on tobacco consumption in 4 Nordic countries, Norway, Sweden, Denmark, and Finland, which was supported by the Swedish Federation of Commerce. He submitted a proposal with Professor Massimo Squilanti from Italy for a joint research project on development of new stochastic models for genomic data mining under Indo-Italian Program of Cooperation in Science and Technology 2005-7, which was approved by DST and GOI. Subsequently, he joined the collaborative initiatives with representatives from Italy, Cambodia, and Spain under Asia Link project to offer a master's course in quantitative methods for e-governance and quality evaluation in the public sector. He's a recipient of a BSR one-time grant by UGC New Delhi in 2012, Academic Excellence Award of 2008 from MSU, SCRC Visiting Fellowship from DST-GOI in 1999, and Young Scientist Award by Tamil Nadu State Council for Science and Technology in 1996. An excellent academician with experience of over 3 decades, we are really fortunate and honored to have you, Professor, chairing this session. So without further ado, I invite you, Professor Kannan, to take over the session. Over to you, sir.
Thank you, madam. Greetings, good evening to all. I take this golden opportunity to welcome and thank our beloved and respected Professor Satish Kumar, Chairman, Professor and Head, Convener, Chairman and Icstc 2022, Department of Statistics, University of Kerala, India, for having given his valuable guidelines for their excellent arrangements to conduct this 8th International Conference on Statistics for the 21st Century 2022. In this occasion, I wish to extend my warm greetings to all the faculty members of the department. I am very much glad to welcome Professor Bimal Kumar Sinha to be resource person. I wish to record my thanks to our respectable resource persons for accepting this wonderful event in this beautiful occasion. Bimal K. Sinha, shortly called as BMS, joined the Indian Statistical Institute ISI Calcutta in 1971 and stayed until 1974. BMS joined the Department of Mathematics Statistics at the University of Pittsburgh, USA in the fall of 1975 and stayed there for about 10 years. In 1985, BMS joined the University of Maryland, Baltimore County, UMBC, as the founder of Statistics Graduate Program. BMS joined extensively on a number of research topics during the last 50 years, published numerous original papers in many international journals, produced 30 doctoral students, and became IMS ASA Fellow. Due to his singular contributions in statistics, UMBC honored him with the title UMBC Presidential Research Professor. The University System of Maryland, USMS, in recognition of BMS' tremendous contributions in statistics, offered him the title USM Research Professor. His outreach and research collaboration is indeed global, with collaborators from many countries: Australia, Canada, India, Thailand, Japan, Taiwan, Germany, Sweden, Portugal. Through an MOU with Mahildal University in Thailand, BMS jointly supervised 5 doctoral dissertations. BMS is the co-author of 4 books in reputed press, academic press, John Wiley 2 books, Springer, and have written more than 130 original research papers with his national and international collaborators and students. The secret to his success, he says, is simply do good work and be nice to everybody. A message his students and colleagues have taken to heart. Thank you, Professor. Thank you. Most welcome, Professor. Please. We invite you on behalf of Department of Statistics, Kerala University, India. Please share your ideas in young scholars and young minds. Thank you, Professor. Most welcome, Professor.
Thank you. Thank you. Thank you very much. Okay. Thank you very much for your kind words. And of course, I thank the organizers for this invitation and the nice online conference. So I request the slides to be displayed. Thank you. Okay. So if you look at the title, we have a few keywords here. First thing, we are dealing with a multivariate setup. We are assuming, and the most probably widely used multivariate distribution is, of course, the multivariate normal. Unlike in the univariate case, we have a variety of non-normal distributions we can deal with mathematically. But in the multivariate case, it's really the multivariate normal which plays the dominant role, because you can do a lot of nice math, and also you can apply various techniques based on a multivariate normal population. So we are assuming that we have data from several multivariate normal populations, and we know that a multivariate normal distribution will have a mean vector and a dispersion matrix. So here the idea is we have dispersion matrices. They are all different, unequal and unknown. But we are assuming that there's a common mean vector. So it's a setup which leads us to believe that the mean vectors, they are all the same. So we have to have a situation like this so that we can apply the theory which is being developed in this paper. So there's a common mean vector from several independent multinormal populations, and of course the dispersion matrices, they are unknown and unequal. And that's the setup. Under that setup, our goal is to draw inference about the common mean vector. So inference should mean, naturally, it would mean estimation of the point estimation of the common mean vector. We can call it mu. Then a test for the mean vector mu. and a confidence set for the mean vector mu. That's the idea. Okay. It's a joint work with my colleague, Dr. Kifle, who just made the presentation. By the way, this is an extension of the univariate normal setup, which Dr. Kifle just presented. And it's also a part of the doctoral dissertation of our student, Elaine Mulu. Okay. Next one, please. It's very rare that we remember our parents every day, let alone our professors who taught us long time back. So for me, I take this opportunity to pay my tribute and respect to two academic fathers. One is Professor Shailesh Bhushan Chaudhuri, who taught. If you look at the picture, Professor Chaudhuri is in the middle, and myself and my twin brother, Professor Vikas Sinha from the Indian Statistical Institute. We are here with our teacher, college teacher. So for me and for us, it was 1962. So exactly 60 years back. So we are just boys, twin boys, about 15, 16 years old. That's when we got our first statistics training. BSc Statistics Honours, 1962, first year. So I take this opportunity to pay homage and tribute to my academic father. That's at the undergraduate level. And the next slide, please. After our BS, when we moved to the Calcutta University, for us it is 1967. So we was just about maybe about 20 years old. So we moved to Calcutta University to get our master's in stat and PhD in stat under Professor Horikinkar Nande. So I take this opportunity to pay my pranam to the two academic fathers. And I really want that all of us who make presentations in national, international conferences, please take this opportunity to recognize your teachers. Normally, we hardly remember them. We hardly remember our parents also. But you say on days like this, on occasions like this, it is a very good idea to remember the contributions made by our gurus early in our career. It's really it's my deep privilege that I'm able to pay my homage to the teachers. Okay. Thank you. Next one, please. I think Dr. Kifle already mentioned that meta-analysis is nothing but, so we have the basic idea is to efficiently combine information or the evidence you have from different independent sources. Of course, there has to be a common goal so that it makes sense to combine the information from different experiments or different studies. So that's the idea. There are many examples. So it is in the spirit of there's a topic, small area estimation. So it's very similar to the idea of small area estimation. There also we try to get evidence from neighboring counties or neighboring units to in the spirit of borrowing strength. So you have the same idea. I have one study, then I can do some statistical analysis. But if I have many studies, and it's natural to combine, then we must combine the evidence, that we can have better inference. That's the whole idea of meta-analysis. Okay. Next one, please. Okay. This is a classic example in the univariate case which Dr. Kifle presented. So, of course, here, you see, there's a very natural setup of a common mean. It can also happen in the multivariate case. So here the idea is, there are 4 experiments to study the percentage of albumin in plasma protein in human subjects. And if you look at the sample means, so the idea is, the experiments they have been designed in such a way that, or the underlying the underlying topic is such that the sample means they happen to be very close, 60 to 60, 59, 60, suggesting a common mean in the population. But if you look at the variances, of course, we cannot assume that the population variances are the same. They're very, very different. So in the multivariate case also, so the idea will be, yes, I might have samples from in the context of environmental sampling. It's a huge area, and we are suspecting that perhaps something is wrong. So we'd like to take samples and get it analyzed so that we can take some remedial actions. And it's not uncommon to collect samples, from the area, from the whatever that contaminated area, and it's not uncommon to send it to a few labs at the same time, because usually the chemical analysis of the analysis, it will take quite some time, and we may not want to wait that long, because if really something is wrong, we want to fix it as soon as possible. So the idea is to send it to a few labs at the same time, and we get the results, the analysis back from the various labs. And because they are all from the same area, it's possible that the chemical or the components we have, they may have the same mean. But because the lab variation is there, the instrument variation, analysis variation is there, so we cannot expect the same variability, because when the results come, so maybe the mean is the same. That is kind of the application in the multivariate setup. The means may be the same, but the variances will be unequal due to the experimental variation in the different labs. So that is the idea in the multivariate setup. Next one, please. This is the result in the univariate case, which Dr. Kifle already presented, so I'll skip it. Next one, please. Yeah, I can skip this part also. Dr. Kifle just presented. By the way, in this paper, in honor of C.R. Rao, we have this this paper here that summarizes all the results in the univariate case. So if you're interested, you can take a look at it for the univariate case. Okay. Next one, please. Yeah. So in the multivariate case, how do we proceed? So there's a common mean vector mu, and there are the dispersion matrices. They are unknown. And then we have K population, sample of size Ni from the ith population. That's what we have. So first thing we do after we collected the data, because it's the normal setup, so we can summarize the data in the form of the sample mean vectors and the sample dispersion matrices. They denoted by Xi bar and Si, capital Si, that's the Wishart matrix. And because there's a common mean vector mu, so natural extension of the Gray-Bildel estimate, and this is the GB estimate, Gray-Bildel estimate from the univariate to the multivariate case is something like this. So you can combine the evidence from all the different samples or from the K populations here through this way. There's a natural estimate of the unknown mean vector mu in the multivariate case. The question is, what is the variance, what is the distribution? These are all very hard problems. Even in the univariate case, the distribution is difficult, is very complicated. Variance is also complicated. So what we do, we use the large sample approximation. In spite of the fact that it's normal, still it's very hard. So we use the large sample approximation. So this is the variance, estimated variance, large sample. So large sample right here, estimated asymptotic variance. In the large sample case, the asymptotic variance will be given by something like, estimated variance will be given by something like this. So now we have a point estimate of the unknown mean vector mu, we have a point estimate and an estimated variance covariance matrix. So we can use these two components to come up with a test for mu, a confidence set for mu, but everything will be large sample. Okay, next slide, please. So that's what we do here. we are for testing mu is equal to mu 0. We can use the chi-square, which is an asymptotic test. Chi-square test is similar to Hoteling's square. You can say that mu hat minus mu 0 over the dispersion matrix inverse. And an asymptotic confidence set can also be obtained by applying this thing here. It is centered at the Gravel-Lill estimate, and this will determine the shape of the confidence ellipsoid. But anyway, so we have a nice solution in the multivariate case in large samples. Next one, please. There is another solution also. There is another solution also based on the idea of another approximate solution based on the idea of a generalized p-value. So the original idea of generalized p-value goes back to 1989. There are two faculty here. They are the statisticians at the University of Wisconsin-Madison. This is the first time you have a paper in JASA, 1989, Journal of the American Statistical Association. Very novel idea based on generalized p-value. I believe these authors, they struggled to solve some testing problems, as you all do. And some testing problems, they look very simple, but they are natural, they're very difficult, non-trivial, and there's no easy way to solve them. So they came up with this idea of the generalized p-value. Okay. For example, it can be used, generalized p-value can be used to get a solution for the usual ANOVA problem, testing the equality of means when the variances are unequal. That's the variance special problem. In the case of the one-way random effects model, test for the variance component, test for the treatment effect variance component. And in connection with the reliability, if we assume that this the stress strength model, what is the chance that the reliability can be defined as strength more than the stress? So if we assume this kind of, even in the simple case of normal, then the parameter, the reliability parameter, happens to be a function of the sample means and the population means and the variance. A parameter something like this, and it's not easy to get a test for this parameter. Even in the case of the one-way random effects model, it's not easy to get a test for the parameter, the treatment variability. So there are many testing problems which are very useful. They're very natural problems, but there are hardly any solution. There is no solution, except of course in large samples. So these authors came up with the idea of the generalized p-value solution. This is a method which can be used to solve not only these problems. By now, there are many papers. There are some books also, books on generalized p-value. And at one point, it was a very pet topic for me. I gave seminars based on generalized p-value at many places. So this is the univariate idea they had back in 1989, and of course subsequently also in 2003 and so on. Next slide, please. So following this idea, our statistician friends from Taiwan, three of them, Lin, Li, and Wang, in 2007, what they did, they took up the idea of Sui and Yuanhandi, all sorts of problems based on the generalized p-value, and they extended, they had to work very hard. They extended that concept to solve the problem we are talking about. How do we get a confidence set for this multivariate mean vector mu in our setup when the dispersion matrices are unequal and unknown? So they extended from the univariate case to the multivariate case. It's a non-trivial extension. I'll tell you why. I tried myself and many other statisticians who are, who work on multivariate analysis. I tried myself to extend to use the generalized p-value idea in the multivariate normal case. It's not easy, So I think these authors, they deserve a lot of credit, So what they did, they come up with a very nice, it's a nice paper, lot of theory. But the good thing about this paper is that the part of which I really like is that they also came up with an algorithm, step by step, 5 steps. So all you do, you follow those 5 steps. You don't have to delve into the theory. You just follow these 5 steps and you can come up with a nice solution. So that's what, I put that as bullet point here. Anyway, the slides will be available in the department with the chair, Dr. Satish Kumar. If you're interested, or you can even take a look at that paper by 2007 paper, the various steps. If there's an occasion for you to apply this generalized p-value in this context of multivariate normal mean vector, you want to get a confidence set based on the generalized p-value idea, just follow these steps. That's what we did. Next slide, please. And look at the final bullet here. That's the confidence set. So we have a point estimate when you have T, so defined here. And there's a dispersion matrix sigma T. And finally, this is the beautiful confidence ellipsoid, the unknown vector. So you have 2 solutions now. One is the last sample solution I showed you earlier, a few slides back. And now you have the solution here, confidence set based on the generalized p-value. So this is an approximate solution. And the one I showed you earlier is the approximate solution, last sample solution. Okay. So these are the 2 solutions for the confidence set. Next one, please. We applied this to, of course, you can have many applications. So one application here is we are looking at some counties in the state of California, and we are looking at the bivariate data. I think one was the income and two sources of income. We are looking at the data, so they are the counties here. And see that the sample size is very large, so that we can apply the last sample theory and the approximate solution also. And we have the data in the form of bivariate sample mean vectors and the 2x2 Wishart matrices. And we can use it applying the theory. So next one, please. The last sample method, which is based on the generalized, which is based on the Gray-Milldin estimate. So the confidence set looks like this. And the next one, please. And the generalized p-value method, generalized p-value method, confidence, very nice, nice confidence set. Of course, now so we can compare also, because we can compute, probably we can get the expected volume, because the volume will be random. So you can compute the expected volume and you can compare them. So that is another idea also. Next slide, please. Now that we are dealing with multivariate normal, after all, normal theory has been so well developed over the last 60, 70 years, why approximate? Why not something exact procedures? Okay, so that's the idea of the second half. What you can do in the context of the multivariate normal mean vector, the natural thing to look at is the Hotelling-T-square test, Hotelling-T-square statistic, standard definition, and there's a standard rejection criterion here, and the confidence set, everything is known based on Hotelling-T-square, except that here I'll have not just one T-square, I'll have, because I have k normal populations, so I have the data from each of these k populations, so I'll have T-square 1, T-square 2, T-square k. So there will be k independent Hotelling-T-squares, and then my last bullet here is how do I efficiently combine the F tests based on T-square or the corresponding p-value. They are equivalent. So how do I combine the test procedures based on t squared 1, t squared 2, t squared k, right? Because after all, they're all addressing the same question, namely there is a common unknown mean vector mu. And I do have information about me from each of these k populations. So natural thing would be to combine. So that's what we are going to do. We are going to suggest various ways of combining Hoteling's t squared test based on either f or p. And there is no approximation here. All of them will be exact test procedures in the multivariate case. Okay. Next one, please. And I think Dr. Kifle mentioned the same ideas in the univariate case. So it's a matter of just extending from the univariate to the multivariate case. So first thing, we can have a linear combination of Hoteling's t squares statistics, called it a capital T, and based on that we can have a test procedure here. Next one, please. When it comes to the p-values, we can compute the p-values out of Hoteling's t squared test procedures. Then we can combine the p-values. There's so many p-values. One is the t-patch test. So here will be the rejection region. I reject the value if something like this happens. Next one, please. In the Wilkinson's test, instead of the smallest, we can take any intermediate order statistic, intermediate p-value, so RH smallest p-value, and then the test procedure is given by this simple idea here based on the beta distribution. The next one, please. We can have the inverse normal test to convert each p-value to a standard normal, and we can combine this way, and we can have a test procedure based on the inverse normal idea. The next one, please. And of course, by far the most widely used is the geometric mean of the p-values, which in another form is the -2 log p. So we can use this. So all these are various test procedures, exact test procedures to combine the TIs to the p-values. So these are the test procedures, and what we can do, next slide please. To get confidence set, all you have to do, instead of the rejection set, you look at the acceptance set, and then you can convert. That's the direct connection between an acceptance set and the confidence set. So you can use that. So these are all the various. So earlier I showed you the two confidence ellipsoids based on the Grable-Deal estimate and the generalized p-value idea. But now we have 5 more. So in all we have 7. We have 5 more confidence sets. And these 5, there's no approximation here. They are all exact procedures and exact confidence sets. So when you have so many of them, naturally, first thing is if I look at the data set, let's see how they how they look. That's number one. Number two, I really want to compare these different confidence sets. So one way to compare will be, you have a confidence set, you can compute the volume. The volumes are going to be random because everything is based on the data. So you can compute the expected volume. That is one way to compare confidence sets or confidence intervals. You look at the confidence interval or the confidence set, you compute the volume. In the multivariate case, compute the volume and then compute the expected volume. That's one way to compare. Other way to compare will be the test procedures directly. So I can look at the power of the test procedures. But in the multivariate case, power means really power in which direction and so on. It's very hard to compare the power in general. So what we do in the multivariate case, we compute the power locally. So local power. So take an alternative very close to the null, and then we can compute the local power, and then we can compare. Okay. So that's what we are doing here. Next one, please. Yeah, comparison of local power. Then when it comes to comparing local power based on Hoteling's t-square, the natural thing will be the non-centrality parameter. In the case of Hoteling's t-square, is the non-centrality parameter this. Of course, in our case, we will have delta square. There's a common mean vector mu, and there's a mu0 here. But we will have k different non-centrality parameters because of sigma. It will be delta square 1, sigma 1, delta square 2, sigma 2, and so on. Not only that, we have sample size n, so it will be n1, then sigma 1, n2, sigma 2, and so on. So it will be k non-central parameters. Of course, all of them dealing with the same. There's a common mean vector. So this part is the same, but we will have n1 and sigma 1. There will be several non-central parameters. Doesn't matter. So you are going to compute the local power. Okay. So there are two scenarios. The general case will be when the sample sizes are unequal, and the second case will be when the sample sizes are equal. Only the sigmas are different, but the sample sizes are the same. That's the special case. And you can use some technical lemma here. You can have the expansion of the power function, and finally you can compute the local power. Next one, please. Yeah, so this is kind of little bit of course, it's a multivariate case. You can expect some sort of kind of complicated expression. That's very natural here. So you can compute the local power in the general case. And the next one, please. Yeah, and the special case when the sample sizes are the same. Something nice happens here when the sample sizes are the same. So the parameters delta squared, because they are different because of sigma I, but the role of sigma is only in the blue term here. The rest of this is a constant independent of sigma, and because the sample sizes are the same, there is a common sample size, so there is no sigma here, there is no sigma here. So it's the unequal sigmas, they are only in this common part, which means in this special case, it is possible to compare the local powers. All I have to do, I have to consider they are all alpha plus local power, alpha plus something, very small, a tiny part, because delta square is assumed to be very small. That's the shift from the null, assumed to be very small. So it is alpha plus something, and all you have to do in this special case, you have to compute to these quantities and compare. So we have a uniform comparison irrespective of the unknown dispersion matrices. So all you have to do, I just compute these 5 quantities, and I compare which one is the largest and so on. So that's nice. So we noted that in the case of equal sample size, a uniform comparison of local power is possible, irrespective of the values of the unknown dispersion matrices. Okay. All right. Next one, please. Yeah, so you do some computation, and the next one, please. Then you find out that the Jordan-Krishnamurti test, and some tests are they stand out. So you can have take a look at these tables and so on. Next one, please. Okay, going back to that, this is the bivariate data set that California counties. We have data from 3 counties, and if you look at the sample size is pretty big. So you can apply the Grable-Dill estimate, which is based on large samples. We can apply the generalized p-value. We can also apply these 5 or 6 test procedures which are exact. And we can see what kind of solution we get. And as a statistician, it's good to have an arsenal of tools, so that you're not restricted to applying only one method. It's good to have this flexibility that we have so many methods we can apply and we can suggest to our clients. So it's good that way. So if we apply, let's see what we get. Next one, please. This is this one. This is the Jordan-Krishnamurti method. They're all exact methods now. Next one, please. The generalized. This is the inverse normal method. Okay. The next one, please. Let's look at the similarity. Then this is the Fisher's method. Very good. Next one, please. This is the Tippett method, which is the smallest p-value based method. And the next one. This is the Wilkinson's method, taking R is equal to Wilkinson's is the intermediate order statistics. In our case, we have three counties, so we can have the minimum or the second or the maximum, the 3 of them. So this is the R is equal to the intermediate order statistics. It's interesting to note that the confidence set here is not quite an ellipsoid, and it's a very, very funny shape. And next one, please. This is the last sample method, which is the method based on the Grable-Deal estimate. And the next one. This is the generalized p-value method. Now we can put all of them together in one slide. Let's do that. Next one, please. Yeah. So when it comes to data analysis, we can apply some last sample methods. Yes. Tulsi, go ahead. Yeah. Do you have any question? Okay, let me continue, then you can ask. So if we put all of them together, that's the kind of thing we had. So you can suggest to our clients that yes, we have a lot of technique. More or less, they are there. Of course, there's some subtle comparison is there in terms of local power. I think in terms of local power, two of them will stand out. One is the inverse normal method, another will be the Jordan-Krishnamurti method. Marginally, they are better. Next one, please. Well, the technical results here basically because we are dealing with the developing the local power based on Hotelling-Stee square. Hotelling-Stee square is essentially F. So naturally we need to have the non-central. This is the central F under the null, and this is the non-central F, and we have to have a local expansion of the non-central F. So non-central F PDF, and we look at the local expansion. The first term will be when delta square is 0, and then the second term. So that's what is important here. The non-central FPDF, which is the Hotelling-Stee square under the alternative. So we expand it locally. First term is the null, and the second term we retain terms only up to delta square because the local power. And the whole analysis is based on the contribution from this second term. Okay. You see all the theoretical expressions of local power, they are all based on this expansion idea. Next one, please. Yeah, well, let us not go through the details. The basic idea is the same. All the details, they appear in the next one, please. Yeah, also it's kind of and dry math. You have to go through this exercise to finally get the results. Next one, please. Yeah, next slide, please. Yeah, if you're interested, you can send us an email. The details appear in a technical report. So that's all the details are here. All the derivations and everything. Next one, please. Okay, some of the references are here. This is the paper by our Taiwanese friends, Li, Lin, and Wang. This nice paper in JSPI. Very, very nice paper. Next one, please. Yeah, some other references here. This is the book on generalized p-value by Sam Wearhandy. And there's the nice paper, 1989 paper. Next one, please. Okay. So let me end my talk with every day I remember my colleagues with a lot of pride. My colleagues in the first row, they're all from the background from the Indian Statistical Institute. Thomas Mathew and Agnes Mitchell on Indoroy. And our campus believes in diversity. So the unity in diversity, we have statisticians from Israel, from mainland China, from Korea, Ethiopian friend, Dr. Kifle, and from Vietnam. And this is the only native, Dr. Stanwyck. So that's the stat group at UMBC. Okay. And I thank you for your attention. Okay, thank you.
It is a good presentation. It's a motivation. His Professor talk is motivated to
young researchers, young minds. Now, I request professors, you please interact with some more time is available, some 3 or 4 minutes. So please interact with the browser. Browser is any query, any ideas, he will definitely clear your ideas and your issues. Please interact with the browser. It is a very good, great opportunity. Professor Satish Kumar has created a great opportunity for interact with such a great professor. Please.
Sometimes they feel shy also. Anyway, if you have any questions, you can always send me an email. You can reach out to me later. Okay.
I expect some of the young scholars, please. It is a great opportunity to interact with the professor. Bimal Shinko is a great professor. It's a wonderful topic. It's a lot of research.
Somebody raised there, but I don't know. I don't see that person anymore.
Professor Satish, if no query, we will wind up the session.
Oh, okay, Professor. If there is no query, let us wait 1 or 2 minutes to yeah. Kalaram sir, we want to add anything or say? Okay.
I think I'll wait to hear from Dr. Mathu now, right?
Oh, okay.
So yeah, I take this opportunity to thank Nikhil for displaying the slides on my behalf. Thank you, Nikhil.
Thank you, Professor. If anybody is interested, please send the mail. Professor is clarify your doubts and queries and further research problems. He will motivate the young scholars, please. Now, with the permission of Chair, we will thank on behalf of organizing committee and behalf of University of Department of Statistics, University of Kerala, Tamil Nadu, India. Please, thank you once again for sparing a wonderful talk in this great evening. Thank you, Professor. Thank you. Thank you for all experts and all young scholars. Thank you for passion. Thank you.
Thank you, Professor Sindame Kannan, for chairing this session in a very beautiful way. And Professor Sinha for your wonderful talk. Thank you so much. No doubt several are enjoyed your talk, and a lot of things are there because just before Professor Kepler.
Particularly, Professor Gopal and Professor Harijit is enjoying your talk, Professor. And behalf of him, thank you very much. Both of us enjoyed your wonderful talk. Thank you.
Really benefit to the researchers that working in that group. No doubt about that. Thank you. On behalf of the Department of Statistics, University of Kerala and the School of Physical and Mathematical Sciences, and on behalf of the organizing committee, we would like to extend our heartfelt gratitude to Professor.
Thank you.
Professor Sindame for chairing this session.
Thank you.
Professor Gopal, Professor Thomas Matthew are there in the group, and there are several other professors. In fact, everyone is anxiously now waiting for the next talk from our professor, our alumni, in fact, Professor Thomas Matthew. Let me to please, Anjana, without wasting time, let us go to the next session. Even though this session is at 8:35.
Yagan Thomas, good evening, Professor. Yagan Thomas.
Yeah,
Good
Yagan.
evening.
Yeah,
Good evening.
Good evening.
Good evening.
So may I?
Yeah, Professor Yagin Thomas sir is there to chair the session. Anjana, please introduce our chair, Professor Yagin Thomas sir, to the audience, to the participants, and to this gathering. And please help the chair to further proceedings of this session.
Sure, sir. Warm greetings to all. We are moving on to the technical session 8 of ICSTC 2022, which is a special session in honor of Professor Eliama George that shall be chaired by Professor Yagin Thomas. Now, Professor Yagin Thomas is a faculty at the Department of Statistics, University of Kerala, India. He was the Emeritus Scientist of Kerala State Council for Science, Technology and Environment from 2016 to 2019 and Professor Emeritus in 2013. He has more than 1,000 citations and numerous research publications to his credit, including on some modeling problems of statistics, as well as applications of ranked set sampling in estimating parameters of Morgenstern type bivariate logistic distribution. Dr. Yagin Thomas has always been a man of distinct vision and a constant source of support in all our events. So it is with great pleasure that I cordially invite you, Professor, to chair the session. So over to you, sir.
Yes. Warm welcome to all to this very important session of this conference. And regarding this this section, I am happy to announce you that the speaker is Professor Thomas Matthew, a prestigious alumni of the Department of Statistics, University of Kerala. He frequently visits our department and give inspiring talks to students of this department. Some years back, he stayed a week in Karyavattam to give special talks about his research work as an erudite scholar. He earned his PhD from ISI Calcutta during 1985. His current research interests include statistical methods for analyzing exposure data, calibration problem, and tolerance regions, inference in linear mixed and random models, and univariate and multivariate bioequivalence testing. He is the author of a book published by Wiley with the title Statistical Tests for Mixed Linear Models. He is also about to publish a book on statistical tolerance regions. He has to his credit more than 120 research publications and about 2,000 cited about his work. So, with all these things, I need not explain his association with the professional bodies, his involvement with so many statistical activities, and all those things goes naturally with this important statistician who is working as a senior professor in the University of Maryland, United States. I am very happy to invite him to this 8th session of this conference. He will be talking on inference on the drug interaction index based on binary response data, a fiducial solution. And this is a very important area of research in medical studies, because in most of the medicines, when we look in the net, we will notice that the response studies regarding this the interaction of this drug with other drugs is not studied fully. So this type of researches will definitely help humanity in the apt treatment of diseases by different types of drugs. So on this occasion, Professor Thomas Matthew, come forward and present your talk.
Okay, let me thank Professor Yagi Thomas for that nice introduction. And I want to thank Professor Satish Kumar and the conference organizers for inviting me to make this presentation here. Actually, I feel especially privileged and honored to speak today because, first of all, as already pointed out, I am an alumni from that department. And secondly, two of my teachers and professors are in the audience. Kalyana Raman sir was my teacher when I was doing a master's there. Sir, I'm really privileged to have you in my audience. And the previous speaker, Professor Bimal Sinha, is my senior colleague, teacher, mentor, and friend. So it is a real privilege to speak in this session following the presentation by Dr. Sinha. And Dr. Sinha briefly mentioned about the generalized pivotal quantity. I will also briefly touch upon that. So I thought that was quite nice that he mentioned it in his talk. Okay, let me start sharing my slides. All of you can see the slides?
Yeah, it is coming, Professor. Yeah, now.
Okay.
Yeah, now it's fine. Professor.
Looks good?
Yeah, we can see. It's clear.
Okay, good. So this is actually joint work with Xiaoshu Feng, who was a graduate student. She finished her PhD sometime back. And a former colleague, Kofi Adragni, who left our department. This is joint work with both of them. I'll start with an example to introduce you to the topic of drug interaction index. Then I will drug interaction. Then I will introduce you to what is called the interaction index, which is used to quantify interaction between drugs. Then I will introduce you to what is called a fiducial quantity, which is basically what Dr. Sinha mentioned, generalized p-value, or it is also called a generalized pivotal quantity. I will introduce that using a very simple example, that of the univariate normal. Now, I am going to talk about binary response data today. So I will be using logistic regression. So I will explain to you the construction of fiducial quantities under logistic regression. Then we will go back and look at the computation of a confidence interval for the interaction index based on the fiducial approach. Discuss some coverage probabilities so that we know how accurate is the procedure that we developed using fiducial quantities. Then I will illustrate the methodology by going back to the example and analyzing that data. And I will conclude with some references. Okay, so what exactly is the interaction we are talking about? So this example is taken from this 2000 paper. And the example deals with, you can see the title, Departures from Additivity in Drug Chemical Combinations. So when two drugs are combined, basically to treat the same thing, by the way, for example, in this paper, they are talking about combining two what are called analgesic drugs. That means these are drugs used to relieve pain. Tramadol. Tramadol is used for treating for pain relief, mild to severe pain, especially following surgery. And the acetaminophen, this is, we all know, the paracetamol, Tylenol, and so on. That is acetaminophen. So the question is, if you combine these two pain relievers, tramadol and acetaminophen, is the combined effect more or less than what you would get if you take only one of them? So this is the problem. So this article appeared in the Journal of the Agricultural, Biological, and Environmental Statistics, and the paper actually has reproduced the entire data from this study. So the study was carried out using mice. So these mice were given either tramadol alone, acetaminophen alone, or combined doses of both of them. And after half an hour, you verify if the mice is exhibiting any sign of pain. And the sign of pain is assessed by checking if the mice is showing if there is any abdominal constriction. That means severe tightness of the abdomen. So the mice will twist and turn. That will be an indication of pain. So the question is, so you give the mice, you inject the mice with this chemical, acetylcholine bromide, and then you also give them these two drugs and verify if the mice are exhibiting any sign of pain. So this is going to be binary response data. That means either a mice exhibits pain or it does not, 1 or 0, 0 or 1. So you observe the mice for a 10-minute period. So after 10 minutes, the effect of this is probably gone. This chemical is gone. And if there is pain, the mice will twist and turn. There will be arching of the back, extension of the limbs, and so on. That means there is a severe abdominal tightness. So if there are no constrictions, that means the drug is effective and they got pain relief. So 1 will correspond to pain relief. 0 means no pain relief. So each mouse was used only once. That means you have independent observations. So we talk about several replications. That means several mice were used to collect the data. So notation-wise, I'm going to use M and MI to denote the number of mice that received a certain dose of these drugs. And R and RI, these are the binomial responses, the number of positive responses. So we have the binomial distribution. Now these drugs were administered in different doses. So the probability of a positive response or the binomial success probability will now depend on the dose level. So we are going to use logistic regression to model the probability as a function of the dose. So this is part of the data. The entire data is produced in that article. Let us see what this data is about. So in the first few observations, tramadol alone is given, acetaminophen dosage is 0. Tramadol alone is given. So when the tramadol is 2 units, it was given to 15 mice. 3 of them showed pain relief. Then tramadol 6 units given to 45 mice, 20 of them showed pain relief. So you increase the dose level from 2 to 16 when tramadol alone is given. And if you carefully look at the data, you can see that the percentage of positive responses or the percentage who got pain relief, it slowly went up with the dosage. Now, the second set of data, you are giving acetaminophen alone, starting with 30 and increasing all the way up to 400. Again, you can see the proportion who got relief is actually going up. And then you are giving combination of both of them. For example, 0.5 of tramadol, 50 of acetaminophen given to 60 mice. 12 of them showed pain relief. And you have various combinations here. The question is, when combined, do these two drugs interact? Maybe at certain dose levels. So the interaction could depend on the dosages used. Okay, what does that mean? So what that means is, okay, let us look at this 7.5 and 7.5. So when each drug is given 7.5 units each, given to 30 mice, 24 of them showed pain relief. Instead, suppose I give 15 units of tramadol alone or 15 units of acetaminophen alone. Will the percentage getting pain relief more or less or the same? If the percentage is the same, we say the two drugs don't interact. The percentage could be more, percentage could be less. So we are going to come up, exhibit a parameter that will capture this idea of the interaction. Now, I want to mention here that interaction as understood conceptually is the same as interaction as we talk about, for example, in analysis of variance when you have factorial experiments. However, the way this is modeled and analyzed is very, very different from what we do there. A very interesting aspect of the problem, and also very something that makes it very practical and important, is that you never model the probability of a positive response corresponding to a combination dose. That is a major feature of this work here. Okay, so let's look at D1I and D2J. These are dose level of single dose administrations of the two drugs. X1I and X2J, the number of positive responses. That means the number of mice who got the pain relief. Remember, this is for single dose administrations, not a combination dose. So pi1I will denote the probability for pain relief when a mice is given tramadol alone at dose level D1I. So you have logistic regression here with the intercept beta 0, slope beta 1, and this is the natural logarithm of the dose level. Pi2J similarly is the probability of a positive response when the second drug, acetaminophen alone, is given. You notice that there's a common slope beta 0, because if the dose level is 0, then these probabilities should both be the same. That is why there is a common slope. Again, as I just mentioned, the modeling is done only for what I would call marginal response rates, not marginal probability in the usual sense. That means only when one drug alone is given. So the probabilities, the modeling is done, logistic regression is done only for the individual administration of the drugs. In other words, when a combination dose is given, we are not going to use a model. We will collect data, but we will not use a model. Okay. Now the interaction index, this is a parameter or a criterion that is used to assess the possible interaction between the two drugs. This is based on what is called a Loew additivity model. So this goes back to the work of Loew, long time back actually. I don't remember the actual year, probably in the 1940s or 50s probably. He did something very, very clever. So here is what he says. If the drugs don't interact, then giving a combination dose D1, D2 of the two drugs should be equivalent to a dose of D1 plus D2 of any single drug. So this is the argument he used in order to develop a model and also something called the interaction index. So lack of interaction means a combination dose is equivalent to a single dose consisting of their sum of any single drug. This is the argument he used. All right. So let's do the following. Let us fix a success probability or a response rate equal to pi. And suppose d pi1 is the dose level of the first drug, tramadol, that will produce this response rate pi. So the success probability is fixed as pi. It will, of course, depend on the dose level. So d pi1 is the dose level of the first drug that will produce this response rate pi. Similarly, for the same response rate pi, d pi2 is the dose level of the second drug. So this means, if you look at the ratio d pi1 over d pi2 units of drug 1, it will produce the same response rate as 1 unit of drug 2 if there is no interaction. If there is no interaction, the drugs behave in a similar manner. So d pi1 is the dose level to get a response rate pi for the first drug, d pi2 for the second drug. So d pi1 over d pi2 units of drug 1 will produce the same response rate as 1 unit of drug 2. In other words, in the absence of any interaction, a dose combination d1, d2 of the two drugs is equivalent to d1 plus d2 times d pi1 over d pi2 units of drug 1. Basically, this simple algebra follows from the argument given above. So this is the amount of drug 1 required in order to get a response rate of pi in the combination therapy. All right. But we already know d pi1 is the dosage level of drug 1 to get a response rate pi. That means this dosage should be equal to d pi 1 in the absence of interaction. This is the argument that Loew used. You divide with the d pi 1, you get this equation here. d1 over d pi 1 plus d2 over d pi 2 equal to 1. So the quantity on the left-hand side is called the interaction index. This is referred to as the Loew additivity model, a very, very popular model in the investigation of drug interaction. If you go through the literature on this topic, you will see that many conditions that or treatments, surgery or whatever, that can produce severe pain. For example, some of the cancer treatments, very often a combination therapy is used so that the pain relief will be much better. And before they do that, they test it if there is interaction or not. Okay, I'll make it more precise in the next couple of slides. So I have given a quote from this paper. It says, we conclude that the Loew additivity model is one of the best general reference model for evaluating drug interactions. Again, you keep in mind, we did not assume any model for the response rate when you have a combination dose. And that is what is very important here. There is research on this topic where people also assume appropriate logistic regression models corresponding to the combination dose, but none of them is as popular as the Loew additivity model, because then that becomes an additional assumption. See, the logistic regression is a well-accepted model, but when you have a combination dose, the question comes up, how do you express the logistic as a function of D1 and D2? Is it simply adding, or should there be a product term, etc., etc.? So it becomes a little bit problematic because of the additional assumptions. So these authors review a lot of work on the until 2007 on the testing drug interaction, and they concluded that the interaction index is the way to go if you want to study interaction between two drugs. And you can see very easy to extend it to more than two drugs. If you have 3 drugs, just you add one more term. That's it. Okay, now let us see. So this is equal to 1. That corresponds to no interaction. Now keep in mind, D1 and D2 are dose levels which you can decide. The d pi 1 and d pi 2 will depend on unknown parameters. It will depend on pi, and it will also depend. Why is pi unknown? Because we don't know what the response rate will be corresponding to the combination dose D1, D2. And the d pi 1, the dose level required to produce a certain response rate, will depend on the logistic regression parameters. Okay, continuing. Now, suppose this is less than 1. If this is less than 1, then the combination dose, right? The combination therapy requires less amount compared to a single dose administration of drug 1. That means the interaction index will be less than 1. So that means the combination dose is as effective as lesser amount of drug 1. So in other words, if I use a combination therapy, and it is more beneficial, this is referred to as drug synergy. And we say that the two drugs, they interact, and they interact synergistically. You can have the converse, and that is referred to as drug antagonism. The two drugs interact and they act antagonistically. So that means the combination dose to produce a response rate is more than the amount of a single drug applied to produce the same response rate pi. So basically our problem is so if there is interaction or not, the problem will be to test if this parameter is equal to 1. Or you may want to test if they act synergistically. That means you want to test if this parameter is less than 1. Or antagonistically, the parameter is more than 1. So here it is in summary. D1 over d pi 1, d2 over d pi 2, the interaction index equal to 1, no interaction. Less than 1, interaction but synergy. More than 1, interaction but antagonism. And remember that the interaction index criterion depends on the dose level D1, D2, and also a function of the logistic parameters and the response rate pi. So I'm going to address the computation of a confidence interval for the interaction index using the concept of what is called a fiducial quantity. Remember that whether two drugs interact or not depends on the dosages used. At some dose levels, drugs may interact. At some other dose levels, they may not interact. By the way, if anybody got any questions, feel free to interrupt me and ask. Okay. Now, Dr. Sinha mentioned about a generalized p-value. There is also a generalized confidence interval based on what is called a generalized pivotal quantity. There are special cases of what is called a fiducial quantity, which goes all the way back to Fisher. Now there is a revival in fiducial inference. I will give you some references shortly, because it so happens fiducial inference can handle many complicated parametric problems when traditionally the only solution available to you is a large sample approach. Okay, let me introduce you to fiducial inference using the simplest example you can think of, the univariate normal. Let's say you have a sample size n from normal mu sigma square. You have the sample mean and sample variance, x bar and s square. Now I'm going to distinguish the random variables, capital X bar and s square, and the observed values, lowercase x bar and s square. So lowercase x bar and s square, they are just numbers computed once you have the data. Now here is the t statistic, dfn minus 1. Obviously, once you have observed data, you compute the value of t, and then you can use the t percentile, simplify, get confidence interval, carry out test, and so on. Here is what we are going to do. Keep t as a random variable having the t distribution. Replace capital X bar and capital S with the corresponding observed data. So this simplifies like this, and solve for mu. Here is the solution. I will call that mu tilde. So mu tilde is the sample mean, just a number observed from the data, minus capital T, the t statistic, times the sample standard deviation observed from the data over square root of n. This is what you call a fiducial quantity. Remember, when you want to compute a confidence interval, usually you do need the distribution of a pivot. You need a pivot. You also need observed data. The only difference here is you have combined everything into a single quantity. The observed data and the pivot, the random variable, you combine them into a single quantity. For convenience, I'm going to replace the minus with a plus because the t distribution is symmetric around 0, so it doesn't matter. So we'll call mu tilde. Actually, you can keep minus itself. Doesn't really matter. We call mu tilde a fiducial quantity for mu. You can compute the percentiles of mu tilde, essentially amounts to computing percentiles of capital T, because the x bar and s are just numbers. So keeping the observed data fixed, you can compute the percentiles, and those percentiles will give you confidence limits for mu. In this case, it simplifies to the usual student's T confidence interval. So in other words, going by the fiducial approach for the univariate normal mean, it has not produced anything new right now. It just produces the usual student's T confidence interval. Okay, we'll come to that. You can do the same thing for the population variance. You scale the sample variance appropriately, you get a chi-square, and then you look at, you solve for, you replace S square with the corresponding observed data, solve for sigma square. Here is sigma tilde square. It involves observed data and the chi-square random variable, and we call that a fiducial quantity for sigma square. Again, this will produce the usual chi-square confidence intervals for sigma square, nothing new. So is there anything new? To see why this is powerful, let us look at the log normal distribution. So that means x is log normal, y is log normal if the natural logarithm follows the usual normal distribution. So suppose I have a sample from the log normal. So if we take the logarithm, I get a sample from the normal. So you compute the sample mean and sample variance corresponding to the log transform data. That is my capital X bar and capital S square. Based on these two, I can compute fiducial quantities for mu and sigma square. We will call them mu tilde and sigma tilde square. Now the log normal mean is given by exponential mu plus sigma square by 2. In other words, if I want a confidence interval for the log normal mean, I need a confidence interval for mu plus sigma square by 2. All you have to do is replace mu with mu tilde, sigma square with the sigma square tilde. That will give a fiducial quantity for mu plus sigma square by 2, which I am denoting by eta. And you can re-express it in terms of the standard normal as well as the chi-square random variable, both of which are independent. So the quantity you see here, eta tilde, is a fiducial quantity for eta, and it is a function of the observed data x bar and s, and it depends on two independent random variables, a standard normal z and a chi-square u square. So computing the percentiles of this is very easy. Simulating the percentile is very easy. You just have to generate a standard normal and a chi-square, that's it. And compute this, let us say 5,000 times, get the percentile, that will give you confidence limits for eta. The interesting thing is, this is highly accurate, highly accurate. This is the reference due to Veerahandi's paper. Dr. Sinha also cited some of his work. This is what Veerahandi would call this a generalized pivotal quantity. It is nothing but a fiducial quantity that Fisher spoke about. We investigated this, Krishnamurthy and myself. Dr. Sinha also cited some of the work by Krishnamurthy. We noticed that this is highly accurate, starting with sample size 3. It is practically exact, very simple to implement. You have to numerically obtain it, but doing a Monte Carlo simulation to compute those confidence limits, very, very simple and straightforward. I mentioned earlier that the fiducial inference is now has gained some revival now. Actually, Veerahandi is responsible for that, but the fiducial quantity has been put on a very firm theoretical basis, noting a lot of applications by Hanik in 2009, and a lot of other papers by Hanik and co-authors. This is a long paper, about 50 pages in Statistica Silica, 2009. If anybody is curious to read about fiducial inference, this will be a good paper to read. Very good review, talks about computation, extensive list of examples. Now, in my problem, I have logistic regression. Now I mentioned, let me check what is time. Okay. I mentioned that we have this fiducial quantity mu tilde for mu. That means if I compute the, I can compute appropriate percentiles, mu had u for an upper confidence limit for mu. And you can simplify that. That will become the usual upper confidence limit based on the t. So as I already pointed out, the percentiles or the fiducial quantity will provide you confidence limits. And the observed data is fixed in this derivation. Now, we have this connection between the binomial CDF and the beta distribution. So we are going to exploit that to compute a fiducial quantity for the binomial success probability pi. So here B delta 1 delta 2 denotes a beta random variable, and K will denote the observed value of the binomial random variable X. For example, we know that the CDF of X is actually the beta random variable with parameters K plus 1 and N minus K greater than or equal to pi. So that is the binomial CDF. So if this is the 1 minus the CDF, again, you have a representation in terms of the beta random variable. You notice you have a random variable beta distribution, which depends on the observed data K. Very similar to what we do here. There's a random variable. It involves a random quantity T and the observed data X bar and S. So actually, these two beta random variables, Bk n minus K plus 1 and Bk plus 1 n minus K, you can take both of them as fiducial quantities for pi. Both of them are appropriate as fiducial quantities for pi. So what we will do is, we will pick one quantity as a fiducial quantity for pi, something that is stochastically between these two. And that will be beta K plus half n minus K plus half. Remember that K is the observed value. So Krishnamurthy is somebody who has worked quite a bit on fiducial inference. I have also collaborated with him, and this is the idea that he proposed. Actually, this goes back to an old paper in biometric in 1950, how to compute fiducial limits for binomial and Poisson. Okay, so this is our fiducial quantity for the binomial success probability, K being the observed value of the binomial random variable. Now we are in logistic. Okay, so suppose I have the response rate pi I corresponding to a dose level Wi. Wi could be the log dose. And let us say you have mi binary responses corresponding to the response probability corresponding to the dose level Wi. And Ri is the number of responses equal to 1. That means the observed value of the binomial corresponding to the response probability modeled as logistic. Then a fiducial quantity for pi I, what we just saw, will be the beta random variable with the parameter Ri plus half, mi minus Ri plus half. But keep in mind, I am not interested in a fiducial quantity for pi I. I want fiducial quantities for the parameters beta 0 and beta 1. So here is what we will do. And we will denote them by beta naught tilde and beta 1 tilde. Yagin Thomas, sir, how much more time do I have? Hello? How much more time do I have?
Yeah, Professor, Yagin sir, you is unmuted. Please unmute. It's muted, Professor. Yagin sir, please unmute your mic.
You can take 12 minutes more.
Okay, no problem, no problem. Oh, that's all I need. Okay. So I need fiducial quantities for beta 0 and beta 1. I'm calling them beta naught tilde and beta 1 tilde. I have a fiducial quantity for pi I. So we'll write pi I tilde, the fiducial quantity we just got. Remember, this is pi I tilde. I'm going to express it as a function of beta 0 tilde and beta 1 tilde. This is at the covariate value or dose level Wi. Now, suppose I have R different dose levels. Then I will have R different equations like this for the same beta 0 tilde and beta 1 tilde. You do the logic transformation, then it becomes like linear regression. The fiducial quantities to be determined are beta 0 tilde and beta 1 tilde. So you just do a least squares. Least squares based on this. I know what is pi I tilde. It is a beta random variable involving the observed binomial quantities. So do least squares, that will give you beta 0 tilde and beta 1 tilde. So this is how we obtain fiducial quantities for logistic regression. Now let us go back to the interaction index. So I'm going to denote that by tau, D1 and D2, specified dose levels. Now pi, this is the unknown response rate when a dose combination is administered. Again, remember, no model is assumed about pi. It's a very important point actually. I'm emphasizing it again and again. So d pi 1 and d pi 2, dose level for drug 1 and drug 2, that will also produce the same response rate pi. So this is what I'm doing. I'm going to administer a combination dose D1, D2 to a patient. That will produce a certain response rate pi, which I do not know. Corresponding to pi, there is also the dosage of drug 1 and drug 2 that will produce the same response rate pi. So pi is unknown. D pi 1, D pi 2 will depend on the logistic parameters. Suppose I have m response rates corresponding to the dose level D1, D2. So this m response level corresponding to the combination dose, again, I have binomial distribution there. So I can compute a fiducial quantity for pi tilde, using that beta relationship. Then pi is given by this expression if I'm looking at drug 1 alone, because the dosage is now d pi 1. This will give me an expression for d pi 1 right here. So I already have a fiducial quantity for pi tilde. And I know how to compute fiducial quantity for beta 0 and beta 1. I just showed you that. So that will give me a fiducial quantity for d pi 1. I will call that d1 tilde. I can do the same for d2 tilde. Once I have fiducial quantities for d pi 1 and d pi 2, I have a fiducial quantity for tau. There it is. So this is the fiducial quantity for tau. So you notice there is no MLE calculation or anything, right? We are just using the observed data of the binomial responses along with the that beta random variable. So simulating the percentiles of this, very, very easy. And the percentiles will give you a confidence limit for the interaction index. So what is available in the literature is large sample results based on normal approximation of the MLE of tau or that of the natural logarithm of tau. Actually, the natural logarithm of tau gives a slightly better normal approximation compared to the MLE. Okay, now let us see how good the solution is. So apart from what is available in the literature, we have produced another solution by using the fiducial approach. So I'm going to compare 3 methods for computing a confidence limit for the interaction index tau. So we carried out extensive simulations. So I'm going to show you just a small snapshot of that corresponding to that example. These are the parameter values for the example, assuming the logistic regression. Remember that these estimates are obtained based on the data corresponding to drug 1 alone or drug 2 alone, because there's no model when there is a combined dose. So we are going to look at 2 sample size situations, the original sample sizes, and then we reduce the sample sizes. So scenario 1 corresponds to the example as given. Scenario 2 is for a reduced sample size. So here are the estimated coverage probabilities and the expected width of the confidence interval when you use a 95% confidence level. So you can see in the setup of the original example, the fiducial method coverage is around 0.95. Normal approximation of tau hat, it is slightly small. Normal approximation for natural logarithm of tau hat, it is better. But what really surprised us is the width. So the fiducial method gives you a confidence interval whose width is significantly less, sometimes less than half of what you would get when you apply the normal approximations. In other words, the fiducial method is giving you better coverage with a shorter interval, something that is quite remarkable. When we first saw this, we thought we made a mistake because this is too good to be true. So independently, my collaborators did the simulations and they got exactly the same result. So this is for a reduced sample size. Again, coverages are quite good and the expected width significantly smaller compared to what is available in the literature. So you get a shorter interval with better coverage. This is what the fiducial method will give you. Okay, I'll quickly go through the example and then conclude. So this is the data I showed you earlier. You can see this interval corresponds to dose level 0.5 and 50. 0.5 for tramadol and 50 for acetaminophen. And the estimate of tau is 1.507. So it is more than 1. It is more than 1. So the fiducial method gives, this is the interval. This is the corresponding interval under normal approximation of tau hat and natural logarithm of tau hat. Clearly, the fiducial method gives you a much narrower interval. You notice that the number 1 is in this interval. Remember, tau equal to 1 corresponds to no interaction, right? So since tau equal to 1 belongs to the interval, for all 3 of them, we had to conclude the drugs do not interact at dose level D1 equal to 0.5 and D2 equal to 50. This is for a different dose combination, 0.5 and 200. Now you can see that the number 1 is not included here and the interval is to the left of the number 1, right? That means the interaction index we have to conclude is less than 1. That means the drugs interact synergistically at this dose combination. Again, narrower interval here as well. So the normal approximation is probably problematic because tau is a positive parameter. The lower limit here is actually negative. Probably not that big a deal, but the natural logarithm gives you a much better interval. Okay, there are 2 books on the topic in case somebody is interested. The second one is an edited volume. Actually, the second one is quite interesting. You see quite a few articles talking about drug interaction in the context of a cancer treatment there. And there are a couple of chapters in this book that talks about the interaction index, the parameter I just discussed. And finally, I already cited this paper by Hanig. This is a more recent article in JASA, again, review of fiducial inference. So this is something that I wrote with 2 colleagues. And this is where we introduced, this is for a bioset application. This is where we first introduced those fiducial quantities for logistic regression. With this, I conclude. Any questions, feel free to bring up.
It is a very nice and interesting talk, useful as well, because the drug industry is keenly looking for studies of this type, as I already informed. Moreover, this fiducial interval is quite ignored, as you said, it is an ignored area. I remember in 1973 to 75, during my studies, there is this topic given in our syllabus for estimation with the confidence interval, another fiducial interval, and these things are included. But the teacher himself told us that not much priority is given to this.
Yeah, I have to make 2 comments on that. First of all, I guess during no, you brought up a good point. During
happy
the,
that
I remember
that
during
is
the
successfully applied nowadays. So we have to, the students can take actually interest in studying these things as well as applying this technique for their problems as well. With this words, let us congratulate Professor Thomas Matthew, and it is time for discussion. Audience, please. Okay.
Again, Thomas sir, I want to make 2 comments on what you just mentioned.
The audience can ask questions with the Professor Matthew.
Yes.
I want to make 2 comments.
Yeah.
The
Kalyan Raman sir.
The 2 comments.
Yes. Dr. Thomas Matthew, very nice that you are associating with our programs. And I just want to
carry on.
Make a clarification. With you made a statement about fiducial quantity of
definitely.
Can you make a little more clear about it? But I would like to get a clarification. What exactly you mean by that? That interaction index itself is an estimate. Am I right?
No, the interaction index is a parameter.
It's a parameter. So you
it's a function of parameters.
Okay. And what do you intend by saying the fiducial quantity of that interaction?
Well, that is a quantity. This is okay. Let me go back. So this is what I presented for the normal. Basically, simply put, what I have is a quantity that involves the observed data and the t-statistic, the pivot.
Oh, yes, this definition is here, yes. Okay.
Yes, and its percentiles will give you confidence intervals.
Okay.
I am doing, see, the nice thing is the following. Okay, Kalyan Raman sir, the nice thing is the following. See, we have a fiducial quantity for the log normal mean.
Okay.
Which is a function of mu and sigma square.
Right.
You can have any function of mu and sigma square, doesn't matter how complicated it is. You have a fiducial quantity. That is the power of this thing. You can have very complicated parametric functions, and yet you have an accurate way of computing confidence limits. No large sample approximation involved. Yeah.
Okay, thank you. All the best.
Thank you. Yeah, I want to make two comments based on the points brought up by Professor Yagin Thomas. One is that there was a time when people used to worry about philosophical issues, Bayesian, frequentist, and fiducial was kind of forgotten in the process. I'm not sure if people bother with such things these days. If something works, use it, right? Something works, use it. And the second thing is that very often you have to compute the required percentiles by Monte Carlo simulation, which is no problem these days. Maybe when Fisher first introduced this, probably computation was an issue. That is no longer the case. Maybe that is why it is picking up right now. Any other questions or comments? If not, I will stop.
Okay, Professor. In fact, okay. Thank you, Professor Thomas Matthew, for your excellent talk and very interesting. And several are, in fact, enjoyed the talk. And we are always grateful to you, Professor. Also, we extend our gratitude to our Guru, Professor Yagin Thomas sir, for chairing this session in a very beautiful way. Once again, thank you, professors, both Professor Thomas Matthew and Professor Yagin sir, for
thank you.
Supporting our activities through your deliberations. We
Thank you.
Continue to support. Yeah, thank you, Professor.
The next there was some interruption.
Okay, sir. Okay.
Thank you.
Now, I think let us move to the next session. It is, there is time, even no problem. But in the next session, we have Professor Gauri Datta and Professor Kibriya. Both are there in the group. And Professor Parameshwar Pandit is here in the group to chair the session. I think we can take some more time. If you have to discuss anything, no problem, or otherwise we can move to the session, because 8 more, some more minutes are there. Just to, I think we can introduce the chair and thereby move to the session without wasting the time of the speakers. That's better. Anjana, please.
Sure, sir. So we have reached the 9th technical session. Sir, am I audible?
Yeah, audible.
Yeah, sure. Thank you.
We can use this time for the introduction part and then move to this. Yeah, please.
Yes, sir. So we have reached the 9th technical session of Icstc 2022, which is a plenary session that shall be chaired by Dr. Parameshwar V. Pandit. Dr. Pandit is the professor and chairman to the Department of Statistics, Bangalore University. His research interests include non-parametric inference, inference on reliability, non-parametric quality control, and SPRT. He obtained his PhD in statistics from Karnataka University, Dharwad in 1997 and has almost 3 decades of experience in the field of teaching. He has co-authored more than 70 papers published in various scientific journals, including classes of non-parametric regression tests published in the International Journal of Applied Mathematical Sciences and estimation of stress strength reliability for transmuted exponentiated inverse Rayleigh distribution, published in the International Journal of Scientific Research in Mathematical and Statistical Sciences. It is indeed with immense joy and honor that I invite you, Professor Pandit, to chair the last technical session of Day 1 ICSTC 2022. So without further ado, over to you, Professor.
Welcome, Professor Pandit. Please carry over the sessions. Sir, you have to unmute the mic. Your mic is muted. Professor Pandit, please unmute the mic. Yeah.
Okay. Thank you, Professor Satish Kumar and his team for giving me this opportunity. So this is plenary session 3, I suppose. Yeah, we have 2 speakers in this session, and the first session is speaker is Professor Gauri Datta, University of Georgia. He will be talking on pseudo-Bayesian small area estimation. I request Professor Datta to start the talk.
Good evening or good morning, because I have to say good morning. I can see my big brother, Professor Sinha, he presented an excellent talk and followed by Professor Matthew. I was, there to enjoy their presentations, and excellent. Yeah, Thomas, thank you. Nice seeing you. We didn't have coffee for a long time.
Oh, we cannot do that virtually, unfortunately.
Yeah, that's right. Yeah, here I have a cup.
Okay. I'll get one myself.
All right. Okay. Thank you. Thank you, Professor Satish Kumar, for inviting me. Hopefully someday, as I was talking to Thomas, that I will visit his department back in India someday. Let's see when things get normal. So now,
Most welcome.
I'd like to share my screen. Let's see if I am successful. Okay. What happened? Let's see. It's working. Something is going on. Let's see. You are, yeah.
Now you can go to the slides, Professor. We can see your desktop.
You can see it, but I cannot see myself.
Yeah.
I do not see it at all, actually.
Now you can select your slides.
If you can see it, that's fine. Let me see if I can go back to. No,
we can see your slides.
And we can hear you, and we can. Yeah, now the
Yeah,
slides.
you can. I understand that, but I cannot see the slides. I mean, I need to see the slide myself. You're presenting to everyone. I want to present to myself also. So I'll stop presenting, then I'll retry again. Sorry.
Start again.
Let's see. Maybe a tab.
We have time, sir. No problem, because we started 2 minutes there. Time.
Not that. This is not working. Let's see, a window maybe. If I
render screen, you can select.
Entire screen?
Yeah,
I tried last time. I tried the entire screen.
Okay.
And
Professor Satish Kumar, if you have the slides, you can just.
I mail you the slides also.
If there is any difficulty, we can share from here. No problem.
Yeah, it's better.
Okay, now it is coming. Now you can select the concealed slides. Go to the slide that file. You can go to that file.
You see the slides, but I don't have any slides for myself.
We don't able to see the slides now, sir. So we can see.
I want to see the slides. Let's see. Okay.
No, yeah.
It is okay. It is coming. It is coming.
Okay. I will present
yeah.
it from here. So you have the slides there anyway. It's part of work with my two of my students, and also I'm part of U.S. Census Bureau, and for that I have to make a general disclaimer. So what you have now, I'm just going through independently through my slides here. So I hope someone can, there is this, the map I am showing, that map of US. It is showing the 4% family median income coming from the 2000 census, the income for the year 1999. And here I have the map of the continental US, and it's color-coded map based on the level of income. And here I have the scale also. The goal is to actually estimate incomes, 4% family median income for each state. And for that, we have the data coming from some survey. And what we are interested in, from the survey, we are getting some number. I'm actually in page 4 of my slides. So what we have, that from the survey, like a national survey, it's called current population survey. From that we have the data, and based on the data we have YI, and theta I is the population characteristics, which is like the median income for the 4% families in state I. And what we have, that usually the survey estimate is sort of unbiased for the population parameter theta I. So we are just, the data sample size computing YI is typically not large. And consequently, the sampling variance for YI will be large, and that might not be a good enough accurate estimate for publication or making policy decision. So what we have, we are interested not only in for one single state, but we are interested in a collection of states, in this case all the states in US. So we have like 51 states including Washington DC. So what we are doing, we are trying to improve on these direct estimates by borrowing information from the neighboring states, as well as from some covariates, which I collectively call XI, and they may be coming from previous census or some administrative data file. So what I have here, we are using some model, and the model is basically, there are two parts in the model. One is that simple thing that, the direct estimate YI is estimating theta I, so there is some error there, and that error I call EI, which is the sampling error. And usually the sample size may not be too large, but whatever, approximately large, and we can assume that YI is approximately normal, mean theta I, and variance in DI, and the variance DI has been estimated, and we assume that estimate is kind of known. And now this unknown theta I, what we think that, they are kind of, they follow the latent parameters thetas, they follow some sort of model, and the variability in the theta i's, their variation can be explained by some covariates, vector. And so these vectors, the covariates are known, and we have some language for simplicity, like a multiple linear regression on the latent parameter theta I. And whatever we cannot explain the theta I by the covariates, that's part of this random error VI, that's the model error. And the second part is called the linking model. So we have these two models, and these two models together, they gave what is called the Fay-Harriet model. And we are assuming the VI is normally distributed, mean 0, and model error variance A. And now we are going to use this model to make inference about theta I to produce more accurate estimate. This is going to be done following Stein's shrinkage estimation idea. So basically, if we believe in this model, that model that I presented here, the slide number 4, that under the normality assumption, if you look at one distribution of the yi and theta I, and we are just going to take some kind of, for prediction, is look at the conditional on what you have observed, which is the data yi you observed. So look at the conditional distribution of theta I given yi, and if you do that, you'll find it's a normal distribution. It has some mean, and the variance is given by a di by a plus di, and the mean is given by this quantity theta I b tilde, which is like the best predictor of theta I, assuming that model error parameters, beta, regression parameter, and model error variance A are known. So that's the best predictor. And if you look at here, what is happening, that we are actually changing the direct estimator yi, we are shrinking it towards the mean regression function xi transpose beta. And the extent of shrinkage will depend on the relative magnitude of the sampling variance di and the model error variance A. However, right now that we still do not know beta and the model error variance, so we need to estimate those things, and we are going to estimate those things from the data. So now I'm moving to slide 6, and so first we will consider that the model error variance is known, and we'll try to estimate beta. And one way to estimate beta is just the weighted least square estimator, or which is under the normality, you can show that this beta m tilde is the maximum likelihood estimator of beta. And in this estimator, if you look at the data pair xi yi for the ith state, xi is fixed, but yi is actually assuming random. So this pair is receiving the weight in this estimate reciprocal of the total variance of the data point yi, di plus a. So if di is large, then that means that yi is less accurate. We are going to give less weight to that pair in estimating beta m. And so this is what it is. Now again, finally, the A is still not estimated. So for this estimator beta m tilde, if we replace that unknown beta in the best predictor I showed you in the previous slides, then what we get is basically this theta I tilde blob. This is best linear unbiased predictor, okay? And still this is not usable because it involves the unknown parameter A. Now we need to estimate this parameter A, and we can do it from using the profile likelihood for A, or using the residual likelihood for A, or there are some other method of moments estimator, namely methods used in the paper by Prasad and Rao in 1990 JASA. So I'm looking at slide 7. So unknown A estimation we are talking about. I'm not providing the details here, but I just mentioned how to get the various estimates of A in these citations here. Now, once I have the estimator of A, I plug that estimator in beta m tilde, and then once we have that, I also plug that A hat in the shrinkage coefficient gamma I A, and consequently what we get is the empirical best linear unbiased predictor E blob. And for in the small estimation literature and for citation, one can look at this book by John Rao and Molina. They extensively consider a derivation of the mean squared error of the E blob and how to estimate that thing. So here, if you look at the way the E blob was proposed, first assuming the model parameters beta A known, we found the best predictor for theta I. And then, since the model parameters are unknown, we just look at the marginal distribution of the data, and from that distribution, we found the best estimator. Maximum likelihood estimator, typically optimal estimator. We get the optimal estimate for the model parameters and plug that unknown parameter in the best predictor. So this is this hybrid kind of prediction, and this has been used in the small error estimation for the last, beginning like mid-70 till 2011. In 2011, Jiang, I'm looking at slide 8. Jiang and his co-authors argued that EBLAP is not suitable, especially for small areas for which the YI is less accurate. I mean, based on less sample size. And his argument, or their argument, is that that unknown model parameter estimation. If you remember, I mentioned to you that beta, that pair XI-YI is receiving the weight reciprocal to the total variance DI plus A. So if DI is large, it will receive less weight, and DI small, it will receive more weight. And they argued, Jiang et al. Argued that that it is the less accurate estimates, they should get more assistance in developing better estimate. And if those estimators do not have a good influence in determining the model error parameters, then which is not the case in the regular EBLAP. So this estimator might not be appropriate, especially in the context of model misspecification. So they suggested, instead of determining the model parameters by maximizing likelihood function based on the data, they said that the whole thing should be based on one single quantity, and in particular they look at sum of squared error loss. Like here I have the summation Ti minus theta I. The theta I is the parameters we're estimating, and based on the quantity T1, T2, Tm, and we, for given parameters, we minimize that loss function with respect to Ti based on the conditional mean, and that's, we have the theta I b tilde, the best predictor I mentioned earlier. And then they look at this total sampling design based mean squared error of the best predictor. So this is now let's look at this. This is a function of the model parameters beta and A, and it was simplified using the expression for the best predictor. There is some simplification of this expectation, the total sampling based mean squared error. And now Jiang et al. And also Rao and Molina, suggested you just look at a quantity that you want to optimize, which is function of both the parameters and the data, and you can do that thing by dropping this this design-based expectation, and then you get a objective function. And basically, you just minimize this objective function with respect to the model error parameter. So if you look at it, first, that best predictor was obtained by minimizing this the sum of square error loss, and then you are also again minimizing the same sort of objective function to determine the model error parameters. And if you do that, so this is the objective function I have like in equation 2, and particularly if you look at the second line in the display, you see that in determining the beta, that beta is in yi minus xi transpose beta square, and you are going to minimize that thing, and the weight to yi you are giving is gamma I square, and gamma I was di by di plus a square, and for larger di you are giving more weight to that yi, and that is precisely the that means that you are giving more weight to less accurate estimator for yi in determining the model parameters. And so you can optimize this parametric this function with beta n in 2 steps. For given a, you get an explicit expression for beta, which is given by this thing beta o. I'm looking at slide 10, and then you replace this beta value in the Q function, and then you get a function of a and then you minimize that thing as a function of A subject to non-negativity, and then together will give you the best predictive estimator of beta NA, and you plug those estimators in the best predictor to come up with what is called the observed best prediction of theta I, and this is the one Jiang et al. Proposed in their paper. So this is actually a frequentist approach. All these EBLAP was also frequentist approach. There is also a parallel Bayesian approach to this problem. And in the frequentist approach, they look at the mean square error approximation and estimation of the mean square error. I am focusing on the Bayesian aspect of these problems. So now I am in slide 12. And here is the regular Bayesian method for the Feherian model. And in this model, what you have, it's just, I'm just rewriting this thing 1 and 2, basically what we had in the very first slides, that yi given theta I is normal, mean theta I variance di, and theta I is second step is theta I given psi is normal, mean xi transpose beta and variance A. And in the Bayesian approach also you have to put prior on beta NA, suitable priors, maybe non-informative priors, or if you have useful information, you can use that. Typically, we use uniform prior for beta and also uniform prior for A. So based on these models, if you know, you can find the posterior distribution for the parameter psi. It is coming from this quantity. Basically, you have to normalize this quantity to get the posterior PJ for psi. And the second step, what is I call post 1, that conditional on the data and the psi, the distribution of theta I is really the normal theta I b tilde, that's the best predictor we had, and the variance matrix A variance posterior variance A gamma I. So to make inference about theta I, what we can do, we first generate psi from the posterior in post 2, and based on the value generated for psi, from post 1 we generate values for theta I, and from those collection of theta I we can make inference about our we can make anything, the median or credible intervals, everything we can create. So this is basically the Bayesian approach. This is called the hierarchical Bayesian model. So there are some similarity and differences among these empirical BLAP, hierarchical based prediction, and overall based observed based prediction. Basically, this is like a two-stage. We did that thing. We had the best predictor, and then in the best predictor, we plug the base unknown parameters in the EBLAP and in the OBP, the unknown model parameters there. And in the hierarchical based case, we basically generate the model parameters from its posterior distribution. So in any case, it is done in 2 steps. It is done in 2 steps. So in the Bayesian version, that what we have in the frequentist case, we, like from the maximum likelihood perspective, that we kind of minimize the negative log likelihood, log residual likelihood to estimate beta and A. So this negative log likelihood that we are minimizing, which is like, in the OBP context, we are minimizing this objective function Q beta A that I showed you before. So now, in the regular base, it is based on the exponent of the negative of the likelihood or residual likelihood, which is basically exponent of L psi, and you multiply it by the prior, and you just update it, normalize that thing. So this is called, basically, you have the prior for beta NA, and you update the prior in terms of the observed data, which is information about those parameters expressed in the likelihood, okay? In the likelihood, exponent of this L psi is the likelihood. So we just and we just get the posterior distribution. Now, when we do not have the likelihood, instead, or negative likelihood, instead we have this, what is called this objective function Q beta A, any non-negative function. How can we use this information and the prior distribution, to update the prior distribution in view of this loss function, which is dependent on the data as well, okay, data and the parameter. And how can we calibrate that loss function and update the prior to get a posterior distribution. And since this is not similar to the Bayesian approach, because in the regular Bayes we have the likelihood based on the distribution data. So here we are going to create what is called a pseudo likelihood corresponding to the loss function, and using this pseudo likelihood and the prior, will update the prior in view of this pseudo likelihood, and what we'll get is a pseudo posterior. Okay, that approach is very similar, but because we have a different kind of, we have a loss function instead of the regular likelihood or negative log likelihood, this is called the pseudo Bayes approach. Now, the Bishiri et al., this is a paper, like in JRSSB, they recommended how one can create a likelihood version for a parameter corresponding to some loss function. Okay, so now here we have the loss function corresponding to the objective function Q0 I talked about. So first we condition on A only for beta, we just look at this loss function, and for some prior pi beta, how we can update this prior in view of this loss function. So that is the first part. And then we look at updating the prior for A with respect to the loss function for A, Q star A. And this Q star A is basically obtained from this, the Q beta A function I mentioned there. And for given A, we minimize that thing, then we have the beta tilde A, we plug it there. Then we have this function Q star A. So with this thing, we are going to mimic this framework presented by Bishiri and et al. I am in slide 15. Slide 15. And it says that, that if you have for some data the PDF, the sampling distribution of the data, and you have the parameter phi, the prior PDF pi phi, then what you will do, you update this prior by in view of this likelihood based on the data by normalizing this kernel, which is the product of the likelihood and the prior, which is precisely the posterior distribution for the parameter phi. Now, in the context of instead of having a likelihood, if you have some loss function S phi d, then this is how you are going to get this exponent negative W phi S d log pi phi star pi phi. Phi star is a suitably chosen quantity. And you know that phi star has no role in this normalizing this quantity to get the posterior for phi. So we basically, we have this loss function L phi d non-negative, and then Bishiri et al. Suggested that if we have a prior for phi, then this prior will be updated by this quantity. You just, this quantity here, I'm in page 16, that exponent negative W L phi d. Now question is, how do you determine this constant W? This W came out to be 1 when you have the likelihood. But when you do not have the likelihood, you have some loss function, you have to calibrate so that it receives suitable weight with respect to the prior. And that is actually given by an expression. This W quantity is determined through some algorithm presented in Bishiri and et al. And we follow their thing. And following that thing, what we find out that HOS corresponding to updating the prior for beta is given by this quantity W beta. And also a prior for beta can be taken to be a uniform prior, a flat prior. So corresponding to this W beta and the loss function Q0 beta AY, I'm afraid that I don't have much time to go back to show you this expression. This is basically a quadratic form in beta, positive quadratic form in beta. And this is what it is. This is basically nothing but a multivariate normal distribution for beta. And then once we have, this is a conditional pseudo posterior for beta given A. Now we have to determine the pseudo posterior for A. For that, first we have to get the pseudo likelihood for A, and for that we need to have the calibration coefficient for A. And I'm in slide 18, and we are using some prior pi A plus d bar to the power minus 2, which is a proper prior which we need to use. Otherwise, we will not get a proper posterior, because in this particular application, the loss function Q star A does not go to infinity as A goes to infinity. So for that reason, we have to use a proper prior. And corresponding to the prior, we get this calibration coefficient WA to calibrate this Q star A. And so in general, here, I have this R here. This R is equal to 1 actually, for general R. We derive this WA thing calibration coefficient. But if we, in our application, we took R equal to 1. So we get the pseudo posterior for A. And so this is kind of a very simple expression. And from that thing, we can basically generate A by rejection sampling. And once we have A generated from this posterior, we can go back to this equation 4 to generate beta from the multivariate beta. And once we have the collection of the pair beta and A, we can go back to the distribution for theta, which is again like theta I has normal distribution with the known mean depending on beta and A, and variance depending on A. And that way we just generate many vectors of thetas, beta and A, and from that we can make inference about our parameters or any functions of these parameters. Okay, so I am in slide 19. So we said that we generate 5,000 vectors of A, beta, theta 1, theta 2, theta m. And using these generated sample values, we can make point estimation, interval estimation of any interested parameters or parametric functions. Here we are interested in making inference about theta 1, theta 2, theta m, in particular, what is their best point estimate and prediction intervals. So here is a simple example that was viewed by Jiang et al. In their JASA paper, that they're looking at 23 hospitals, so and they're doing kidney transplants, and they're looking at those hospitals doing at least 50 transplants in 27-month period, and they're looking at the data. Is they wanted to estimate the how good are these hospitals in terms of their the graft success rate, or if you look at the graft failure rate, the higher the failure rate, the worse is the hospital. So they had some data, the YI, and also they had some covariate XI, which is basically the patient severity index, depending on what kind of patients they are operating on, like number of female or the degree of sickness of those patients, like that. And they found a, I am looking at slide 21. So they plotted the severity index against the graft failure rate, and if you look at it, there is, except that one point in this corner, northwest corner, no, not northwest, it's a northeast corner. There is an outlier there. Without that, you kind of have like a quadratic regression like that, or with the presence of the outlier, it's like a quadratic model with the outlier. Or maybe you can fit this red curve here corresponding a cubic model. So here we have the histogram for the regression coefficients, that when we have the quadratic thing. I'll just skip these things. So I'm in slide 23. I do not know how much time I have.
You have about 5 minutes.
5 minutes. Okay, so if I have 5 minutes, then I will just skip through these things. I will go to basically that, as I mentioned to you, we can create the prediction interval based on the values for theta you have generated based on the quantiles. You can compute the lower quantile, upper quantiles, and we have 95% credible intervals, and also we have 95% prediction intervals for the OBP. I did not give you the details on that. Now I'll go to our example of median incomes, that the motivating example. I showed you the map initially. So what we have here, we have 50 US states. I'm in slide 24. 50 US states and Washington DC, total 51 small areas. And these estimates of the median income are needed by this US Department of Health and Human Services. They use this thing to determine which families will receive, based on their low income, money in terms of subsidy or assistance program for home heating and cooling. You know that US right now is very cold, and they have to heat their homes. And the lower income families, they receive support from the government. And US Census Bureau was asked to produce estimates to determine cutoff, and the cutoff is based on the estimated 4% family median income in the state. So it is important to estimate these incomes accurately, and any families fall